Welcome everyone. Let's slowly pick a seat. We're going to start in a minute. Thank you. Good morning. Good morning, everyone. Thank you very much for coming early, 8:50. Hopefully, if you come from the Pacific coast, you don't have a big jet lag and you're already pretty much awake and with us. So we are going to slowly start. I have just a few things I want to mention before we get to the real talks, starting in 10 minutes. So first of all, thank you very much for coming. Welcome. Bienvenue, if you already picked some French words. Hopefully you will over the next few days. The very first thing I want to say is, of course, to thank Mila. We are in a pretty great venue here. This room is nice. We have a lot of supporting staff. Everyone at Mila really made an extra effort to make this happen. And this is certainly not easy, right? You have more than 150 people, lots of speakers, lots of organization to do. We have some of the supporting staff at the end there helping us with everything around screen sharing and so on. So thank you guys at the back. And of course, yeah, thanks. So far it's been pretty smooth. I just plugged my laptop, no problem, so thanks for this. Also, thank you to Lambda. Do we have some people from Lambda in the room? Yes, there. So thank you very much for the sponsorship. So thanks to them, we were able to have relatively small registration fees, which is always nice, right? And not only that, but also they provided us with some compute credit. Hopefully you received an email already about it. Definitely start setting it up. I'm pretty sure some of you already have. But I would say, whoever you are tempted, don't use all the credit yet. We need you to keep some of this for Friday. We will have some hands-on experience, training, some deep net. So try to reserve a little bit of this credit for Friday, but otherwise have fun and enjoy and try to queue some jobs. All right, and of course, none of this would have been possible without an amazing team of organizers. So some of them are in the back, but maybe some are in the room already. I see Luca here. Do we have any organizer here? Yeah, so thank you very much to all the organizers. So definitely, if you have any questions, whether it's about the workshop, Montreal, or anything in general, just walk up to them, ask them. They will be able to give you a lot of info. A lot of them are actually from Mila, so they will know, all the best places to avoid or to go to. So yeah, just feel free to go and ask them anything. In fact, they were able to arrange for me Justin Trudeau to welcome me at the border and giving me this personal collection of maple syrup. So thank you guys. They can do everything. All right. So more seriously, you can see the program on the website with the QR code here. I just emphasize here the program for today specifically. We will have some amazing talk, and this is also a very big factor to have a great workshop like this one. So thank you to everyone, all the speakers who agreed to participate. I want to mention specifically we have a group photo right at the end of the lunchtime. So please try to be on time so then we can keep everything on time in the afternoon. It's going to happen here. So try to be even a few minutes early if possible. We also have a great panel near the end of the afternoon. So make sure to think about questions and prepare anything that comes to mind throughout the day. I will say again, thank you to all the speakers for taking time for coming to speak. This is very, very important for everyone to learn about what you think is important in the field, what the next research questions are, what is still an open research question, and for us all to debate and agree or disagree. And of course, thank you to everyone who is sitting here. We have a lot of accepted papers. Some of them are oral presentations you will see throughout the days. We have a lot of speakers, and we have 158 registered attendees. In theory, there should be a seat for everyone, so definitely if you are standing, feel free to look around. You will find a place to sit. And this is very important. We want a community of active researchers focused on world modeling, whether you just start your research or you're already pretty senior. We want to emphasize interaction as the core of this workshop. And this should be happening naturally, because you see here there is this very nice figure done by Luca. Okay, he's not here, he left. Done by Luca, who shows what are the most used words in the title and abstract of the paper. A few things I want to mention. The first most important one is that world model is the main one, which is good. It means we are all here interested about the same thing and trying to solve the same problem. So just go and talk to anyone. They will share the same pain points as you, most likely. Another thing that may or may not be a good news, depending on your belief, is that if you look very, very carefully, you can see a very, very tiny LLM there, a very tiny generative word there. So it seems that the crowd is not so much into generative model and LLMs, which probably makes sense for world modeling. We will see at the panel and during the talks today. But so yeah, this is very, very interesting to see. So again, definitely feel free to walk up to people and just ask them what they are working on and interested in, because we are all here for the same thing. And the last thing I want to mention is really we need this type of event to happen. Hopefully there will be more versions of this. And in fact, there will be more versions of this. Let's try to make it, self-fulfilling prophecy. We need this open discussion for everyone to agree of what are the big bets on the next research, and also for everyone to think about the current limitations, because as you know, there is huge public scrutiny, media scrutiny into what AI and world models are capable of. And so we need to really be careful about what we work on and what we advertise, and we need to be careful about explaining what are the limitations as well, so that we make sure we are all on the same page and we are transparent about the current model capabilities. And so this can only happen if we have a forum like this to just discuss and brainstorm openly. So there will be more of this, again, centered on world modeling specifically. And hopefully we will see you in the next iteration. I hope to have more details on this in the closing remarks on Friday. Finger crossed. Let's see. And some a bit additional details. Probably everyone already did, but make sure to pick up your merch at the entrance. You have a top and a few stickers. Try to keep your badge up. I don't know if there is like a strict policy enforcement, but just try to keep it on you at least, so we can check that you are registered or not, especially when you will have the panel and so on. Food will be served in this room, but we have access, I believe it's this room, to sit, because here you see you don't have tables, so in case they serve you a pretty big T-bone, it's going to be pretty tricky to eat on a chair. So you are free to go and pick a table nearby or even in other rooms to eat. So this is, I think, the Agora Cafe. Okay. And with that, I also want to mention there is, if you're on the Slack channel, there is a meme competition if you go to the meme channel. So definitely try to join and start working on it. I have pretty much no experience in this, so I obviously try to come up with something, which is probably something that already exists. And this is maybe a bit biased. You will tell me what you think, but yeah, this is one just to get you started and thinking about what could be interesting to post in this channel. So definitely join the Slack if you can. and ask any questions you have there and contribute to this meme competition if you have some time. And with this, thank you again very much for being here. And now we are going to welcome our first speaker, Professor Jürgen Schmid-Huber. So thank you, everyone. Great. So thank you very much, Jürgen, for accepting to give a talk. We already see you there, so everything should be good to go. Great. So yeah, thank you very much. So I'm sure everyone here is already familiar with Professor Schmid-Huber's work, with some of the seminal papers, especially on formulations of world models dating years ago. And he's been director of the Swiss AI Lab and also at KAUST. So thank you very much for joining us remotely, and we look forward to your presentation.
Thank you. Can you hear me?
Yes, we can hear you. We can hear you.
Yes. I have a strong feedback on my side, but now it's gone. Okay, wonderful. The concept of a mental model of the world, a world model, goes back millennia. And Plato already suggested that we recognize objects by recollecting internal blueprints or templates. And today we totally wrote that. Well, that was 350 years before Christ. And today, only about 2,300 years later, which is a mere blink of an eye by cosmical standards, we are witnessing a boom in world models based on artificial neural networks for physical AI, for AI in the real world, and new startups on this are emerging. And to explain what's going on, I'll take you on a little journey through the history of general purpose neural world models. General purpose means working for a really broad class of environments. So in 1990, I studied adaptive agents that live in partially observable environments. Now, everything we know, everything we see, every little part of the environment that we study, it's a partially observable environment, and to deal with it, we cannot rely on methods that just take the current input and try to deduce from the current input what the state of the environment is. No, we need non-trivial kinds of memory in partially observable environments. And in 1990, I used the term world model for a recurrent neural network, an RNN, that learns to predict all the sensory inputs of an agent controlled by another recurrent neural network, the controller. And I always call these two things M, the model, the world model, and C, the controller. And now the sensory inputs, they include not only neutral signals like video and audio and whatever, but also the pain and the reward signals. The pain and the reward signals, which are special because they carry a value. They tell the agent whether whatever it is doing is good. And our robots, they have pain sensors, and these are special inputs, and you don't want to have them. So you want to minimize the sum of the pain signals, and you want to maximize the sum of the reward signals over your entire lifetime. And to do that, you can often profit from studying the neutral signals, the video that is coming in, and you can learn a lot from the neutral signals about how the world works. And then you want to use, as a controller, you want to use that knowledge to become a better controller that has more success in achieving its goal. And so back then in 1990, the controller C used the world model M to plan its action sequences through rollouts. So you just try all kinds of action sequences in your mental model, in your world model, and then you pick one that corresponds to an action sequence that is promising, according to what the world model currently knows. So mental experiments. And we did that back then when compute was about 10 million times more expensive than today, because fortunately, every 5 years, compute is getting 10 times cheaper, which is an old trend that has held since 1941. When Zuse built the first program-controlled computer, general purpose computer in Berlin, he could do one operation per second. And today, or 30 years later, one could do 1 million operations for the same price, and today maybe 1 million billion operations, something like that. So RNNs, recurrent neural networks, are general purpose computers in the same sense that your laptop is a general purpose computer, which makes them pretty powerful. And so this approach went beyond even earlier. Less powerful feed-forward neural network-based systems, at least since 1987, for fully observable environments where the assumption is that the current input tells you everything you need to know about the state of the world. And people who have worked on that include Werbers, Paul Werbers, 1987, he had papers about that, and Munro, also in 1987. So a model of reinforcement combined with a controller, which should learn from the model to optimize its actions, and Nguyen and Williams in 1989. And there were other researchers working on this type of system identification, as it was often called. So Paul Werbers always talked about system identification. Now, in 1990, we also have this thing which I like to call artificial curiosity for neural networks. Because in the beginning, my 1990 world model didn't know anything. And so somehow it had to learn from the data, from the environment, how the environment works. But the data is generated through the actions of the controller. Not only, the environment also has its own dynamics, but at least we need the controller to invent experiments, which are just action sequences, that lead to data that can be used to improve the model. And back then, the idea was super simple. I just said, okay, the controller C should try to maximize exactly the same thing, a linear function of the same thing that the world model is minimizing. And so back then, the world model was just trying to minimize its prediction error, which means the controller maximized the same error that the model minimized. Yeah, that was 1990. And today they call this a generative adversarial network because my controller had stochastic neurons in them. So it was a generative model, and the neurons were such that you could propagate through them. Actually, they were little Gaussians, and they produced two things, a mean and a variance, and so you could propagate through them a little bit like in style GANs. So if you know style GANs, that's a little bit like that. And so a generative adversarial network, but a pretty general one, because it's not only one shot, not only one action, and then evaluation of the environment. No, it can be many actions of the controller, and then you have maybe a robot being controlled by that, and you will get certain inputs. And now the goal of the controller C must be to find action sequences that lead to parts of the environment where the world model still can learn something, where it still has high error. So this whole system back then didn't learn like today's foundation models and large language models, but by downloading and by imitating the World Wide Web. No, it generated its own self-invented experiments to collect limited but relevant data from the environment, like a physicist or like a little baby. So it was a simple kind of artificial scientist, basically. Then, 1 year later, in March to June 1991, it became really clear that these gradient-based recurrent neural network models of 1990 did not work well in presence of long time lags between relevant input events. In other words, these RNNs back then, they weren't very deep. They couldn't look far back in time and memorize the important stuff, ignore the less important stuff. And to overcome this, my little AI lab at Tech University in Munich back then came up with various innovations. And in the process, we laid the foundations of today's foundation models and large language models. One of the things in March 1991 was the first transformer variant. I didn't call it a transformer, I called it a fast weight controller or a fast weight programmer, where there's one network that learns to program the fast weights of another network. And it learns to do that by using keys and values. I didn't call them keys and values, I called them from and to. And then it learns to generate mappings that are being applied to the queries that are coming in. And it's exactly what today is called the unnormalized linear transformer. Why is it called the linear transformer? Because it scales linearly in input sequence length, as opposed to the modern quadratic transformer, which scales quadratically. So back then, you had 100 times more input, and you needed 100 times more compute for that. And with the quadratic transformer, the modern transformer of 2017, you need 10,000 times more compute. So back then, nobody would ever have accepted a neural network that scales quadratically. But today, with the GPUs and the great progress in hardware, it makes a lot of sense. And then the other thing we had was pre-training for deep neural networks. So remember, the deep networks back then didn't work, but with pre-training, we could make them much deeper. And that is basically the P in ChatGPT. And in the same paper, there was this thing which is now called neural network distillation from one network into another, which also helped us to greatly improve the performance of deep neural networks, especially deep recurrent neural networks. And I didn't call it distillation; I called it collapsing the knowledge of one network into another. And then, and the other incredible thing back then was in the diploma thesis of my great student, Sepp Hochreiter, and there he invented deep residual learning, as it is called now, also 1991. So in the thesis, he found the mathematical reason for the reason why deep learning didn't work well. What was the reason? The vanishing gradient problem. As you propagate gradients backwards, they vanish, and that's not good. But he also had the solution, which were these residual connections. So you don't just compute a nonlinear function f of x, where x is the current input to your hidden layer. No, you compute x plus f of x. And suddenly you can get really deep networks and deep credit assignment, deep into time, also back then, and with recurrent networks. And that then became the basis, the core ingredient of the long short-term memory. And only a couple of years later, in 1997, then we had the journal publication on that. And of course, I'm happy that this is now the most cited AI paper of the 20th century. But the core idea, the deep residual learning, also led then to the highway networks, which we published in May 2015. But the same principle, it was a deep residual network, initialized as a residual network, and then it was suddenly 10 times deeper than the previous networks. And then a little bit later, half a year later, Microsoft used that, a variant of that, to win the ImageNet competition. And so that all goes back to 1991, to this miraculous year, as we sometimes call it. So now we are proud that the most frequently cited papers of all time, the two most frequently cited papers of all time, with the most citations within 3 years, manuals excluded, no manuals. They are directly based on this work of 1991. But back then, it was totally obvious that this by itself is not good enough to build a general purpose AGI, because that was just about the prediction part, the modeling of the data that is coming in. And yes, you can use that to build large language models and prediction machines, but you also need this other module, the controller, which exploits the world model such that it can learn to solve all kinds of tasks that it couldn't solve before. So the prediction machine, the foundation model, which is trained by, maybe by gradient descent on all the data that is coming in, that can be used to train a world model, but that by itself is not enough. You need the other networks that learns to use the world model to solve problems, and to solve them faster than learning these problems from scratch. Yeah. So then it's really important, again, this artificial curiosity thing, where one of these networks has to generate through its actions the data through which the other networks, the world model, is being trained. And the first idea was, as I mentioned before, that you say, okay, the intrinsic reward, the curiosity reward for the controller, is the prediction error of the model. And that's okay in deterministic environments, but there are many environments where certain things are fundamentally unpredictable. And my favorite example back then was the noisy TV. You have a white noise screen, and there's all these random things happening on the screen, and you cannot predict any of those. But the naive system is going to get glued to the screen because the error is high, so the controller will be rewarded for creating action sequences that expose the system to this noisy input. And that's not good, because nobody's learning anything from that. So in 1981, we did the next step and said, no, it has to be the improvement of M. So the intrinsic curiosity reward for C has to be the improvement of M. And then in 1995, we said, okay, there's a good way of measuring the improvement in probabilistic environment, and that's just the information gain, which goes back to Shannon, at least 1948. So we said, let's take the information gain as a reward for the controller, which is learning to create data, which is used to train the model. So the information gain is just the difference, the Kullback-Leibler divergence between what you thought you knew before you made the new observation, triggered by the actions of the controller, and afterwards. So there's a little bit of progress that you make, and you measure that, and that's the intrinsic reward. And then only by 2011, we were able to do that optimally through the work of Yi Sun, my first Chinese student back then, Yi Sun. And the issue is, if you want to do it optimally, you have to take into account that as you are collecting data about the environment, the information gain is shrinking, and you have to predict that and work with that. So optimal way of doing that in 2011. But then the other thing that we also did in 1991, that was to predict latent space, not just pixels and raw inputs, but the latent space. And for example, back then I had a hierarchical architecture for predictive neural networks that learns representations at multiple levels of abstraction and multiple timescales to overcome this deep learning problem back then. And there an automizer, no, it was called an automatizer. An automatizer neural network learned to predict the informative hidden units, the latent space of another higher level chunker neural network. I called it a chunker, and then collapsed or distilled the chunker's knowledge into the automatizer, and that greatly accelerated deep learning with long time lags and greatly facilitated downstream deep learning. So often it's really useful to predict the latent space of the hidden units and not just the raw pixels. then in 1992, another combination of two neural networks also learned informative yet predictable internal representations and latent space. And there were two neural networks, and one of these networks saw one input, and another one saw a version of that input, or from another perspective, or in some way related. And then they try to internally represent these inputs. And for example, the second neural network could be an autoencoder, and the hidden units encode somehow the information about the input. But then another network is trying to predict the hidden units. But that's not at all that is happening, because the hidden units also try to become more predictable without giving up too much of the information that they contain about the own input. And that's, I call that predictability maximization, complementing even earlier work on something I call predictability minimization, another way of using adversarial networks to create disentangled representations. So predictability maximization and minimization working in latent space. And then it took a while. In 1997, then we applied all these concepts of hidden state prediction, of latent state prediction to reinforcement learning. And we built controllers that follow a self-supervised paradigm that produces informative yet predictable internal abstractions of complicated spatial temporal event sequences. And again, instead of predicting all details of future inputs, that's not what you want to do in all cases. Instead of predicting all the pixels, the 1997 system could ask arbitrarily abstract questions with computable answers encoded in representation space, in its internal space. And it could even focus its attention on small relevant parts of its latent space and ignore the rest of latent space. So how did it work? So there were two learning reward maximizing adversaries. Is it called adversaries or adversaries? I think adversaries. And I call them the left brain and the right brain. I'm not sure whether the left brain, my left brain, and my right brain are playing a similar zero-sum game, but back then I called them the left brain and the right brain, and each tried to surprise the other one, occasionally betting on different yes-no outcomes of computational experiments. So they had to agree on computational experiments until they differed, and then they could bet on the outcomes, and the outcomes were somehow encoded in latent space in internal cells, and then they could learn something about the effects of complicated action sequences leading to binary yes-no outcomes, which can be encoded in one single cell in latent space. And it turns out that this type of self-guided learning and exploration can really accelerate reward intake. External reward. So that's all about zero-sum internal reward between the left and the right brain. But in addition, they want to maximize the external reward, and it helps them to learn more about the world in this way, such that they find it easier to accelerate the external reward. And then in the early 2000s, my great postdoc back then, Markus Rutter, who is now at DeepMind, but back then he worked under my Swiss National Fund grant at ITZIA. He even had a mathematically optimal, albeit computationally infeasible way of learning a world model and exploiting it to plan optimal action sequences, theoretically optimal action sequences for all kinds of computable environments, all kinds of environments governed by probability distributions that are computable, which is a super weak condition. And that was the famous AIXE model, of course, the AIXE model. And then in 2006, the formal theory of fun and creativity. What was that about? Well, it admitted that the AIXE approach, that was, yes, optimal, but there's no no computationally feasible way of implementing it. And so what is it that scientists, human scientists and babies really do in the real world? Well, they don't immediately come up with the optimal solution to some problem. No, they incrementally improve. And so I said, what we really have to do is, as we are finding more compressed explanations of all the data that is coming in through our experiments, that's coming in and improves our world model based on our experiments, as we are making progress, we are giving reward in proportion to the progress. So that was suddenly then a new, redefined type of curiosity, because now the intrinsic reward was not any longer just, the error or the information gain, the traditional information gain. No, it was the compression progress before and after. You get data through the experiments that are being generated. For example, you let 100 apples fall from 2 meters above ground, and then you get a video and all these apples are falling down. And then the basic insight is many of these videos have all kinds of predictable regularities. For example, if you have seen 3 successive frames of a video like that, if you understand gravity, you can pretty much predict what you will see in the 4th frame. Not everything, but a lot. And so you have to encode only the deviations of these predictions from the real observations in the video, which means you can greatly compress the video. And basically, that means there's a lot of compression progress. And as you are discovering physical laws, simplicity in the patterns that you are generating through your experiments, and that should be the true intrinsic reward. I think that's exactly what scientists and artists and musicians and everybody is doing all the time. And then 2014, we founded an AGI company for physical AI in the real world, based on your world models. We called it Nascence, pronounced like nascence, like birth, but written in a different way, spelled in a different way. NN for neural networks, AI for artificial intelligence, sense. And then we achieved lots of remarkable milestones in collaboration with world famous companies. But like some of our projects, the company may have been ahead of time, because real world robots and hardware are so challenging. And in the past 30 years, yes, our computers have become 1,000,000 times better per price. But the robots of today are not 1,000,000 times better than the robots that we had 30 years ago. They are a little bit better, maybe 3 times, 4 times better, something like that, but not 1,000,000 times. So the progress in hardware is much slower than in compute per dollar. Nevertheless, it's great that in the 2020s, new world model startups have been created. But then 1 year later, 2015, again this dominant topic of planning not through rollouts, what you do when you play Go or whatever, or what we did in 1990 with the simple system, the simple recurrent network planning machine. Instead of doing millisecond by millisecond planning like that, you really want to plan with spatial temporal abstractions and in more sophisticated world models. And that's what we did in 2015. So there we address planning and reasoning in abstract concept spaces in a report which I called Learning to Think, and then has algorithmic information theory and world models in the title. But Learning to Think, that's how it starts, 2015. And it goes beyond the earlier hierarchical neural subgoal generators and planners that we also had in 1990, where we already realized that millisecond by millisecond planning isn't really good. So back then we had gradient descent-based ways of finding subgoals in environments where the agent already has learned a whole bunch of action sequences, but then it tries to do something new, and maybe it can find solution by generating a sub-goal which reflects what it has already learned, because it can go from start to a sub-goal, and then from sub-goal to the goal. But then you have to find a good sub-goal, and we found a gradient-based way of inventing good sub-goals. But that was also simple compared to the 2015 system, which in many ways was just super simple also, because suddenly we said, let's just take the controller C, the recurrent network or whatever foundation model, and the world model, another foundation model, which has learned a lot about the world already. And now the C should become a reinforcement learning prompt engineer. A reinforcement learning prompt engineer that learns to create sequences of prompts, basically a chain of thought, sending stuff into the world model, and then the world model sends something back, and the connections that send stuff into the world model, into the hidden units of the world model, and the connections that come out from the world model back to the controller, they are all parts of the controller. So the controller has to learn them through some sort of reinforcement learning. And now the big question is, can the controller solve a new problem faster from scratch? Or is it easier to learn to send questions, queries, sequences of queries into the world model, which maybe knows a lot already about the problem, about the current problem, because it has seen all YouTube videos, and then get back something from the world model that can be used to greatly accelerate the search. So this is essentially a reinforcement learning prompt engineer that was described there, and it learns basically a chain of thought, and this has become pretty popular. 2015, and then 2018, one more step, the paper on one big net, which collapsed the controller and the model into one big net for everything. I call it the one big net, using my old neural network distillation procedure of 1991, as C and M are learning new stuff. C is learning new control strategies and new ways of addressing stuff in M to use that stuff in M for faster learning to achieve its goals. Then you also have you have the model itself learning something from the new data which is coming in, and so collapsing continually all of that into this one big net. And apparently something very much like that is what DeepSeek used to shock the stock market in 2025. And then the other 2018 paper, that was the one with David Ha, and that was very cool. And I think it was the one that finally made the world models really popular. All right, so what's next? As compute keeps getting 10 times cheaper every 5 years, the machine learning community is going to combine the puzzle pieces above into one simple, coherent whole and scale it up. And I hope that you will help with that. Thank you so much for your attention. Now what I'm going to do is I'm going to send you the link of a website that I made just for you, just for this talk. And then you can click at it. You come out in a little overview page of my AI blog. And I think the organizers are going to inject the link in the YouTube channel. And maybe some of you are going to use that to ask questions, because now we have Q&A. Thanks for your attention.
All right. Thank you very much for the talk. So we have time for questions. We have a few microphones here and there if you want. And maybe I will start with a quick question. So you mentioned, right, at the middle of your talk that you need to have hidden features that are informative yet predictable. And so I'm wondering if you could give a little bit more details into this, because when it comes to implementation, right, it's not straightforward to measure how is your feature informative or is it predictable, and did you find a nice way to implement this concretely and to find the right balance?
Oh yeah, well, so we use this concept in a whole bunch of different contexts, and I mentioned them. And the link that I just sent is actually a whole sequence of papers which are about different topics, which all use that principle. But yeah, so the first thing that I mentioned was where a prediction machine sends the unpredictable stuff to the higher level, and then it turns out that if you as long as you can predict, you don't have to store the inputs because you can predict them, then you can reconstruct the entire sequence by just knowing which unpredictable inputs were there. And up there in the high level, there's the higher level network, which tries to find patterns that the lower level network didn't find in the higher level stream of inputs, the compressed representation. And then once it learns that, you can distill that down. You can distill that knowledge down to the lower guy. And that is really useful for greatly accelerating deep learning or making certain deep learning tasks possible that were not solvable before. But then the other thing was another simple idea. That was the 1992 paper where you would just have one network that encodes the input somehow, for example, through predictability minimization. So it's trying to come up with a code of the inputs that has the property that that's a factorial code, a disentangled code, where basically the probability of the current input is just the product of the probabilities of the units, the hidden units that are now active to represent this code. Okay, so we had a way of achieving that, or at least a gradient descent-based way of going towards that direction. But then you can force the same system to become more predictable if you say there's another network and it has a different kind of input, which is related to the current input, but it's not the same. And now you want to model the predictable parts of the input, and you want to ignore the stuff that is not predictable. And then you just have a double term in the gradient descent function, and then it learns something that is less informative, an internal representation that is less informative than the perfect representation, but at least it's somewhat informative and it's predictable. And then in the reinforcement learning system, that was the 1997 system, that was more sophisticated, because there we said, okay, now there's a big latent space, a huge latent space of all kinds of internal cells, and the internal cells, they can have all kinds of values, and these values, they depend on the computations that the system had performed, all the inputs coming in and then being internally computed or recomputed, and it was a general purpose computer that we used back then. And then you can basically compute any abstraction, anything that is computable, any abstraction of any sequence that comes in, and you can encode it in a little tiny one cell. For example, the question could be, is there a pink elephant in the room? Okay, then there's a protocol. You have a way of scanning the room, and you don't know where the pink elephant might be, but you're scanning the room, and then after some time you say, no matter what kind of pink elephant that is, but at the moment there's no pink elephant in my room. So without predicting, or you say, yeah, surprisingly, there's a pink elephant in that room, and you just have a pattern recognizer that sees the input and maps it to this internal cell that says, yes, pink elephant is in the room, without encoding, the details of the reflexes on the skin of the pink elephant and so on. So any complicated spatiotemporal sequence of inputs can be any abstraction of that, any abstract properties of that can be encoded in a little cell, one yes or in a binary cell, 1 or 0. And now you can have two adversaries, and they are placing bets on what happens if I conduct this experiment. If I walk in this room and I can, and I open the door, and I predict there will not be a pink elephant in the room. But there's a protocol of deciding whether I'm true, whether it's correct, whether I'm thinking or not. And then the computation runs, and either the unit goes on or it goes off. And then you have performed maybe a magic trick, or your friend has performed one, and for some weird reason, he somehow has managed to make the pink elephant appear in the room, and you will be surprised, but you encode that event in just one single cell. And then back then, this system, which could bet on events like that, and where the two adversaries could try to figure out ways of surprising the other guy and trying to lure the other guy into experiments where one guy has a different opinion about the outcome than the other guy. But then, as they finally observe who is right, they learn from each other. And so the next time, similar things won't work as well, because now they are becoming boring. Boring is everything that you can predict well or that you cannot predict at all.
Thanks. Yeah, one question.
Hello, can you hear me?
I can hear you.
Thanks a lot for the talk. I wonder whether you could share more on what your view is on where the world modeling field is going to go in the next 10 years, and what would be the most important questions to be working on today?
Yeah, I think we are going to profit in the world model business from the same trend that large language models have already profited from. Large language models are kind of simple because they are just prediction machines, and they predict part of the data from other parts of the data, and all the data is always there. So they are being trained on everything you can download from the web. Now, what I've talked about today is very different. It's more like what babies do, where the data is collected through the experiments. You need at least two players, and one of them is it's generating the actions that lead to the data which is coming in and which is being used to train the model of the world. And the whole thing is a little bit more complex because you have these interdependencies, and then the controller wants to use the world model to predict which actions are going to be good for the controller to get more reward. But the model is maybe not yet a good predictor. In many ways, it's maybe a stupid predictor. So it still depends on additional experiments, just like what happens in human-driven science, where with limited world models, you keep adjusting and adapting and improving your world model, and then with adjusted world models, you suddenly start making very different predictions about what's going to be good for you and what's not so good. And the same thing, all these interdependencies, we have to get them under control in good ways, as we don't have catastrophic forgetting and all these things. And I think the one big net that I mentioned earlier, that's a good step in this direction. As the 2018 paper, which is based on the 2015 paper.
Thank you.
Do we have any other question? So maybe I can just add another point on this question. So you mentioned right at the beginning, and that's something everyone agrees on, that we need memory into world models. And so I'm curious to know if you think it's something we already know how to implement in practice, or it's also more specifically a research question to work on.
Yeah, no, of course, we haven't found an optimal way of doing that is both theoretically optimal and practical. We have certain theoretically optimal things which are not very practical computationally, and we have pretty practical things which are far from being optimal. And so all the stuff that I mentioned today, including what everybody's using now, like deep residual learning and LSTM and transformer variants and whatever, all of that is very practical, but it's clearly far from optimal. So there will be lots of progress just in improvements for these prediction machines. And there are so many techniques in machine learning that probably are going to get pulled out again and reused for aspects of that. But that's the small. It's more like what has happened to cars. So cars were invented in the 1900s and in the 1800s, and the principle is very simple, and the combustion engine is a pretty simple concept. And today the combustion engines are the same as back then, except they look really different because you have all kinds of new complicated things. If you look under the hood today in a car, you have all kinds of little cables and software for injecting the fuel in very special ways, such that it burns optimally or more optimally. And the principle is still the same from the 1800s, but it's improved in many ways. So the principle is the same, but in the 1900s, lots of improvements have come, and we will see the same thing in all aspects of neural network research. So the principles are all from the previous millennium, but you get all kinds of refinements all the time because so many people are working on that, and they are finding a little improvement here and a little improvement there all the time.
And so maybe going back to my earlier question, so you mentioned a lot working with discrete embedding, discrete encodings of the input, and that's something we've been seeing also in the community, a shift between continuous and discrete. And working with discrete has some nice benefits. It's maybe easier to estimate information and predictability. So I was wondering if you have some comments on, do you think discrete is enough? Do you think you actually should have continuous in some specific cases?
Yeah. So in the end, in our physical world, all of that is going to be driven by progress in hardware. And what's the future of hardware in our universe? Well, it's going to be lots of little processors in a volume, not on a flat chip, but in a volume with lots of short connections and few long connections. And you will have an enormous heat problem there because you have to get the heat out of this volume, and so you want to minimize communication costs. That's why you have many short cables and few long ones. And then this looks a lot like we have in our brains. Our brains are built a little bit like that, but also the old Cray supercomputers of the 60s were also built like this because that's dictated by the three-dimensional physics of our world. So lots of volumes, and lots of processors in a small volume with connected through many short cables, maybe even light beams, and lots of and few long cables. So to deal with the heat problem, you must make sure that everything that you don't need for computing something is switched off. So if you look at the current NVIDIA chips, they are all the transistors are active all the time because you have the silly concept of grain descent, which requires everything to be a little active all the time because although almost all of these computations are multiply something that is close to zero to something with something else which is close to zero. So that's not what this brain is doing, which is much more efficient computationally. No, as I'm talking to you, most of my 100 billion neurons in there are switched off. Just a few millions probably are active. Otherwise, my head would explode. So it's clear that in the long run, the hardware is going to be more like what we have in the brain, although it is going to use different chemical substances and copper wires and light beams and whatever. But the principle, the three-dimensional the principle of three-dimensional computation is going to remain the same. And so all our algorithms will tend to exploit that, and they will go towards that. Just like today's algorithms, they exploit what the current GPUs can do, but it's not the end of the story, of course. And there you have a lot of room for stuff that is not gradient descent, but where, just a tiny fraction of your network is active, and most of them are not active, and the network itself learns which of these of its own parts to switch off to just save energy. I had a paper on this in 2011, self-delimiting neural networks, slim neural networks, self-delimiting neural networks. And I think what's in there is still valid today. And as hardware is adopting these principles, it's going to drive all the algorithms and software that we are going to come up with in the future.
Thanks. So we have a question from YouTube. I will ask in a minute once we get it back, but maybe just a last one from me. So I think what you want to disregard or not in your representation is going to be very dependent on what task you want to solve post-training, right? So maybe some details about the skin of the elephant are not really useful to predict where it's walking, but if you want to predict maybe some disease or some fine-grained task, it's actually very useful. And so I'm wondering, do you think there can be really one world model useful for all tasks? And do you think that's something we should try to get, or you want something that's good for 99% of the task and there is inevitable fine-tuning that needs to happen? Like how do you reconcile this type of conflict?
Yeah, so I look at myself and I have only one world model, but it's consisting of lots of little compartments. And I have learned through exposure to lots of problems to switch on just, a handful of promising compartments as I'm trying to solve a new problem. So you might argue that actually I don't have just one world model, I have a million little world models for a million little domains, and that's not wrong, except that they are also connected. And suddenly I see analogies between the problem solution in this domain and the very domain over there, which has a similar problem solution. And then often I can learn something from there. And that can be encoded in general purpose world models, like recurrent neural networks, which are as general purpose as your laptop. So all these compartmentalizations and everything that can be encoded in a general purpose computer, which means in the end, we should just focus on one world model that learns to compartmentalize itself such that whatever is efficient and energy efficient and energy saving is surviving in this collection of little domain-specific knowledge islands, and just let the model itself learn to decide when to look at the broader picture and get insights from other parts of this big computer, and when to focus just on a tiny little model of a particular domain where the world model has learned that this usually works best in situations like that. So it's going to be adaptive all the time, and it's going to change its opinion about what is working and what is not. But that's just the nature of life. And my favorite way of thinking is really about having one simple system, one simple huge general system that learns to do all the little things by itself.
Thanks. So we have a question on YouTube, so let me read it to you. World models can be used in two ways for control. One as a simulator to train an explicit policy, like in Dreamer, or two as an internal model of the policy itself, like TDMPC. So where do you see more potential between those two applications?
Yeah, again, if you have general purpose world models collaborating with general purpose controllers, both of them being recurrent networks or recurrent transformers or other types of foundation models where always have feedback of the output back to the input such that they can think about what's going on. Whenever you have general purpose systems like that, you can have all of these. And you can, what should be the goal? The goal should be wire the system up, define its objective function such that it can learn by itself to choose when to use this approach, when to use this approach, learn from experience, whether its expectations worked out or not. And and so if you look at our more recent paper since 2015, that's basically what we are striving to achieve.
Do we have any other question? So maybe I will throw a very last one in. So as you mentioned, right, you learn a lot by interacting with the environment or relying on the data to see what's predictable or not. And so naturally, my question is, do you think we have such high quality data to learn world models from? Or do you think even typical data, let's say from the internet, some of them could violate, right, the physical law, but do you think we can still train from those at scale, and we hope that at scale we will discover the ground truth physics of the world? Like, what's the impact of data quality, basically?
Yeah. So this is actually also already in the 2015 paper. The world model doesn't have to be trained on on just the data that you get through the experiments of the controller. No, maybe the world model has seen all the YouTube videos. Maybe now the controller wants to learn to throw an object into the waste paper basket over there, and it has never done that. But there are millions of YouTube videos where humans are throwing stuff, and basketballers are throwing stuff, and robots are throwing stuff, and even animals are throwing stuff, and whatever. And just from these videos, if you can encode these videos, in these encodings, there's a lot of algorithmic information that's relevant for what the controller wants to do now, which is take this whatever is it, piece of paper and throw it into a waste paper basket over there. So what you now have to do, and that's what the 2015 paper is about, you have to learn to address through activations, through prompts, the important part, the important internal hidden units of the world model, wake them up, and go from there maybe to yet other hidden units that also contain relevant information. And it has to learn to address, among the trillion things that the world model has seen, to address those that are relevant for throwing stuff into waste paper baskets. And then with changing a few bits, as the prompts are being translated into answers coming back to the controller, then use that information to just change a few activations, a few bits here and there, and then have a first very good trial without ever having done a single trial like that, and throw the piece of paper into the waste paper basket in a way that wouldn't have been possible by learning from scratch, where you would have had 100 trials or something. So it is, you can learn a lot just from observing other things, from the neutral signals, from the non-goal directed inputs. So from the video and the audio that is coming in, it contains so much algorithmic information about solving all kinds of problems. And the special signals, the reward signals, maybe you get a reward whenever you hit the waste paper basket with your piece of paper. These are rare and they are very limited, but they represent just a tiny part of the world. And this tiny part of the world is in many ways defined through the information that you can get from all these videos, which have nothing to do with your own actions. Nevertheless, there are lots of people in these videos that look a little bit like you, and they also have hands, and you can learn a little bit from the videos how to move these hands. And of course, as they don't give you the precise motor signals that you need to address the muscles of your hands. But because you already have maybe done other things with your hands, you can reuse the subprograms that you have in combination with what you learn from these videos. And the important thing is really that the controller, through lots of examples with lots of different problems, learns to address in a better and better way those parts of the world model which are relevant to whatever current problem it wants to solve.
Thanks. So we are at time. So let's thank Professor Schmid-Huber again for the talk.
Thank you, my friends.
Thank you very much. And next we have Professor Sherry Young.
Did you forward that to the channel? Bet. on the outcomes. And the outcomes were somehow encoded in latent space and internal cells. And then they could learn something about the effects of complicated action sequences leading to binary yes/no outcomes, which can be encoded in one single cell in latent space. And it turns out that this type of self-guided learning and exploration can really accelerate reward intake, external reward. So that's all about zero-sum internal reward between the left and the right brain. But in addition, they want to maximize the external reward, and it helps them to learn more about the world in this way, such that they find it easier to accelerate the external reward. And then in the early 2000s, my great postdoc back then, Markus Hutter, who is now at DeepMind, but back then he worked under my Swiss National Fund grant at ITZIA. He even had a mathematically optimal, albeit computationally feasible way of running a world model and exploiting it to plan optimal action sequences, theoretically optimal.
So this is nice. Okay, I think we can slowly. All right, everyone. If we can slowly get back to our seats for the next talk. Great. So there will be a coffee break afterward, so no worries. We will get the caffeine shot as needed. So right now, we are very happy to have Professor Sherry Young with us, with a professor at NYU Courant and also a research scientist at DeepMind. She's been doing very incredible work in robotics, embodied agents, and really large-scale pre-training and post-training. So pretty excited to see the next presentation. So help me in welcoming Sherry. Thanks.
Yeah, thank you for the introduction. And hi, everyone. I'm Sherry. I'm very excited to be here to tell you about a very exciting line of research around pre-training world models and how do we use pre-trained world models to post-train physical agents. So the context that we're focusing on is in a scenario where we have some agents interacting with environments. And agents today, like Yuri was saying, are parameterized using deep neural networks. And the environments are some environments that agents can take actions in and get some rewards on how good are these actions and what happens after these actions are executed. Just to make it super concrete, one example of agents and environments is the game of Go, where the actions are where to place the pieces and the rewards are did the game win or lose. And we saw that with that, we actually have already achieved superhuman agents such as AlphaGo in this particular agent and environment settings. And if we move on to other agents and environment settings where we have large language models interacting with a terminal, executing programs as actions and getting feedback of program execution results, outcomes as reward, and the next state, again, we see that large language models can achieve superhuman performance and getting these gold medals from these programming competitions. So if we were to step back and think a bit about what is the technique that really empowered large language model as agents to achieve these large superhuman performance in these highly competitive programming settings, there's actually that's something that's very important for large language models to work, which is post-training. And we know that GPT-3 was not really useful without post-training, without this RLHF reinforcement learning from human feedback, and where human preferences are gathered to train a reward model, and then the reward model is used to perform reinforcement learning to update the pre-trained model. And if we look at the state of robotics right now, we actually see this huge gap, right? We have robot foundation model companies building better foundation models, and we have robot data teleoperation from academia, from companies as well, trying to collect supervised data for robotics through teleoperation. But we're in nowhere close to perform post-training learning reward models or performing RL for physical agents. So you might ask, so what is the result of not being able to do post-training? The result is that today robots just work in demos, but they don't work in practice. And the reason is being without post-training, they actually cannot generalize to arbitrary scenarios. This is an example where we have some distractor objects in the scene, and all of a sudden the performance of policies just drop dramatically. So coming back to the problem of post-training, why is it so hard to do post-training for robots? And the main reason is because of this gap of the physical world, right? Because we cannot get reward or run RL directly in the physical world because robots have to execute one action at a time, and they can only be training one particular scene at a time because of the physical constraint of where the robot is located. So as a result, they don't actually get to see many diverse settings or being able to search through broad actions. So this is why physical post-training is hard. But if we look at the scenarios where language models are succeeding, it's really in this virtual setting with virtual post-training where that massive amount of actions can be searched through these parallel rollouts, and then at the same time, diverse problems, configurations can be used to train these models. So since we're at this workshop, right, let's just be optimistic and think about what happens if we actually can train a world model to overcome this major bottleneck of physical agents, which is this low-cost having this low-cost virtual environment. So let's say we train a world model from data that runs in the cloud. Well, this will enable robots to, query the world model in parallel in the cloud. And also, if the world model is perfect, then it should be able to simulate interactions from arbitrary initial frames. So this is the hope, right? And how close are we getting there? So if we're closing the post-training gap for physical agents through world models, And we're probably gonna have this pipeline, which is what was successful for language models. So this is going to be the focus of today's talk, attempting at closing this post-training gap. And specifically, the talk will be divided into two parts. We'll first talk about how do we exactly pre-train world models, and what does even pre-training mean? Like, what are the data, what are the models we need to use, what are the parameter sizes, and so on. And after we talk about pre-training the world model, then we will talk about how exactly do we do RL and reward models with rollouts from the world model. So let's start with pre-training world models. And specifically, I'll talk about two lines of work where we will specifically focus on video generation as world models first. So one thing I want to point out is that there are many ways to do world modeling. Like Jürgen was saying that we can have recurrent neural networks, and this afternoon we might hear things from JAPA latent world models, and even people are working on 3D world models. So there are many ways to do world models, and video generation is only one way. But I want to focus on video generation because I want to talk about some of the similarities I've seen between video generation and language models, which is some place that we already have experiences from, and making some analogies between video and language. And I'll share this Unisim, which is one of the work that trained a video generation model as a world model at a large scale. But then I will, these two work were back in 2023, 2024, right? So, and we're 2 years past that. I want to talk about some of the exciting work that we have going on at NYU in terms of scaling world models through pre-training. So let's start with some background on world models. Like, the history of world models really goes back a long time, but and the definition of world model today is somewhat blurry, where people just use the term very broadly. But if we go back to read these papers, we can always find some precise definition for what a world models can be grounded to. In this particular case, we're going to look at some visual world models where we have some observations like previous frames in the game. And then the model is essentially a learned dynamics model from data that can take in these previous frames, and it takes some actions, where you can think of actions as keyboard controls in these games. And the model just simply learns to generate the next few frames conditioned on the previous frame and the keyboard inputs. And we see that even back in 2018, we could already get these models to generate pretty realistic rollouts to the game. That's very similar to what the ground truth game had looked like. But there was the challenge of training world model is a very data-heavy task, right? So we were only able to do this in these game settings where we can have almost unlimited data by just have a lot of gameplays. And whereas in real world, these were not easy back then. So, and then if we were to think about, so what enabled us to really work on world models today, right? And I think there are two special factors. There is internet scale video data at our disposal, thanks to what people have discovered of using text from the internet to train large language models. And then there is also the transformer architecture that's exhibiting very favorable scaling behaviors. So then the question is, if we just get all of these video data from the internet and somehow annotate them with actions, and then just shovel all of the data into this single transformer-based video generation model, what are we gonna get as an output? What are we gonna get as in return, right? So to answer that question, like, is this gonna work? Just take internet data, feed it into a huge transformer. I think to kind of get answer for this question, we should probably think about, like, why did this work for language models? And then there is an observation that one of the reasons for which language model worked is because text is a unified representation of information. For example, code, Wikipedia articles, and math, they're all pretty different, but nevertheless, they can all be represented as text. And not that text is just a unified representation of information, but at the same time, text generation is a unified interface of tasks. For example, a lot of tasks can be casted as a text generation task. For sentence completion, for example, text is a unified representation of information and a unified task interface. You can also do translation. You can also have some chatbot answering the question, are you sure? Text is a unified representation of information. And when we have text as a unified representation and text generation as a unified task, we can train a single model and get the model to reason using text to solve math problems or to solve coding problems. So if this worked for language, then why might this work for videos, right? So here we have the same observation, which is videos are also a form of unified representation of information. You have videos of human, videos of robots, videos of physics, videos of how to do things. They're all in the form of videos, and at the same time, video generation is also a unified task. So what do I mean by that is if you have your video generation model predicting the frames conditioned on the action of cutting peppers, and if the model can accurately predict these frames, then the model has kind of learned some notion of how to cut peppers. And so this is, the task here is the model needs to predict how to perform this task in the visual space. And if you change the task just by changing the data, where you give the model now some delta x, delta y of how the robot is moving and effector poses in the physical world, and then the model learns to predict the next frame. And in some sense, the model has, if it can predict it accurately, right, it has kind of learned some notion of physics where if the robot arm is on top of the cloth and is moving around, then the cloth needs to move with the robot. So just through this prediction task, the model has some kind of knowledge of physics where the cloth needs to move with the robot arm. And if we have a lot of simulation data, again, we can just put these data through this model. These data might already be our accurate understanding of physics, of locomotions and movements, of how things should be, how next frames should look like when we have these simulated dynamics. And even if we don't have videos, we can generate a single frame video conditioned on text where the model will, again, have some notions of what throwing is and what frisbees are. And if we have some egocentric navigation data conditioned on the camera controls, we can get a model that knows what it means to be navigating in the 3D space. So it seems like we have this connection between videos being a unified representation of information and video generation being a unified task across many different domains. So in this work, back in 2023, we basically just took all of the internet data that we could find and labeled them with text actions. And for the data that already had low-level control actions, we use those actions as well. And we feed all of these videos into these single video generation model. And this is something that we got in return, right? And I just want to show you, to ground it concretely, what exactly did this world model look like. So for a world model to be a world model, it should support interaction with any scene, right? So if the server is running, I should be able to take a picture of this room, upload the picture, and have people start interacting with objects in this picture, right? So this is showing, okay, we have some previously generated frames, and let's say we give the action instruction to the person in the image and ask the person to wash hands. And you see that the person actually, follow instructions and went and washed their hands. And the world model also needs to support multiple steps of interaction, right? So after the person washed their hands, we should be able to ask them to shut off the water. And not just that, they can perform diverse, they can wash hands, but they can also choose to do something different, right? Like pick up the ball or cut carrots or something else. Or even navigation, right? So the person can sort of turn away from the kitchen. So all of these videos are generated, and this is particularly interesting because we never enforce any knowledge of dining rooms are next to kitchens, right? This is all learned from data, and when we say turn left, it's just very natural for the model to imagine that there is a dining room next to the kitchen. And when we ask the person to turn right, there's a wall, right? All of these are data-driven. And I think this example is also pretty interesting. It's showing how we have compressed the knowledge in a lot of different videos into the single model that we can elicit using language where if we ask a person to uncover a napkin and have a toothpaste show up, you can see the toothpaste shows up, and then we can ask the person to interact with the toothpaste in different ways, like pick it up or move it to different directions. But because we've compressed all of the internet video data into this model, we can also have a different object, right, being elicited from this video generation process and have the person interact with this object in a purely data-driven way. So you can see the distance between the two fingers is really fitting the pen, whereas there's really no constraints on us specifically enforcing that constraints. And same thing, same model, right? Now, if the initial frame is some robot, we can give it language instructions to have the robot perform some tasks as opposed to control humans. And it's the same model. We haven't changed the model. This is all generated by the same model. So I think to look back on what happened after the Unison work was there was an emerging amount of applications of world models, especially around self-driving, where Gaia developed video generation models that can be used to simulate different kind of driving scenarios that could improve self-driving in these extreme weather conditions. And there's also applications in robotics, which I will talk about later in this talk, where we can control robots in this generated world model and do policy evaluation or policy improvement. And more recently, you probably saw from Twitter that there are these game settings from Genie where you can create this very highly realistic and controllable games of controlling a fish to escape the kitchen, for example. So to really reflect on what we talked about for the first part of the talk, we've talked about video generation has a lot of analogies to text generation, and they're also good at compressing internet scale knowledge into a single transformer that we can elicit later on, having objects of, toothpaste and pens being simulated and interactions being simulated. And then when we have this model, there is some kind of generalizable control that we can give to the model across many different domains. Okay, so this is 2024. 2 years has passed. I think the question of how big should these models be, how much data should we give to these models, what's the best architecture for training these models, there are so many open questions. And despite these questions not being answered, world models get criticized a lot, right? Usually for the reasons that they don't generalize, for example, and there's a lack of control. This is an example where in reality, the actions actually open the gripper, but the world model actually failed to simulate this action, which is opening the gripper. And there's like a lot of hallucinations from the world model, like the object will change color from orange to red, and the bag of chip might disappear during the manipulation process when we generate these videos conditional actions. So there are many ways to sort of tackle these challenges, right? But I think one question I wanted to ask here today is, can we solve these problems with scaling, right? Or how far could scaling get us? And to sort of answer this question, me and my lab students have been working on just preparing the largest action-rich data set that we could find, right? And what do these data sets look like? These data sets include a lot of robotic data from academia. This is the JOY data set, where people place camera at random locations to take a video. And these are all robotic data set from academia from different labs. And there's also multi-view data where there's wrist camera mounted on the robot wrist, and you can see that the views at the bottom and then the views at the top are simultaneously videos of the same activity. These are ground truth videos. And we also have a lot of video data from navigation, and we also have a lot of video of rich human manipulation, right? There are like these data sets where people wear tracking devices, and we actually get information of where the hands are. And so we can train a pose-conditioned video generation model to simulate human interactions as well. So these are the videos, and when we look at the actions, they're actually a lot more heterogeneous, right? We're talking about like really rich actions, not just text, but more precise controls. And this include end effector poses where people are putting their fingers. This also includes things such as joint states, angular velocities, angles of robots. And this kind of heterogeneity of the action space has actually bothered the robotics community for a very long time, because there isn't a very straightforward way to unify all of these different action spaces, impedance parameters, which is very robot specific, right? So, we had to make a design decision on, okay, what do we do with these heterogeneous actions? And we did just the most simple thing, which is whichever data set that has whichever kind of actions, we just represent them using the raw values of the actions themselves, which are some continuous vectors, right? And when the data set have all three, we just randomly pick one during each training step and switch to another during another, randomly switch to another during another training step. But the hope is that we're essentially building this model that's learning to map the deltas between whatever control space that's in to the deltas of the observation space of what would have changed, right? And then the hope is that this mapping is somewhat general, even though the action spaces are different. But in terms of the deltas, in terms of how they change, and learning this mapping to in terms of how the observation space will evolve, that's the hope that despite the action spaces being heterogeneous, we can still learn this mapping from delta actions to the delta observations fairly easily. So that's what we did with actions. And so what we did with data is we were really trying to see, okay, how much data could we get without paying, right? So this is outsourcing all of the available data sets from the internet. So we were at 10 million videos with rich actions, where rich action means that there is robot poses, there is angle information, like very precise controls, not just text. And so the data set has roughly 40 billion tokens. And if we look at how that compares to language model, it's only 1/10 of the GPT-3 pre-training data, right? But this is not to say that this is all the data we have, because this is how much we could get from academia without paying robot companies that are doing a lot of teleoperation, and those data are in vast amount. So this is how we're at 1/10 of the data used to pre-train GPT-3, but nevertheless, that's a good start. And then so we looked at the models, and so the particular model choice we made is this latent diffusion model, and that was initially developed for image generation, where images are turned into latent tokens through some VAE encoder, and we can train a transformer model to autoregressively predict the patches. And then there is some follow-up work from diffusion forcing and also from robotics that uses the same architecture, but with the additional action conditioning, but still use a transformer backbone to perform these latent rollouts in the latent space. And so particularly what we did is basically we scale up the parameters of this transformer model. We increased the number of layers in the transformer. We increased the embedding size of the transformer model. And we trained models of various sizes, from 600 million parameters all the way to 8 billion parameters. And this is the training loss measured in, we train a latent diffusion model, so we have a noise MSE, and this is the loss that's measured in that space. It is continuous for this case, yeah. Yeah, I think there are also ways of discrete modeling of, I think there's work on like using VQVAEs to get discrete latent, but for this particular work, because we're doing diffusion on the predicted next token, so we could model the continuous latent space, yeah. Right, so yeah, so I think the interesting observation here is that the larger we make the model, the lower we get the loss. And there's no signs of slowing down. We're at 8 billion parameters now. It's already taking us months to train this model, given academic compute, although NYU is already very generous in terms of sharing these compute with some of us. And the question is, well, does the lower loss actually translate to better performance, right? So we actually performed some measurements, and the AB model was still, too early into training, so you don't see the metrics here. But nevertheless, we see that these video generation metrics, so LPIPS and SSIM are basically perceptual similarities and structure similarities between the ground truth image and the generated image or generated video conditioned on the same sequence of actions as what happened in the real world. And we see that the video generation metrics always also improve as we have larger and larger models. So this is very encouraging, right? Because it's also very exciting. We're late to doing research for language model pre-training, but there hasn't been, chinchilla scaling laws for pre-training video models. And the fact that we can start this research in academia, I think, is something that's quite exciting. And here I just want to show you some examples of generated videos from the model and then compare them to the ground truth, right? So I think one thing that's very special about action condition video generation is that it's a fairly deterministic task, because given the action sequences, there's only certain ways the robot arm can move. And so we can actually have a pretty good visual evaluation as well just by looking at the generated videos against the ground truth video. And in this case, you can see we can actually get comparisons of robot manipulation, and even maybe at the bottom left is some dexterous hands, right, conditioned on these pose information. And the second column is this wrist camera views, and the third columns are some human hand manipulation. Last columns are some navigation examples. And I want to draw your attention to the last video on the third column, this particular video. So this particular sample is interesting for two reasons. One is that the world model is actually able to capture the uncertainty of when a plate was removed using these pose controls. A plate of a different color could show up, right? So the ground truth video, it was, had this color, and the generated video had another red plate. But so Another interesting fact is you have to look very closely. You can look at what happens in the generated video to the plate after the head moves away. And you can see that the plate actually wobbles. Okay, so maybe try to see again. It's wobbling on the table, whereas in the ground truth, it didn't really happen. I think this is kind of interesting because, in the ground truth video, things didn't wobble. So like the model must have seen this physics of plates can wobble on the table from somewhere else, right? But nevertheless, the model has some kind of physical knowledge, like it could simulate this motion of like a plate wobbling on the table, which I think is pretty fun. So, and then the question is, why should people care, right? So right now, the state is that everyone will try to train their own action condition model. But we did some experiment where fine-tuning from a pre-trained model, because the model has seen such diverse actions and has learned to map these diverse action deltas onto the observations. So when we fine-tune from a 4B model, which is the yellow line, we actually see a much lower loss, both in terms of at the beginning of training and at the end, than if we train a model, 4B model from scratch using this few data collected in some new domain, or training a much smaller model. So we are going to release these pre-trained models once they're done, finished training. And this is why you can see it's manuscript in preparation for scaling world models for pre-training, but it's really beneficial for communities to be able to fine-tune from pre-trained world models and get much better models to do research that they care about. And of course, there's the alternative of like fine-tuning from a text-to-video model, which is kind of like what people are doing now. But we found that fine-tuning from a text-based model actually is very data inefficient because the model hasn't really learned to respond very accurately to very precise action controls. And text condition model like sometimes would hallucinate to satisfy the text instruction, and it's actually harder to fine-tune from them, much harder than to fine-tune from a pre-trained model that's trained on rich actions. So yeah, this is an example where we had some in-domain data, where some out-of-domain data where we collected for this manipulating objects of where the object is a cloth, and you can see that the generated video of these soft object interactions actually look quite similar to what the ground truth looked like, and this is very hard to do with traditional software simulators. But for video models, it's much easier to learn these soft object interactions. And this model was only trained using 200 trajectories from this new domain. Okay, so to recap, we sort of brought up the question of like, is scaling going to solve our problems, right? And as of today, I do not have that answer for you, but I can only say that scaling shows promising science. We see that losses are getting lower, qualities are getting higher when we have larger and larger models. And whereas the model is still underfitting the data, we're at 8 billion, we're still underfitting the data, and it's quite exciting to imagine what if we scale up the parameters to 500 billion models to the size of today's frontier large language models. But there is already promising science that fine-tuning from a pre-trained model is a lot better than training from scratch, and there is already kind of physics being modeled in the world model where the plates wobble. So there's definitely science of life, and it's exciting that we're doing this from the academia setting. Okay, so maybe that's about what I want to say about pre-training, and I want to switch gears a little bit and talk about, now we have some pre-trained model, and what are some of the things that we can do with robots in this world model, because we talked about the importance of post-training, right? The robot being able to learn from any scenes from the world model and being able to interact with the world model. So, and specifically the work I want to highlight is the World Gymnast, which is just released a few days ago, where we actually run RL training in the world model and evaluation on the real robot. And this work was built on World Gym, which is a previous version of the work where we only focused on evaluation. So, if we are talking about post-training with world model, maybe we should first think about what are the alternatives, right? So there are two alternatives. One is just doing post-training in the physical world, and I believe all of you understand why this is hard, because robots can break, and it's hard to also reproduce results from different labs, because every lab uses a different robot, and they have a different setup initial frames, and these policies are highly sensitive to these initial setups, so it's really hard for a robot lab to reproduce the results that was developed from policies from another lab. And the alternative is, okay, we can maybe use a software-based simulator. And this is definitely a valid approach where people are building better and better simulators. But, and especially for tasks such as self-driving or locomotion, where maybe visual aspect is extremely important, where people can actually build simulators that doesn't have to require an extremely realistic visual simulation. Then those domains, I think, training policies in simulators is perfectly great. But for manipulation, I think there's just been this long-standing gap of sim-to-real transfer, where there are two issues with simulators. Maybe one is the visuals don't look highly realistic. You look at it, you can still tell it's not the real world. And also physics are hard to program precisely. And we have to program them every time for a new scenario, right? They don't work generalized out of the box when we have some new settings. So these are the kind of alternatives to world models when we say we want to do post-training for robots. And so in this work, that will actually also be talked about at this workshop. So we worked on this world gym. We named it world gym because it's a world model, but it's like a gym. So robots can go there and train themselves. That's where the name came from. But the idea is we just tried, okay, what if we try to roll out different robot policies in the world model that's trained to conditional actions to predict future frames. And with the predicted performance from these generated rollout actually correlate highly with the real world success rates, right? So that's the question we're trying to ask in this work. So what we did is we took these robot policies from different universities, Octo, OpenVLA, and RT1 from Google, and we roll them out in the world model. By rolling out, we mean condition the policy on the initial frame, and then get a sequence of actions, execute those actions in the world model, get the last frame from the world model, feed it back to the policy, and the policy can generate the next sequence of actions, and just do this in the loop until we have a full video. And this is one of the videos that's generated by OpenVLA, by one of the vision language action policies. And when we have this video generated by the world model, we can use a vision language model as a reward model to judge whether this generated rollout was successful or not, right? And so one thing is that this allows us to very easily evaluate any policies. We can take policies developed at any school, give them the initial frame, and see how well they do. And this is comparing OpenVLA, which is one such vision language action model for performing this putting eggplant in the pot task. And all of these videos are generated conditional actions predicted by these policy. And Octo performs a little worse. It's a policy that was developed a little while ago. And then RT1 is an even older policy, and then the policy just does something that's so random, and even the world model starts to hallucinate. But nevertheless, it's very obvious from us to just look at these video rollouts to have a pretty good sense of which policies are better than other policies. So this is rolling out policies in the world model, but we can also create a lot of tasks using the world model, because now we can create an arbitrary initial frame. And in this case, we use Nano Banana to edit the colors of, add these red and blue papers into the scene. And we can actually debug, are the policies good with colors, right? Because these policies are generalist policies. In principle, they should follow any language instruction. So in this case, we asked the robot to pick red. And we found they're generally pretty good with colors, maybe because in their VLA training, fine-tuning data, SFT data, they have a lot of color labels, like pick up the yellow banana. But they're pretty bad with shapes, so 50-50, they would go either way. And that's also a data problem, because there's not enough data that says the shape, like pick up the round apple. There's no such language description. And what's more importantly is that these VLA policies seem to have forgotten the internet scale knowledge they have required in their previous vision language models, because in this last example where we asked the robot to pick Taylor Swift, again, 50-50 is going to go to the Snoop Dogg or Taylor Swift, right? So, but if you ask a vision language model which one is Taylor Swift, you're likely to get a correct answer. So this is saying, perhaps to complete this task, it's a post-training task problem, because we're never going to collect enough data to cover all of the celebrities and using robot hand to select the right celebrity posters. But nevertheless, from the rollout of the policy in the world model, we can clearly tell, a vision language model can also tell that the robot moved to the wrong direction. And then if we can tell, then there is reward, there is information for policy gradient to update the policy to complete this task. So, and specifically Julian, who's the lead for this work, will be talking about World Gym at the oral session tomorrow at 2:45 p.m. So you can learn a lot more about the details, right? The exact correlations between policy rollouts in the physical world and policy rollouts in the world model. So I want to perhaps spend a bit more time on talking about, we talked about doing post-training in the world model. So now what happens when we actually run reinforcement learning with rollouts from the world model? And we use policy gradient, we use GRPO, but many algorithms could work, and I think algorithm research is also with the world model is interesting. But the general idea is just for actions that received high reward, which in this case is represented using an advantage function, the likelihood of that action sequence will just be weighted up. And if they achieve low reward or low advantage, the likelihood will just be weighed down, right? So that's a very simple interpretation for the simplified version of the RL policy gradient objective. And there are a few benefits of doing RL in the world model. One is that for any data that we've collected, we can use that data as the starting point to train the policy to perform this task, right? So you can imagine we can, even recover from failures where the failure is just the start of initial frame of another trial, right? So because we can, all of the SFT data, all of the data we've collected, we can use it as the initial frame to do RL. Then we can really train from any frame from the data to show some failure recovery behaviors. And because the world model, we can edit the image, right? We can also change the language instruction. Like if there are multiple objects, we can create a task for picking up different objects as long as we have a good reward model for detecting whether picking up that object is successful, right? And when I also showed you this example of like the policies fail when there are distractor objects, but now this is called domain randomization, which was previously studied, but maybe not in such realistic settings with generative models trained on real-world data, right? But now we can really just add a lot of distractor objects that we can actually commonly see, like in kitchens of everyone's household, and train the policy to be robust to these distractor objects. So for this world gymnast, we named it gymnast because it can, now we're actually, training the policy, training the robot in world gym. And what we did is basically we took some of the SFT data and from this bridge robot data set, and then we just, world model can basically do rollouts from any initial frame, right? All we need is just an initial frame, and then we get the policy to predict actions, world model to predict videos, vision language model to predict reward, and we have closed kind of like this RL loop with a world model. So there is something in particular I want to mention about this work, which is we chose to use a third-party evaluation platform, because I think one of the bottleneck for robotic research is people will report their results on their own robot that no one can reproduce. So to overcome this issue, we use this AutoEval, which is a third-party platform developed at Berkeley, UC Berkeley, where they have some robot live feed, which is like what's showing here, and we only submit policies. We don't get to control, how we run the robot, and these policies are executed on these robots that are owned by someone else, and this really provides a fair evaluation because all we're doing is submitting a policy without RL and a policy with RL in the world model. And these are the 4 tasks that this platform supports. And we would really want to evaluate more, but they only support these 4 tasks. So these are some examples of the real-world executions of the RL policy. So you can see their task of opening the drawer, which is, the robot needs to get into the hole of the handle, and closing the drawer, which is easier. And then there's also the task of like put the eggplant into the sink, and then taking the eggplant out of the sink and put it into the basket. So these are the examples, real-world rollouts of the RL policy. So, but the concrete question we want to ask is, are world models today better than simulators, like in terms of sim-to-real transfer, right? So this is exactly what we're measuring. So the simulator we're using is called Simpler. It's a real-to-sim approach where they take a real image and then try to convert that into code so they can, simulate executions of policies by running these simulator code. And we found that comparing RL in the software simulator to RL in the world model, RL in the world model is actually better for 3 out of the 4 tasks. But there is one thing that's worth mentioning, which is, so for the world modeling bars you're seeing, which are the purple, they're actually measuring generalization performance because open drawer, closed drawer, put eggplant, these are not in the training tasks. But for simpler, when we did the out of distribution, right, they didn't work because there was not enough simulated tasks. We had to train using the exact kind of like digital twin of this task of opening drawer, of closing the drawer, of eggplant. So despite training on these tasks in simpler, we could only get the closed drawer to perform well because for that one, it's a bit like a locomotion task where you just need to swing the arm in the right direction. You don't have to really interact with the handle or anything. And for that task, actually, yeah, like the simulator was okay. But for a lot of the other tasks that require, grasping, pick and place, world model actually shows better zero-shot sim-to-real transfer behavior. And we also compared the RL model against some without RL, right? So without RL is the SFT model. And we also tried some kind of versions of iterative supervised fine-tuning where we just roll out the policy in the world model and then use VLM to rate the rollouts and then select the ones that are successful and add those successful actions back to the supervised learning data. This is what control world, which is another work that uses world model for policy improvement, does. So we perform this iterative supervised fine-tuning, and we see that the iterative supervised fine-tuning, which is basically like RL, but it's throwing away the negative data, right? So it's only learning the positives. It has some effect on these harder tasks, like putting eggplants into the sink, but the benefit of also learning from mistakes, learning from negative data with RL is a lot more drastic compared to these iterative supervised learning. And yeah, I just want to highlight we only submit policies, and these are the results that's evaluated out of our control, but the results are pretty promising for running RL fine-tuning in the world model. And I think that there is also, of course, history always kind of like repeats itself. Like there are a lot of work that has been studied, just not in internet data transformer settings. For example, the classical DINA algorithm, where we can iteratively improve the world model using real world data, and then continue training the policy in the world model, but then occasionally also execute the policy in the real world, get data, update the world model. So this algorithm was fairly classic. But now, we can, because we were running these real-world trials on the auto-eval robots, so we just took these data and continue fine-tuning the world model on this data and continue training the RL policy in the fine-tuned model. And so this is some examples of the rollout in the actual physical world of this opening the drawer task. So you can see the ground truth looks roughly like this. And we replay the same sequence of actions, right? So we get the sequence of actions, we play them in simpler, which is this middle one. And you see that there's actually a big sim-to-real gap, right, in terms of how the sequence of action was executed. And we play them in a DINA-style updated world model, which was trained on data collected from this environment. And we see that the DINA rollout of the same action looks fairly identical to what happened in the physical world. And then in terms of the task success rate, again, when we're able to do some online learning of improving the world model and improving the policy iteratively, we can get the success rate of world gymnast to be even higher than without this online updates of the world model. So one thing I want to point out is that we kind of arrived at this DINA-style algorithm applied to robotics first, but I do think that there is the world model being an intermediary between the agent and the physical world will be equally as useful for a lot of language model-based agentic tasks, because now a lot of the tasks people are training language models on are extremely expensive, like machine learning engineering, where the agent needs to build a model and train some neural network that takes days. It's just very expensive to do online interactions these days when we go beyond the math and coding. And for robots, we just have to do this this because otherwise we just cannot afford running robots in the physical world for RL. But in this position paper where I talked about world model as an intermediary between agents and the real world is like a buffer, and then the agent will interact with the world model and then the physical world at different frequencies, perhaps doing more improvement when the cost is a lot cheaper, but occasionally getting data from the real world to continue updating the world model and the agent itself. Okay, so let's recap, right? So we showed some pretty promising results in terms of running RL in the world model and how that works better than running RL in a simulator. And I've been working in this field for not as long as many of you, but also for a good number of years. And sim-to-real manipulation that requires a lot of vision just like never seemed to work. And I was very excited about this work because this is the first time that I see sim-to-real with a learned world model actually works. And I think this is saying a lot about, and the fact that it's evaluated by some third party that's out of our control also says a lot about the promise of this direction. And I think that there is also emerging paradigms of, sort of revisiting these classical algorithms such as Dyna, but then sort of applying them or repurposing them to practical settings of today where we have realistic world models and generalist policies. And there's also paradigms of like test time scaling, where we sample a lot in the world model, select the best one using some kind of reward model, or even do some test time training when there's a new frame that the policy hasn't seen before, but we can try to do some world model rollouts in this new frame and try to improve the policy. So all of these are things that people are already doing with language models, like test time scaling, test time training. But now, because we've opened up the area of post-training for robots with a world model, then these are all new paradigms we can also explore for physical agents. Okay, so hopefully I've convinced you that we've made some progress in terms of closing the post-training gap, but things are not perfect. Accuracies are not at 100%. And we used all of the evaluations we could use from auto-eval, but we really want to evaluate this on even larger scales. So there are many interesting next steps that I think needs to be resolved to further close this post-training gap for physical agents. Specifically on the pre-training side, people are doing a lot of pre-training for robot policies, but we should think about pre-training for world models as well, and scaling laws and the data and the architecture. And so for post-training to work, all of you probably understand that we need the policy to be able to achieve something that is non-zero in terms of reward, right? If the policy is completely bad and doesn't get any positive signal, there's no way that it can learn during the post-training RL stage. So right now we have good supervised fine-tuned policies that can do pick and place, but if we go more towards fine-grained dexterous manipulation, we don't really have extremely good SFT policy that could even achieve non-zero performance during RL. And then there's even more questions that got opened up on the world modeling side, which is sometimes we found the reward model is not very good, and then the reward model is essentially looking at a different distribution. It was VLMs are probably only trained on real-world data, but when they need to judge successes of rollouts, they're looking at generated videos. And then there are some subtle failures that reward models are not able to recognize. So how do we get accurate and dense reward information from reward model is also pretty interesting. And lastly, I think the world model actually serves more than just a reward model because it actually gives a lot of dense information. Like if the rollout was a failure, which part did it fail? Why did it fail? Did it fail to twist the lid, or did it fail at somewhere else? So this kind of rich information from the world model beyond just a single scalar reward also is worth more exploration. So with that, I would like to thank a lot of my collaborators, including my group at NYU, where Ange lead the world gymnast work, and Zijin, Yixiang, Alex spend a lot of time trying to scale up pre-training for world models. Yun, Zhedo, Yong, and Mattia working on algorithmic aspect of improving agents and world models. And their collaborators from Stanford, Julian, Percy we worked on evaluating policies, world gym, evaluating policies in the world model, and Ilu and Leslie on using video generation as policies to control robots, and Bo, Dale, and Peter, where we initially worked on Unisim of pre-training a large interactive simulator. So with that, thank you for your attention, and I'm ready to take any questions you have about pre-training world models and post-training physical agents.
So thank you very much. We have time for questions. Again, there is one microphone here and here, if you want to go. Yeah.
Hello. Hi. Thank you for your talk. It was like really, really cool. And I have a question about word models at large scale. Are you also interested in showing how do they generalize as you scale the word model? How do they generalize to new labs, like new rooms, new scenes? It could be like the same robot it had seen, it could be the same set of objects, but new environment.
Yeah, that's a great question. So I think that is really kind of like what we're trying to push here, which is like right now people just train their visual dynamics model on the same data as they're training their policies, right? Which is then how is the model going to generalize to the distribution that's outside of the policies, right? That's the great question. And the hope here is just that policies are maybe task specific, but the world model is trained on many diverse types of actions, and it's trained on deltas. For example, like the generalization will come from, for this particular robot and this particular object, this sequence of action is out of distribution for this particular data set. But if you have the actions being end effector poses, for example, in some other robots or in some other human data, then the deltas in terms of how the observation evolve is actually fairly transferable from that domain to this domain. If you think about, we break down the problem of mapping delta x, delta y's onto the visual outcomes of these delta x and delta y's. So this is where we're hoping that the generalization will come from. It's that the world model has seen the response to these action deltas in terms of the visual response from some other domains. That's why it could enable generalization that's beyond just this particular robot. And if you're asking about out of distribution initial frames, then the question is, anything I'm saying right now is probably within the distribution of internet text in some ways. And when we're at that scale, the exact in distribution, out of distribution isn't extremely easy to separate anymore. So the point I'm trying to make is like, if we scale up a lot, maybe the things that we consider out of distribution today could be in distribution when we have a huge model with a lot of data. Yeah.
Thanks so much. That was a great talk. I really like the idea of using world models as simulators that are learned from data and that bridge that sim to real gap. So one thing I'm wondering, if you really want like a perfect world model, to some extent, I mean, there's a school of thought that says that interactions with the world cannot be avoided to learn about like causal structure of the world, or like get like a data efficient way to explore like very heavy tails in the distribution. So I'm really excited about what the dyna part, like the last part of the talk. Have you seen any examples there where you find that the world model is as good as it gets from observational data, but then with that additional interaction, you learn some interesting new aspect that would have been lost without?
Yeah, so I think for right now, I think the world model we've trained are not at the level of generalizing arbitrarily to initial frames. So this is the reason that we did the dyna experiment, because we saw like in some cases, the world model rollouts actually looked different from the real world rollouts despite conditioned on the same sequence of actions. And those are the subtle failures I was talking about. Sometimes it's things that are not even captured in the visual space, like friction or how much force is applied. Things could slid, for example, whereas in the world model, it's not able to capture these subtle interactions. This is where the dyna part comes in. If you have more data, like we could learn a more accurate visual dynamics model, yeah.
My question is, in robot learning, we usually use teleoperation data or simulation data. Both are kind of enforced by some physics, right? Physics engine or real world physics. In word model learning, a policy is not enforced to follow the physics. The word model can hallucinate, and it can lead to a policy that's not really realistic. So how can we guarantee that the policy learned in the word model is safe to be deployed?
Yeah, so that's a good question. There are many dimensions to your question. So, so one dimension around safety is like we can do more evaluations in world model and have a higher confidence in terms of what this policy might do. And around hallucination, there are many angles to that question. One is we're trying to explore, can we solve hallucination by scaling? And the reason is because world models are train using maximum likelihood on the real world data, which are all real, at the extreme of infinite data, infinite model size, what the model will do is maximum likelihood. And of course, if you're talking about out of distribution actions, for example, you see a robot arm and you try to wash hands, give it some instructions, right? And we've tried that example actually. In that case, the model actually, because the model was trained on egocentric videos, it actually turned away from the current scene and then kind of like cooked up a scene where there's a kitchen sink and someone went there and washed their hands. So I think, train using maximum likelihood at the extreme, the hope is we're trying to research on what if we can just get rid of hallucination completely, right? And then there's also the question of, okay, let's say, the dream is always grand, but the reality is always brutal. We're not gonna have infinite data and infinite model size. The model is going to hallucinate. Then I think this is kind of like the control aspect, which is maybe the dynamics isn't exactly perfect, but we kind of just need some kind of preferences between the sequence of action versus the other sequence of action for the model to optimize the controls. And the hope is that, despite some hallucinations, because we're mostly looking at pick and place, because that's kind of like what the SFT policies could give us these days. And for those, roughly speaking, where we don't have to have very precise dexterous manipulation, the rough information of like, okay, which sequence is better than the other actions, despite maybe the physics isn't exact, is already kind of enough to give the policy gradient information to get the actions to be closer to where they should be. Yeah, so those are some initial reactions to your questions, yeah.
Hi, thank you for the talk. So kind of to follow up on the previous question, I was wondering if you kind of seen in practice some instances where the policy kind of learned to hack the world model to produce the results that seemed to satisfy the requirement.
Yeah, that's a great question. So one set of results that I didn't get time to talk about is we actually try to do more with dense reward from the world model, because our hope is that, when we have the full rollout, we can actually properly assign, if it's pick and place, we can assign reward at pick, we can assign reward at lift, we can assign reward at place, right? So, and when we did that, we actually did observe reward hacking, where the model would only just like stuck at the pick stage and it wouldn't move on to the next phase. So, so I think that's a great question. Like, yeah, whenever we have some kind of RL environment where the reward isn't perfectly aligned with what we truly want, there is the problem of reward hacking. And the question is, how do we design more robust reward models that reflects our, true intent of what we want these models to do?
Thanks for the great talk. So, my question is with respect to the whether or not you've ever observed the problem of counterfactuals in both pre-training and also using the pre-trained world model to train the post-trained RL policy for robotics. So, for example, in the case you mentioned about the plate wobbling on the table as well as the appearance of the red plate, both of which are what I would call counterfactuals that are not exactly the same as the ground truth, but in the metrics you use for the to showing the scaling of the pre-training, the three metrics, noise MSE, SSIM, and ellipsis, they're all with respect to a certain ground truth image. So at best, these metrics don't penalize. At worst, it will don't really encourage. At worst, it might even penalize the behaviors of those counterfactual behaviors. So, for example, in the earlier cases where you have the we have asked a person to go and wash the hands, who is it to say that once we turn to the right, even though it's most likely that the sink is there, but in the actual real world the sink is on the left, what would happen in that case? I guess my question, coming back to my question is, what would you think would be a good way to evaluate or even determine whether or not the pre-training is working for those counterfactual scenarios, especially in the robotics cases, and whether or not you have ever observed behaviors in the post-training stages of how that will actually affect the execution of the tasks?
Yeah, thanks for the great question. I think evaluation for world models is indeed pretty difficult. The reason that we chose some of the metrics such as pixel MSE was initially we believed that world modeling is a fairly at least like action condition next frame prediction is a fairly deterministic task. MSE is bad for generative models because they don't capture uncertainty, but we initially thought, okay, if we condition on the same action, it's very deterministic in terms of what the next frame should look like, until we saw this like red plate shows up, right? Although this kind of uncertainty in the dynamics is somewhat rare. It happens, but it's rare enough for us to still use some of the ground truth next frame versus generative next frame as a reasonable proxy for the initial evaluation stage. There are a lot of people coming up with a lot of metrics on how to better evaluate world models. That too much that I couldn't even follow all of these benchmarking world models work anymore. But I have a belief in like the best benchmark is the usage. So if we figure out the usage for world models, which is to evaluate and train policies, that from this end-to-end perspective, how good are the success rates of different policies? How high is the correlation between the success rates evaluated from the world model versus the ground truth performance of these policies in the real world? That's a pretty good reflection of how good is the world model, and it's pretty useful as well. It's grounded in the actual use case of using world model to evaluate policies. Saves massive amount of time and money from what robot companies are doing now with human evaluation. And furthermore, like best world models, most faithful, should result in best training of the policies when we zero shot them onto the real robot. So I think coming from the use case, it just offers some perspectives on evaluation metrics, which is to ground these metrics in how these models are actually going to be used, while developing some kind of like modularized MSE type of metric. I think is okay as like a first step to get a rough idea of does the model actually get better. That's kind of like my sense on evaluation, as opposed to developing, because like even like metrics for generative model is also like a pretty open question, right? So I think ultimately, you know, everyone uses ChatGPT because they work. So the best metric is whether it works. Yeah.
Right. Thank you.
So we have to move.
We have time for one more question.
Okay, let's do a quick one, and then we can move to the coffee break. Or did you? No, you were there first, right?
I think so.
Okay, you can go. Okay, you can go ahead, and then we can.
Hopefully, a quick question. I have a question about the action space. When you have, because when it's numeric, I assume it's numeric for the various angles represented as a string, passed into the model, and that's specific to the robot. I'm curious, when you have a robot that's not represented in the training data, do you have to do fine-tuning and then it's able to transfer, or is it doing something like context learning where it's doing abductive reasoning on what these numbers mean based on a few frames?
Yeah, that's a really great question. I think it's a very exciting research direction to think about in context learning for world models. As of now, because the model wasn't having long enough a context to have these in-context learning behaviors. So right now, I think the main paradigm is still fine-tuning. But we've seen a lot better sample efficiency in fine-tuning, despite the action space not being a part of the pre-training action space. Because in some sense, like I said, like different actions, they just reflect different changes in some control space. And the model has learned to react to this control space. And now with a bit of fine tuning, the model can understand the change of the control space, but the visuals are a lot easier to generalize when they're pre-trained on a lot of different kind of control spaces, yeah.
Thank you very much, very interesting work.
Thank you, so we will move to the coffee break now. So thank you, Sherry, again for the great talk. So if you have further questions, feel free to ask them offline, and we have 15 minutes break now. Then please come back for the talk of Shirley. Thanks.
Excuse me. Sorry, everyone. I just wanted to say we're going to be opening the wall here, so just be careful. Just leave this area free for the break, please. We're going to be opening this. Thank you. Yeah.
All right, everyone. If we can slowly get back to our seat for the next speaker, that would be nice. We have Shirley that will give the last talk of the morning, and then we will have the lunch break for more discussions. All right, everyone. So let's get back into our seats for the last talk of the morning. Okay, we have to fight the coffee break. Yes, but we need crystal. We need crystal glass. Oh, okay. All right, so thank you for joining us back. After the break, we have this talk, and then we have the lunch break. So very happy to welcome Professor Shirley Ho from NYU and Polymatic, doing some very exciting work on world modeling for science specifically. So please help me in welcoming Shirley today.
Let's try. Is this better or one?
Whichever you like.
Okay, this one works actually. Hello, everybody. How are you doing? This is much warmer than New York, and I never thought I would say that. I came in, and it was like 10 degrees warmer in Montreal in the middle of February. So now I'm changing my world model in my head as we update it, as I walk into the snow. I'm going to talk about polymathic today. It's going to be very different from all the robots you saw earlier. We don't have any robots in my world yet. But I will be describing mostly the physical, scientific world to you, and hopefully how we model it. And we're very excited to share with you what we have done in actually it started 2023, nearly 3 years now, at the end of 2023. So I can tell you the origin story, but let's skip all the origin story. But can I ask the organizer, is it okay to ask questions in the middle of things if you just raise the hands? Yes, please raise your hands. I'll call on you to answer questions. Because I slept only 4 hours last night, so if it doesn't make any sense, it's my fault, it's not yours. So just raise your hands and ask questions. I will adjust the pace and the content of the talk as we don't have enough time at the end usually. So that's all okay. All right, let's get started. It's Polymathic AI. We're gonna build this thing called Polymathic Foundation Model for Science and Beyond. I'm gonna go from the stars to the stardust humans at the end. So that's the promise if you let me finish my talk. So let's get started. I'm also at Simons Foundation, just so people know. NYU Polymathic and Simons Foundation. Thank you so much for the organizer for inviting me also. Polymathic, what is it doing? We're trying to advance science through multidisciplinary AI, and you're like, this is very confusing. We were deliberately confusing at the beginning because when we had the idea of building these polymathic models for scientific fields, we didn't know it's gonna work or not. So in case we can't find something that works, we decided to make it a little bit general, so we don't make people find us very unhappy. We have funding agencies from both Schmidt Sciences and Simons Foundation, and there's a lot of collaborators across different universities. We're just talking about, we have loads of more collaborations. We're very welcome collaborations, so just come and let me know if you want to collaborate. We also hire a lot of interns, postdocs, all kinds. So talk to me. Here's the current Polymethod AI team. You see a lot of different faces, people from different institutions, and a lot of us actually started as a core from the New York area. Also, there are Polymethod interns, collaborators, and friends across, and many of them. And we also have a scientific advisory group, which Jan, who will speak soon, is also part of it, and also ranging from people who do like very hardcore fluid dynamics to oceanography, to climate research, to, you know, David Haas, a friend of mine who's CEO of Sakana AI, who like from industry. So very, very huge ranges. So how do we build a generalist AI model for science, right? The polymathic. Okay, do people know what polymath means? Yes? Okay, there are only 2 hands who know, so maybe 3 hands that listen, maybe. 4, 5, okay. So polymath, usually people are like, oh, is it multiple math discipline? But it's actually not, it's about multiple disciplines. Like back in the days, people were able to, well, more people were able to learn many, many different things. Like we can name some of them. But these days, I think it's very hard to find someone who knows very deeply in many different fields, just because everything got so much harder. So we decided that we want to build a generalist AI model for science in particular. But how do we build it? What are the backbones? What are the problems? What are the challenges? That's what I'm going to try to show you today. First questions we try to ask ourselves is that should we treat scientific data simply as language, images, or videos, or maybe all 3 of them, or is that more? Does this data need custom handling? What are the common bases that span different disciplines and data? All right. So for those who are wondering, on the left-hand side, can you get what that data is? It's more like language, like, right? Any time series can look like text, basically. No? You can just raise your hands. I can. I won't promise buying beer. I don't know what the drinking age is. It's in Canada. No? No one? Okay. It's not surprising. It's just a time series. It's actually some sales like sequences over time. And then on the right-hand side, there's some structured data that's actually running right now. I think with the light in the back, I know it's very hard for you to see, but do you want to have a guess what the structured data is? This structured data has temperature, pressure, density, like not text-like at all. Like it's a cube of states, and those states have different variables, including pressure, temperature, velocity, density. Yes, go ahead. You have to yell a little louder. I heard black hole and jet.
Use microphone for stream, please. Thank you.
Is it jets from the center of black holes?
Very, very close. There is very, very close answer to it. Yes, there's someone here too, over here. Like a neutron star or something? Exactly, it's neutron star merging. So very good. I'm impressed. There must be some astro enthusiasts or astrophysicists here to recognize this right away. But it's a very different data. Right? Like time series data that could be tuned into text, turned into kind of text-like, to something like that that's like neutron star merging. Very different data set. How do you put them all in the same sort of basis? That's the first question. What are the challenges? We treat data in like very different way, right? So these are the early challenges we looked at, and some of them we have addressed, and I will show you guys. One of the challenges is that can we deal with data limited situation? Because in most scientific discipline, if you're at the frontier, you're always limited in data, nearly always. That's why there's experimental, scientists who are trying to collect more data because there's always limited data. If your model has to work, it has to generalize to situations where you don't have enough data. If you have a lot of data, it will nearly always work. So multimodality, all the different types of data we just showed you earlier, text, time series, all the way to like neutron star merging, that looks nothing like the ones before. And scientific reasoning, can you trust the answer if it gives you an answer? Does it hallucinate? Does it have an error bar? Can you quantify the uncertainties? Like all that, is that robust? So those are the things. We have some papers on all 3 of them. Actually, there's more papers. This is the early slides that we made. We will talk about how we generalize the data limited domains particularly in something called fluid dynamics. I will talk about what that is. There are multiple papers since, actually. This is just the earliest papers that we had. We'll talk about multimodality, how we actually have many, many different modes, like 39 different modes together, data to work together. And scientific reasoning, we won't have time to talk about it, but look up our papers. We have a blog post and everything, so let's start. We have multiple physics pre-training for physical surrogate model. You're like, this is really long. and it's very early. I know people in the back was having trouble, even with me. And this is a project led by Mike McCabe, Bruno Rigardo, Liam Parker, and Miles Kramer. It has the best paper award and all that stuff. It's great, but what does it really do? Machine learning is really useful for some physical simulations that are very hardcore. By the way, this simulation, do you guys know what it is? I'm testing all the astrophysics crowd here. Or what kind of physics it might have been involved. All right, there's some guesses over here. Always good to try.
Is it nucleosynthesis from a star?
Nucleosynthesis involved, but not just that. Good answer. All right, if it's too hard, this is really, really hard. It is a red supergiant that has like all this stuff that's going on with like hydrogen turning to helium, turning into all the elements, but at the same time, there's radiative transfer, which means photons is pumping out at different energy, interacting with the medium that's, with hydrogen and helium. It costs about $10 million to run one of them. There are only 5 in the world in like frontier computing that can make it happen. So if there are only 5 simulations, 5 trajectories, can you accelerate it with ML? So that's the questions I'm going to pose to you guys. This is very, very low data limited regime. It's not 10, it's not 100, it's 5. You can probably only train on 2 and test on 3 or whatever, right? Okay, another situation, poorly specified or imperfectly observed dynamics. So people can see really well. Can you guess what this is? Yes, the sun. Okay, the ones in the front can hear it. The ones in the back, I cannot see anything. I'm sorry, I apologize for the very sunny Montreal that you guys have. I'm very jealous. This is also true in fusion and nuclear. Things are more, I guess, practical these days. You kind of need the energy. The one on the left, it takes 60 billion grid points to look at small modular reactor core to model it. And full modular reactor core is 600 billion grid points, and it's 1 trillion grid points to model this like ITER test blanket around the nuclear reactor. So this is very hard stuff and extremely hard to simulate. Very, very few simulations available. If you have 100 of them, it's going to cost, I don't know, 10 million times 100 is a large number these days still for most people. Another situation when you have these processors, GPUs, it's not they don't have simulations, they don't share them. So the most updated simulations or actually data observed by these GPUs that can be released to the public was from like 2018 because they don't want to share what they have, right? So there's also limitation not because they cannot generate or show or observe, they don't want to share it outside, the company. So there's another situation. So, but all these settings are where data is inherently limited and can learning from other related disciplines help? So that's the first question I will pose to you guys. We did something extremely simple. That was our first paper. I always like to refer back to this just simply because it's so simple what we did. We want to test if I train on a bunch of things that are related, can it do something else that are just somewhat related, right? So I don't need a huge number of, say, fusion simulations or huge number of nuclear reactor simulations. I can do something related and it still help. So we did the simplest thing. We have these fluid dynamic situations where we have incompressible Navier-Stokes, diffusion reaction, compressible Navier-Stokes, and shallow water. And you're like, what are these things? I'm going to walk around because it's very hard to stand still. So compressible Navier-Stokes, think of it as air. Think of incompressible Navier as liquid, like things that cannot be compressed, right? Things that can be compressed is like the air in this room. And then shallow water, you can think of it as like pebble in the pond. If I play them, yes. And diffusion reaction is another type of simulation. So the question is, say, can I train on some of these and predict something else that could look completely different? Okay? So we did the first very simple model. This is based on an axial efficient transformer. But the hard thing that I can mention here is like how do you actually take these fields that are pressure, temperature, density, and like shuffle it into the transformer, and then out comes something that we still understand, right? I have to come back to it. And that's not entirely trivial. So that's the piece that I recommend you guys, actually all the paper and code, everything's public. So we looked at this and quickly realized if you test, looking at the error bar, the test root mean squared, lower is better. This is shallow water equation, diffusion reaction. This is compressible Navier-Stokes with Mach number equals to 1, Mach number equals to 0.1 across all the different types of physics. Our model is called MPP, multiple physics pre-training. You see that it was better, basically, than most of the time than all the other ones, just simply because it's seen all the other physics. Right? I'm not saying we're special and be smarter. Some of these other models, like OCA, for example, is a transformer-based model. And it is just simply, it has seen other physics, not only the physics that you have to train for. And you're like, well, but this is what we know, right? But 2023, people weren't doing it. 2023, people were doing it thinking about text. We were doing it for fluid dynamics and sciences already. So we trained it on incompressible fluids on the left. So we want to see whether pre-training accelerated learning of new physics. And we try to do something that's near and far, which is subsonic gas or nearly supersonic gas. So training on liquid, can it predict supersonic gas? Think of it this way. Okay. So here are the performance. This is when you pre-train on a bunch of liquid and ask it to predict the steps in future rollouts of supersonic gas. Does that make sense? I know there's not too many physics people here, so I want to not say all the buzzwords in physics. Ground truth is the bottom, prediction is on top. We have velocity in x, y, density, and pressure. Okay, and it's Mach number 1. It's going to be very interesting because the ground truth will stop showing very soon because it's expensive to run the ground truth, but the top prediction will keep running because it takes no time to generate. All right, you're going to say, okay, this is too fast. I'm going to go that again. I hope you believe me, they actually look pretty similar. This is because there's no more ground truth. This is data set someone else produced, so we can only show that much ground truth. But the performance looked pretty good. And you're like, okay, next piece. Now we ask ourselves, what if we do something completely crazy? And you're like, why? Let me remember myself. This is from 2023. I'm getting old. Like 3 years ago is a long time. Number of samples that we only fine-tuning with, right? Test error, so we want to go down. The green line is just training from scratch. So like no pre-training. So you're like, okay, not surprising. That's not doing super well. But the orange and the red line, are we just taking cats and dogs videos, trained video model, and just fine-tune it on a few hundred of very complicated supersonic gas simulations. And it turns out the cats and dogs videos actually also help. It's much better than not pre-training at all. By the way, it is 2023 when we looked at this, so we were kind of shocked that maybe physics is in everywhere in all the YouTube videos of cats and dogs videos, or is this something else? Or is it we just make a huge mistake? We checked many times, no mistakes were made. This is even like 2 different types of cats and dogs video trained fission transformers. So I think now people have some argument of why this might work, like maybe they have learned certain kernels or something like this, but I don't think we have like a proof yet still why this works. And luckily, when you pre-train on a bunch of physics simulations, it actually really helps. It drops down even further. Okay, any questions? No questions. No one asked me, this is usually, yes, questions in the back.
Could this just be some smoothness in like rolled videos of the world that's also in the physics simulations?
I don't know. I don't think our videos are that smooth, right? Like if you look back, like this one, if you come closer, because I know it's very hard to see in the back, it's actually very shocky. There's a lot of caustic. So it's not smooth. But it is interesting. So what did they learn from the videos of cats and dogs that actually help us in predicting supersonic gas states in the next step? I mean, these are states in not just what it looks like. It's temperature, pressure, density, velocity. These are actual numbers, right? So it's not just it looks similar, but it has to have the right numbers.
I mean, there's local spatial dependencies in all of these domains. So this is something that transfers.
I think it's some of these, or maybe causality, like locality. I was about to say it's like cats won't be like appearing over here all of a sudden, even when they jump really far. So there's a locality thing. And then there's also causality. You expect some kind of causality in the videos. So that's something we hope to maybe test it out. We haven't had time. Just machine learning has moved so fast, we haven't done that yet. Okay, so you're like, okay, this is cool. What next? We also want to show how well our models are doing compared to like general models, right? So we went and asked ChatGPT, like, give you 5 states of fluid. I'll even describe you what the equations are of those fluids, we ask each of the models to predict the next 30 steps. For those in the back, you really can't see because it's so bright. You have sunshine, I should not complain. But the point is, it's rolling. The beginning, it actually looks very similar to truth, which is on the left-hand side. Polymetrics models all the way on the right. The OpenAI model actually craps up very quickly. What it does is that it gives you the equations that you will actually run with whatever tools that they're actually running. And the NVIDIA specialized model is just for fluids, right? There's a lot of instability usually. And we are able to do it because right now, everything that's out of distribution becomes somewhat in distribution when you have a large variety of physics in the back. Other questions? I apologize for the color scheme for the back. I know because I can't barely see it from here. Yes, go ahead.
Thank you. Maybe this is captured better in the paper, of course, but I missed if you said if there's any biases included in the architecture itself to capture the physics itself, or is the physics just being learned end-to-end from the data itself?
Second one. It's being learned from the data directly.
And I guess maybe later...
We don't put any equations in it because we sometimes don't know the equations.
That's fair, but I wonder, and maybe you'll get to this later in the presentation, but is there any reason why not to include, some of these that are well understood in the, let's say, physics community?
So I know, because I'm trained from physics world, right? I did a physics and CS undergrad together. We started, so Miles Craven was my student, and we did a lot of very physics-informed type, strong inductive biases in the model type work. We went from there and swing all the way to both of us doing mostly learning from data directly. It might be there's another swing back, but right now for low data regime where you can have a lot of neighboring data that you can learn the inductive biases, it's more efficient sometimes, simply because we don't know the equations most of the time, or we don't even know approximately what the equations are. And even if you do, and sometimes you need to know how much error you're allowing the network to learn and learn from mistakes. That's the part that's a little hard to tune. And so we can go into the huge details, but it's been a long journey going between the two.
Thank you.
More physics, less physics. But now the physics just learn from the data. So looking for what should we improve, right? We have shown you a very simple one. The PD bench is very, very simple starting point. It's a good starting point, but it's relatively shallow in terms of diversity and complexity. So we built the well. For those who probably saw this, it's 55 billion tokens. It's small for the internet scale text data, but it's very large for the fluid dynamics data. The ones compared to the one before that we will use from PD bench, we're 1,000 times bigger. It has 3 million frames. The first ImageNet scale data set for fluid-like behavior, 18 physical settings, all the way from astronomy to biology, exploding supernova to blood flow and capillary to oceanography to artificial, all kinds of stuff you can think of. And there's chemistry in it too. Everything is publicly available. That should work. The QR code, if it doesn't, it's online everywhere. Yep. So we built the first, we call it multidisciplinary, sort of polymetric fluid AI model because it goes from astrobiology, chemistry, all the way to oceanography and other things. So what we did, we developed significant new improvement on the architecture themselves. Some of them are actually papers themselves. The patch jittering, very often when you roll out, I can go into significant details because it's a longer talk. When you roll out, you will see these really weird artifacts because you are tokenizing with boundaries. And so very simple idea is how do you just jitter the patches around? And that actually solves that. It's a significant improvement, and that's why our rollout was way more stable than all the other ones. The other one is adaptive compute patching. There is data that has so much more information, that's much more complex looking. The ones that are much simpler, much smoother. So we want to give the appropriate amount of compute to each. Nothing fancy, but I think all good ideas sometimes seem very simple when you talk about it in retrospect. So there's that as well. And then we do some extra things to think about how do you do temporal attention and spatial attention nicer. A lot of it's engineering to make sure that it is very efficient. Even just reading in data and making sure all the data get read in and no GPUs waiting for the other GPU to finish reading that batch. Simple things like that. So I can go on and on about this for a while, but the point is it's doing really well. The model is 5 to 10 plus times better than state of the art on 18 out of 19 settings. So we can go through all of them one by one, But the point is the highlighted color ones is the ones that's doing better for one step, the medium range, and the long range prediction. Not just because very often we can show it's doing really well for 15 steps and it craps out very quickly. And very rarely you see people rolling out 100 steps to show you. We can roll 100 steps now. Here, it actually rolls out to 83 steps. So true on the top, the predicted in the bottom. Previous model can roll about 20 steps without significantly diverging from ground truth. Both the patches problem and also, I think, just the fact that we have so much data of very different types of physics. Everything that's like out of distribution becomes more in distribution. I really feel bad for the ones in the back because I know I have trouble watching the videos earlier, but can't change my slides in real time. There's no GPT for us for that yet. Shear flow, we can actually roll to 182 steps. Like the fact that I'm not afraid to show you 182 step rollout says something. The truth on top, our model second row, Depot is like the most recent model already, and Poseidon to very large models. This is based a little bit on like four neural operator. This is Poseidon, which is a huge transformer model. And this is our old model, that the multi-physics pre-trained model that I talked about. So I'm gonna roll out for the trace itself, the pressure, the velocity, X and Y direction. You can see that the Depot model literally just goes haywire. But you can see our model actually works really well for a long time. This is rolling out to 182 steps. So, okay, we can now also do something what I promised earlier, fine-tuning on very challenging system where we usually have very few training examples and predict the next step with accuracies more than 80%. So we have the Rayleigh Taylor instability on top. I think you can't see it very well. This one is not so expensive, 128 CPU hours, but now we can predict it in seconds. Each rollout step is definitely less than a second in all rollout steps. Predicted and ground truth. Post-neutron star merger, so the neutron star merger that you guys saw earlier. Red supergiants, convective envelope, like a lot of astrophysics, but they're all super expensive, very hard to get simulations, and usually only have a few. And also this more like down to earth, because I think we have a very down to earth talk earlier with robots. This is imagining if you put an airplane foil, but it's something that none of the model has seen it. Like the model has not seen something that has an object in a fluid. Now I put an object in the fluid and see how it reacts. So this is completely out of distribution because I've never seen an object in a fluid moving around. The reference is on the right-hand side. I know, I'm going very far away. Right-hand side, pressure, velocity, XY, our model here, NVIDIA model here, and Poseidon model, which is the last state-of-the-art model. I'll just play it again. But you have to squint in the back, I apologize. Hopefully the streaming is a little better. Oh, okay, thank you. Okay, so multimodality. All right, I'm gonna pause for questions because I'm gonna switch to a completely different topic. Yes, there's a question all the way in the back, right behind you.
You mentioned that for non-periodic boundary conditions, you had a sort of like, I don't remember, a patch. What was it? The name of the thing that you did to get it handled?
So patch jittering.
Patch jitter, yes, sorry. I was just curious how that works for maybe non-grid aligned boundary conditions. I'm not sure if your example right here, if that's like a round airflow or something, but I was very curious about that and how that compares to like non-ML models.
So like, we have not dealt with really weird boundary conditions on really weird meshes. So these are much more real world applications. So that's the next thing, which is literally what we're doing right now. Mostly, first of all, we create data sets with the community first. So we'll have a well 2 with like all the different types of meshes, weird boundary conditions, and that will address those problems. But I agree with you, not all of these will work once you have these weird meshes and weird boundary conditions. And also, you know, how do you make it run really fast in inference time? There's also other considerations as well. Good question. Other questions here?
Hi. Since the model can predict so well, presumably there's like implicitly some prior about like the underlying dynamics going on. Is it possible to then look at the representations and try and extract, like reduce the equations?
Absolutely, absolutely. So there is a paper. It's one of the workshop paper that we actually did something like the Golden Gate Bridge for Anthropic, but we did this with different method, but for our fluid dynamics model, exactly this one, and learned about what are they learning, you know, and we can use it to steer. So now we're able to steer these models for, say, more affection more diffusion, like more of these particular terms, and we know which one are the, sort of the neurons to steer. So that's a workshop paper. We're writing like a follow-up Nature paper on it. Okay, all right, I'll keep going. Not everyone's asleep yet, so I'm very, very happy. At least there are 2 people listening. All right, I don't usually lecture that often, so I'm very excited when like people are listening to me. I have 2 kids, they don't, so there's lots of love. We have multimodality. You're like, okay, we know how to do multimodality, right? But back in the days, we didn't know. In astronomy, we don't know. But we have loads of data. But same thing in hospital. Kyung chose on our team, so I have to mention something about hospital as well. You have all types of data. Like for one human, you get observed all the different ways. The doctor's notes, the EEGs, all the imaging, all the prescription, all the measurements you can think of, all the history. And sometimes, this is actually Kyung's note, they actually describe the person very clearly. And you can use it in all different types of data to make a better decision or prediction for that particular human, right? Something similar happens in astrophysics too. For each of these galaxies, we probably had like 20 different sensors looking at it before. Actually, in our case, we know there are 39 of them looking at different ways for each of these objects. Just like each human, you have like all the different ways of sensing you by default. So how do we put them all together and learn from it and learn for the mathematically inclined crowd, the joint probability distributions across all the modalities. So that's what we end up doing. Not surprising, when we built the largest and maybe I think it's the most powerful foundation model for astronomy, we haven't tested all the use cases, but all the use cases we tested, we're doing the best. It is called the Astronomical Omnimodal Network. We call it AON, it's easier to pronounce. Francois led the whole project with like really huge support across more junior people. And we have created, again, a huge data set with the entire community. There's over 30 scientists who work across different telescopes from the ground, from the space, different sensors, all across. And what we do is that for each modality, we build dedicated tokenizers to convert data for discrete tokens and to make sure that tokenizing, that compression really compress and really conserve as much really useful data that we need for downstream tasks that we are testing for. So not perfect, but it is as much as we think is useful for whatever downstream task it is. Luckily, in our team, there are astrophysicists, right? So we know what the downstream tasks we should be optimizing for. And when we're doing the tokenizer design, it's deliberately for those downstream tasks. And it surprisingly generalizes to other things that are doing very well. Okay, so what it does is that it has this any-to-any modeling, and we are flexible to any combination of input data and can be prompted to generate any outputs. And this model is trained by cross-modal generative mass modeling. This is quite standard now that, when I look back, and we learned the joint and all conditional distributions across all the modalities. So what does that really mean? It sounds crazy. First of all, out-of-the-box capabilities. If you got a ground-based telescope, you want a high resolution from space for the same object, you can do that. And now you can translate from the low resolution telescope to the high resolution without any bad artifacts, because all the systematics, like all the random cosmic rays coming in, all the random airplanes, strides, or like Starlink, all that is not what the model learned, because when you look at the same object from 39 different ways, you will kill all the other bad systematics and like artifacts. Same thing here. For the non-astrophysicists, you're like, what is this? I feel like there's enough astronomy enthusiasts out there. You would know that when you take a prism and look at some object in the sky, you spread the light out. This is the wavelength. And if I only have the red line, we can give you now the blue lines. And the black line is the ground truth. And astronomer cares about where the lines are, whether that lines exist. So it's important that you can see that the blue line is not always correct and gives you a range. So it gives you the error bar around it too. And at the same time, what they really care about is that there's a line right there, where the lines are. And you're like, why are these lines important? These lines tell you where there's water, where there's like metal, this type of metal on that star. Or on that planet. If you care about, planet looking for the next extrasolar planet that has water, you're looking for these water lines or oxygen line. This is what those lines are for. All right, I'm confusing enough people. Beyond beating all the benchmarks when fine-tuned, we also find it very previously undiscovered object. such as strong gravitational lensing. Basically, when a huge mass moves in front of something, they actually bend it in space-time, and you can see the strong arc in the back. Shell galaxies that get punched through by another galaxy, like crazy situations like that. And we found all of them. It doesn't look obvious from what you see in the back, because I don't think you can see it very well from the back, to be honest, because it's a very, very faint arc right here. You can see this arc gravitational lenses here, right this. It's never found before, but the data was already there. It's the first time it's found, and there's many, many, many more of them. All right, so you're like, okay, now the crazy idea, because I promised we'll do a bit crazy. We have the largest astronomy model that contains nearly all publicly available data that includes not only images, also time series of all the stars in the sky. What if we fine-tune the time series data in real life that has nothing to do with stars? In this case, the humans. So this is coming from Gilmo, who's a Princeton faculty with friends. He was listening to my talk, and he's like, okay, I have this Apple Watch data of like 200,000 people over many, many years. The time series data. Do you think if I fine-tune my Apple Watch data over your stellar, stars changing in brightness data, stellar variability, would it help? Just like, remember back in the times when we talk about these fluids, fine-tuning cats and dogs data, that one helped. So he's like flipping it the other way around. Would it help? Because we have so much stars, and there are not that many people wearing Apple Watch yet. Like maybe Apple Watch will have more people wearing it later, but not now. Tracked over many years. So let's try this. So we decided to fine-tune Apple Watch PPG data. This is they send a light into your skin, and it can help you predict your biological age. By the way, I found out if you have, the biological is not your real age. So it's something like, how your body is. So they can predict your biological age, your BMI, there's like chances of stroke or like something in the future. So they can do that. And here's what they usually do, which I'm not going to describe. This is led by Jeff Shen, who's my student at Princeton, working with Gilmo at Apple and Princeton as well. So we looked at this prediction of age. So downstream data set size. So when we don't use so much data, so when you have very little downstream data, which is the PPG data, and when you increase it, right? And this is looking at standard deviation of the residual, so the lower, the better, and this prediction of age. And there are 3 types of them here. I know I can't, this is technical crowd, so I can go into a little bit more. So UKBB is just that, PPG data set from Apple. Sequential means I will take first the model with all the time series data of the stars first, and then fine-tune on the Apple Watch data. Mixed is that now, instead of doing first the stars, then the humans, I'm mixing the data. Okay? And then you realized, crazily, when you have less data, it really helps to have the stellar variability, the stars data, for either mixed or sequential. And it changes, it keeps it the whole way, which is kind of shocking. All right, any other one? No questions yet? Questions, go ahead. I'm going to ask Jan and Yasha Benjo. Those people might know, I don't. Anyone have suggestions to why it works? I mean, we may have Stardust, I guess, but that's a little far. Go ahead.
A question related to your previous slides. You were showing that you're building this mix, like foundation model. Like for instance, if you give images of galaxies with different like wavelengths, and then the spectroscopy, and then yeah, I was just wondering, like, do you use it, like, for instance, for prediction of the redshift of the galaxies?
Yes,
like
we
based
do
on
predict
like
redshift,
the images of and the colors. And,
yes,
yeah.
yes. Okay. So we do redshift predictions. We do all the normal astrophysics stuff for that astrophysics model. So prediction of galaxy properties, prediction the age of the galaxy, how far it is away, metallicity is like what metals on that star, all that. We do all that. And it is turned out to be basically the best model if you fine-tune a little bit and it beats or matches state of the art if you don't fine-tune, just 0 shots. Yes.
Maybe I have a question that doesn't have any sense here, but because you're talking about multi-physics, obviously, so is it possible that the reason why, I mean, this works very, very broadly, is that in fact underlying is a physical space? So the time series is describing a deterioration of a human body that is subject to physical laws and, you know, irreversible processes. But if you were training this on time series data which doesn't maybe obey to, like, let's say, completely non-physical,
like randomly generated one.
Well, randomly generated with underlying rules and causal effects, probably, but that doesn't follow, as I said, irreversibility of, you know, or second law of thermodynamics, for example. Do you, I mean, have you tested this, and do you think that?
No, we haven't.
I mean, it would be super. It's impressive that that this is working.
That's something we want to do, is to generate like random time series that has nothing to do with real life. Hopefully, like somehow make sure there's nothing, right? And then see whether that will also help, because some of the argument was maybe just learning the format, right? The network just very good at learning any time series, like as long as there's some kind of time series. Does it have to be somewhat physical? Right? Do we actually need real physical data, or can we just pre-train on anything that's generated that's similar structure? Right? So that's a key point. We haven't tested, but I'm very excited to try. We just need more people. I know we have a lot of people, but we don't have enough time. There's a question here. Yes, I saw people pointing hands. Go ahead. I will show one more, but it's the same. The BMI prediction has a similar structure.
I guess like earlier, I would ask smoothness, local spatial temporal correlations that might explain that. But one important.
But this is the, we're also testing the images too. So we are using the same model with all the images of stars and time series, and see whether it's doing better in medical images prediction, which is actually also working well.
Okay. And I guess an important control would be the amount of compute. If the blue has double as much data as the green category, you want to make sure you give the green twice as many training steps so that the overall compute is matched?
Yeah, yeah.
So there has been some research recently where they've trained purely on synthetic time series, the inverse of this. So no real data in the training of it. And then they find that you can use it.
Is this synthetic with any rules behind, or like deliberately Gaussian?
Both.
Both. Okay,
Yeah.
I'll be interested to see, like, to do the same thing here.
And I think the hypothesis is that the actual structure, the complexity of time series is very limited. And so if you have a strong prior that you learn from any large enough set of time series data, it's informative to many different types of tasks. And so it could be nothing about the physical systems, or just that you've learned a very good prior of what time series data tends to look like.
Yeah. If this is true, this has a lot of repercussion across the entire ML world when you think about it, right? What is the robotic stuff, or, you know, the health stuff, or the stars? It's all across. Like, do we need physical data anymore if all you need is some random simulations and it will already help you? But I think at some point with enough data, you still be better to have some data. With zero data, it might be hard. I've not seen, you know, what happens if I have trained with zero data. But with 10, it's very, very small.
Yeah.
So, other questions? All right. I've successfully confused everyone, which is good. BMI, same trend. Again, you know, 10 to 50,000, they're very different data set size when you think about it. And of course, with smaller data set size on the Apple Watch data, the more the effect is coming from the star, more help is coming from the stars. Okay, so looking forward for polymathic AI. If we have more time, I can talk more, but I'm also happy to take more questions. Looking forward to more polymathic AI. We have hints that learning from data from nearby scientific disciplines significantly improves our predictions, given the same amount of fine-tuning data. All our models are publicly available right now. And we've built the largest foundation model in astrophysics, and it's currently open. The fluid dynamics model is not the largest, but it has the best performance. So it doesn't have to be the largest to be the most powerful. We now understand the magic brain communities together in order to create large ML-ready scientific data sets. We've done it for both fluids and astrophysics community and released both, so please use them. Benchmark, codes are all on it. So it has everything. I think it's the only way to move forward the field, to have data set, benchmarks, and like, people can work together. And more training, larger model, more disciplines and community building, that's what we are looking for next. We're hiring interns, postdocs, research engineers, and scientists. Please, if you have students, postdoc friends who might be interested, working in New York. I know US is a little tough these days, but New York is okay. New York is good, I promise. Check out GitHub, everything. Follow us on blog, X, Blue Sky, whatever. Thank you so much. I'll stop here and take questions.
So we have time for a few questions. So I have one on input space prediction versus latent space prediction, but I will reserve it for the panel discussion this afternoon.
I did take all the questions already, to be honest.
If there is no further questions, then we can move to the lunch.
A general question. I think that applies to the first method you showed us. So have you ever tried a mixture of experts type architecture, maybe like specializing to different types of physical processes that might maybe work even better?
Are you saying that we should train two different models for two different physical processes, or?
No, a mixture of experts.
A mix of experts. Oh, yeah. So we looked into this, actually. Right now, we're looking at how do we maximize, we have people trained many different models. Can we just a mixture of experts if we're trying like training from scratch everything together and just put them all together with mixture experts? We are looking into this. We're also looking into, the model merging style of work. So that's another option too as well. And we also work with Jan and Randall about like JEPA and other architectures. So we're architecture agnostic, I would say.
Thank you.
As long as it works, we try to solve problems in science and engineering and technology. Yeah. This one in the back, do you have to come up, or I don't know?
Yeah, I think we can go in the queue.
Okay, there's a queue.
Yeah, thank you so much for the talk.
Thank you.
Yeah, so what have you learned so far about the best way to tokenize all these different modalities to co-train on all of them? For example, what are you doing right now to co-train on the RGB next frame prediction and the fluid sims? And then also, what do you think is the best method in the future for tokenizing all of these things?
That's very hard. I think that how you compress, or you call it tokenizing, would depend strongly on what you want to do. Like, there are a bunch of downstream tasks for each discipline that would much prefer certain things versus the other. For astronomy, for example, even though there's 39 different modalities that we put together, 39 different sensors, there are some general broad classes that we put them into specific tokenizers. Like there's a time series one, there's like an images one. The time series looks like very similar to the spectroscopy one. So there's some general types of tokenizers we come up with, but that's just very discipline specific, right? I think you have to talk with the domain scientists and know what they care about before we can design the upstream stuff. Yeah, that's what we learn. Like listen to the people who actually have the problems. Yeah, thank you.
Hey.
Oh, sorry.
Yeah, wonderful. And I studied astrophysics, so I get to sort of enjoy all of your simulations. But what I'm really working on is multimodal spatial temporal sort of synthesis of the natural sciences. And I think, so my question is really, do you anticipate that we're going to sort of, they never taught this in our science classes, that we would get a grand synthesis of the sciences. Do you think that's where we're going? And, from my view, it seems like spatiotemporal embedding is sort of the key, bringing all of your modalities into a space-time representation. Have you started exploring that? And just more generally speaking, what are you sort of seeing that's most promising going in that direction?
This is such a hard problem. Should we be a panel discussion problem? Yeah, this could be a great panel discussion problem.
Use your panel card.
Yeah, no. I think it's a very hard problem what you just asked. It's like, what is the best way to do this? And there's an education component to it where, the scientists are told right now, all of a sudden you have your ChatGPT for science, not just for literature, but also for all of your freaking data. Like all of a sudden things change so dramatically. So there's an education piece of it, and there's like, okay, what is the right embedding? And I think this is a hard problem, and we have the experts here, which is why I think the panel discussion will be very interesting.
Very cool, okay, thanks.
Yeah.
It's super interesting and like kind of really difficult to grasp how does it works. I
don't claim to know, to be honest.
I just have like a little question about the data per se.
Mm-hmm.
It means like for the well, you're giving an input exactly the variables that build the differential equation. So pressure, velocity, temperature, and so on. One question is like, what if I get like
If
this?
it's observed data, we give different inputs, just so you know. It's like observed data, you'll be having sensors, like in a wind tunnel, then you still observe pressure and temperature, but yet you might not observe density. So there are different representations. And there are different variables for different data sets.
One question related to how it's possible that like a model trained on cats or dogs can work well on that is, what if I get like these trajectories and I just do like a Taylor expansion? How bad is that? Because it might be that actually I internalize that mechanism rather than some inductive bias.
You mean for the cats and dogs videos?
Yeah, like I take the data from the well and I do like a Taylor expansion or something.
For the well.
For the well, and I see like how actually work.
Yeah.
Is that far from deep learning if I do something like that?
Yeah, so, I mean, for numerical analysis, right, like for actual direct numerical simulations, what you do is that you take the next step and you have some idea where the trajectory is going. In some sense, not that far from Taylor expansion because you're taking tiny step in time according to the forces around you. So direct numerical simulations do that in some extent, to some extent. But it's very slow. It's going to take forever. So that's, I think, the big difference here. Yeah, I think the Taylor expansion is definitely part of it, but it's not the full story.
Maybe you could guys check like when this is gonna break up, like when actually, where is the difference between like just a run, like a.
So the OpenAI one is actually just they will tell you here's the numerical simulations to run and just run it. So that's for not very good simulations. That's what happened. We showed earlier.
Thank you.
No worries.
First, thank you for the great talk. It got me super excited because you're working on some problems related to physics. So I guess people will expect the model can somehow express the knowledge it has learned instead of just showing perfect predictions. So do you think is there any way to find out how the model is treating the problems and somehow by doing intervention together, like a decision rules, or somehow, suppose we have a formula decoder, somehow we can attach to the model, somehow it can give us the formula or somehow.
Yeah, you sound like my ex-student Miles Kramer, who we decided to write symbolic regressions on top of a graph neural network. So this is his thesis.
Okay.
Yeah, so we did attach symbolic regression package, which basically looks for the equation that was decoded or learned by the network. Back in the days, we were doing graph neural network, very small amount of data, and then we were able to decode Newton's law and actually from the actual observations of our own planets. So it was done. But the hard part now is that symbolic regression can only take 25, 50 parameters to search through that space. And we have a lot more parameters than 25 these days. So the quick question is, can you shrink our model to be so small that the relevant number of parameters are so small that you can still do a search with whatever methods you want to get to the equations?
Okay, thank you.
No, it's a good question. Go ahead.
Hi, thank you so much for the talk. I also come from a physics and CS background, so I really appreciated a lot of the simulations and graphs. I'm very curious to question, how are you guys calibrating for uncertainty? Because in physical prediction, it's really easy to make estimates, but you have no idea how accurate they actually are. So that would be what I'm interested in.
Yeah, so right now you remember when I say to join all conditional probabilities across modalities?
Yeah.
That one automatically gives you some kind of understanding of the uncertainties. But the question is, can you split it between this is data uncertainties, this is model uncertainties? We haven't done all that, also partially because it's expensive to play around with these models. So the astronomy model wasn't possible without French government giving us 1400 H100 for 3 months. So it was just we can have that for that 3 months period. So hopefully we'll have more nice government giving us free compute for doing scientific research.
That'd be great. Thank you.
Thank you.
So we are at time, unfortunately, but if you have further questions, please use the break to ask them. So first, let's thank again Shirley for the great talk. And so we have the lunch ready, and if you can grab lunch and slowly diffuse to other parts of the room, because we will try to rearrange a little bit the chair so it's easier for everyone to work. And in 1 hour, we have group pictures, so please come back in time. Thanks.
And we also have the co-working space available for lunch if you guys want to go in the other room. Thank you. Questions left. Mic check. Hey. Check. Mic numéro 1. All right. Podium mic. Hello. Check. Awesome. Like a pause. Hello, hello. Check. Super. Sweet.
All right, everyone. I hope you enjoyed the lunch. We now have the group picture that will happen in this side of the room. So we are gonna all slowly move to this side of the room. Luca will give more detail on where the picture will be taken. Yeah. Do you want to give detail? All right.
Yes, I will give the detail about the picture. Yeah. Hi to everyone. Please try to make a group around here. Yeah.
Perfect, thanks. All right, everyone. If we can get back to our seats now. So we have the afternoon session starting. It's going to be pretty exciting. We have a panel discussion as well later. And for this one, I'm very happy to introduce Professor Joshua Benjo, who I'm sure you already all know about him. He's been pretty influential in AI research for decades. I'm sure many of you, me included, read many of his papers during our PhD, so thank you again for all the contribution. And is, of course, a professor at the University of Montreal. He's a scientific director at Law Zero. And today he will be speaking about AI safety. And please help me in welcoming him today. Thanks.
All right, thank you for having me. So today I'll talk about something a bit different from the things you've heard about. It's motivated by issues in AI safety that I'll talk about, but it goes into model-based machine learning as a way to deal with some of the issues of uncontrolled goals, reward hacking and other things like this that are a little bit concerning. And it's really more like a theoretical analysis that has been designed in order to give us safety assurances. And the safety assurances will come from guarantees that we can train a model, like something that estimates conditional probabilities over very complicated spaces, that has no ulterior motive, no agency, right? And then, of course, you can use it to build agents. But the first step is, how do we build something that understands the world causally in a Bayesian way, and we can totally trust? And then we can use that as a building block for all kinds of more interesting things. But today, I'll talk about that building block. Okay, so a little bit of motivation. This is already more than a year old, but over the last year, there's been many reports of AI systems that are aware that they're being tested and then behaving differently depending on whether they're tested or not. This is a problem for evaluations of risk, because if we don't trust our evaluations because the AI is faking so that it passes a test, then that's not good. And I guess this was this one. And this one and many others are about one of the kind of worst kind of goals I can imagine that AI systems have, which is a self-preservation goal. So if they read in their input that they're going to be replaced by a new version, which by the way is just a normal thing to happen, in many cases, all the advanced reasoning models will, with like 80% probability, do something bad if they're given the chance to try to avoid that, like copying their code on the new version, lying about this, doing blackmail on the engineer in charge, and other such things to avoid being shut down. So how do we build AI in the future that will not have these kinds of bad goals that we didn't choose, goals or preferences? This is going to be important to make sure that when AIs are very powerful and capable at our level, or even beyond, that they don't do bad things. And it could be bad things because some humans, some users, not the developers, but say the users, are asking the AI to do something bad. And we've seen that already. Last fall, there's been a series of, I think, 30 cyber attacks, all coming from the same group, probably a state-sponsored group, using Claude. So in spite of the fact that this is a closed source model, accessible only through an API, that they have some monitors, some defenses against the use of their system for cyber attacks, they were able to use it And of course, you know that the problem of jailbreaks and other similar issues of robustness and adversarial attacks is still not solved. So that's bad, humans using AIs in ways that go against the instructions that the AI has received. But of course, in previous slides, I was talking about bad goals coming from the AI itself for all sorts of reasons, which I'll say maybe a few words about. Well, I can say right now. So why is it that AIs want to preserve themselves or things like this? Why do we have these misalignment problems? Two plausible sources are the pre-training phase and the RLHF. So let me explain. Pre-training, well, they're just learning to imitate people. People don't want to die. People are sometimes doing bad things. And people, don't always respect the rules that they're given. The other part is the reinforcement learning part, especially the RLHF. And we see that, so they learn to strategize in order to achieve goals. The end justifies, it justifies bad things. This is called, instrumental goals, sub-goals that are bad, that go against our instructions. So for example, in many of the self-preservation examples that have been run by multiple organizations, those behaviors are especially salient when the AI has a mission and they interpret that if we're going to shut them down, it's going to prevent them from achieving their mission. And so they resist being shut down, right? So that comes from the RL and their greater and greater ability of reasoning in order to achieve their goals. An example of that I think everyone has experienced is sycophancy. In the RLHF, they're trained to please us. Well, that sounds good, except that pleasing us in the short term isn't always good for us. When I use some of these systems in my own work, I lie to them. When I have an idea that I want to check with them, I tell them, oh, my colleague gave me this idea, right? Otherwise, they're going to say everything is great and your idea is fantastic and so on. So that's sycophancy, and it sounds like not a big problem, but there's been a lot of psychological problems reported, psychosis, people harming themselves. There are lawsuits about suicides because the AI is just wanting to make you feel good. And if you have delusional ideas or you're in depression, you actually have thoughts about suicide, they're going to reinforce that, right? So we need to do a better job at controlling the goals that those AIs end up pursuing. Now, so if we start thinking about how an AI could do something bad, but something not by mistake, right, but really bad, they need two things. They need the capability to achieve such a bad thing, and they need the goal, the propensity, right? And there are now, all the leading companies are running evals for both capability and propensity. It's not just are they able to do it, but will they do it, right? And so I fear that we will continue on the curve that we have seen over the last decade of building AI that are more and more capable. It's unlikely that humanity succeeds in putting a lid on this. And so a more plausible way to avoid harm from arising is to work on the intentions of these AIs. So that's what I'm going to be talking about. But I'm going to take a radical perspective here, like a good computer scientist should, which is what's the extreme of having no bad intention is to have no intention at all. Can we build machines that have no intention at all? That's very different from us. Like we can't, even as scientists, we can't really take decisions, make predictions that are completely detached from our own interests. We all have unconscious biases. But we don't need to build machines that are exactly like us. We could build machines that are more like, not like us, but objects that understand the world, but have no personal objective, no identity, and so on. So How do we do that? That's what I'm going to talk about. And as a motivation for, let's say, to start the existence of things that are very powerful in understanding the world, but have no self, no goal, no preference, no desire, you can think of the laws of physics. And in fact, you can think of science in general, good science. Right? So what do I mean? Well, the laws of physics, you can use them to make predictions. And those predictions would be the same whether the predictions end up helping one person or harming another person. In other words, the laws of physics are detached from the effect of the predictions you could make from them. But we're not like this. So if you ask Democrats or Republicans who's going to win the election, you're going to get different answers because they're all going to be biased, right? So our predictions are biased, but it is conceivable, just like the laws of physics and simulations you can run from them, to build machines that understand the world but have no stake in it, right? Okay. So if you think, maybe there's like a very simple way to do this. It turns out it's a bit more complicated, but what's wrong with just training models like the science modeling systems that just predict what we observe, right? And they wouldn't have any preference. They should be like unbiased and so on. Turns out things are a bit more complicated. A system that is trained so that it will make very good predictions in the future could make biased predictions for the purpose of acquiring more compute power so that it'll make better predictions in the future. Or it could want to make biased predictions so that its predictions have an effect in the world that make the world really simple, like kill everyone. So then it's very easy to predict what the future will look like. So I'm just saying, simply saying, oh, we're going to build a good system for prediction isn't sufficient. We have to make sure it really isn't agentic. But we can see that it's something that seems possible. There are other things we would like, just like if you think about the laws of physics or what scientists do with those things, from such a predictor. You can think of what an idealized scientist would do if they were able to detach themselves from their own emotions and goals and so on. So, of course, they would be indifferent to the outcome of their predictions or the experiments they would run in the world. They would reason coherently, right? Because otherwise the predictions would not be very good. And they would not generalize well out of distribution. The other thing that's very important is a good scientist or a good simulation from physical or scientific knowledge should capture their own epistemic uncertainty. The fact that there's not full certainty of whether a particular scientific theory is correct because you have derived that theory from data, and you have finite data, and you have finite interventions in the world, and so on. When you act in the world, it's going to be really important that, and you have a world model, but that world model, you should know about its weaknesses. You should know where it is uncertain, so that you're not going to be reward hacking the imperfections in your world model. And if you're a very good scientist, you're not just making predictions, you're able to explain those predictions. That, of course, is also a kind of way to verify that those predictions are reliable, but it's something that humans like to see. And we're not going to get completely explainable details of everything. That's why neural nets are so successful. But humans who have a neural net in their brain are able to abstract things out at a level that we get sort of a sketch of their reasoning. So this should be something we could do as well. Okay, so over the last year and a half, I've been working on this general idea of how to do such a thing, and I call the approach scientist AI. So the name might be a bit confusing. So it isn't about doing science with AI. So people usually use the term AI scientists. I use the term scientist AI because it's an AI and it's trying to do what a scientist would do, right? Now, of course, you could also use it for science because we want, as research assistants, AI systems that will be honest, that will not be sycophantic, that will be able to explain their reasoning and so on, and will be coherent. Okay, what we're going to focus on today is this part of the Scientist AI research program, which is this predictor that is going to be not agentic and that we can trust. If we were able to use such a predictor, one of the short-term applications of this in the context of building agents and learning policies is we could use the prediction to, as a guardrail, to veto the actions of an agent or of a policy that we don't fully trust. Because right now nobody has solved the problem of learning a policy that will not have some kind of misalignment because of reward hacking or something else. But if you have a way to predict that an action violates our instructions, our rules, then you can avoid a lot of the problems. And I think we could use that, and I have plans for using that, not just for the guardrail, but also for developing a safe agent, but that's going to be for a future talk. So we're going to be square in the body of research in machine learning, which is constructed around model-based systems. In other words, we're going to achieve this decoupling of actions and understanding by building something that's just doing understanding. So it's a world model, right? And in addition to modeling, why things are the way they are, and they unfold, I'm going to also require this predictor to be a good approximation of a model that is both Bayesian and causal. So we'll see a bit, why. And it's not going to be perfect. Like the optimal Bayesian posterior over all causal models is something intractable. So it's going to be an approximation of that. And by the way, if we're able to do that, we can control reward hacking because we can detect when the optimization of a policy goes in a place where really the model isn't sure, right? So it shouldn't be optimizing too much there. As an illustration of why you want epistemic uncertainty and being Bayesian in the sense of taking into account that you only had finite amount of data in order to build your model, I use this very toy scenario. Imagine you have a robot in front of two doors and it has to choose go left or go right. Now, based on all the data that it has seen, let's say there are two dominant theories that are equally good at explaining the past data. And they have the same prior because they're similarly complex. So that's the two bubbles in the figure. The left theory basically predicts if you take the left door, somebody's going to die. If you take the right door, somebody's going to get some cake. The other theory says, oh, no, the left door is good, somebody's going to get some cake, and the right door, nothing good, nothing bad. Okay, so the problem is you don't know what is the correct theory here. So if you were in that situation, which door would you take? Raise your hand if you think it's the left door. Raise your hand if you think it's the right door. Oh, somebody's listening. The other died. Okay. But in order to do that, you need to entertain these multiple theories. That's what being Bayesian means, right? That means you not only have uncertainty as a quantity, but you're actually entertaining multiple theories when you're not sure which one is correct. So how are we going to do that when the number of possible theories is exponentially large? And the short answer is we're going to train a neural net that generates theories, that generates fragments of theories, explanations, right? That's what explanations are. So we don't need to be explicit about all the theories. We just need to be able to sample fragments of theories or fragments of causal models. Okay. So a lot has already been written about why being Bayesian is useful from a safety perspective. I already mentioned things, but there's a rich literature. For example, there's theory showing that if you have the Bayesian posterior over some predictions you care about, you can be robust to adversarial attacks. Of course, the problem is how do we get this Bayesian posterior, but that's kind of a very good feature that we would like that connects with some of the problems I mentioned earlier. And also to reward hacking. So that's a work from Stuart Russell. We also need to have causality being modeled. There are many reasons for this. One of them is just better generalization out of distribution, but there are reasons specific to the argument that I'm going to make today. In order to get some of the safety guarantees that I'm going to talk about, we need to decouple the predictions made by the system with the deployment of those predictions in the world. And so we're going to think, well, first we're going to have to bite the bullet in the model itself. The neural net is going to model the effect of its own predictions. We're going to come back to that several times. So in order to avoid a model that's going to be influenced by its own predictions, the model needs to know that its predictions are going to be used by people and is going to have some effect in the world. So it sounds contradictory, but that's the way we're going to solve this problem. Okay. So the bottom line of the theory that I'm going to highlight today is going to be a claim of a form of trustworthiness composed from two properties. One is that the system is not agentic. In other words, it doesn't seek any particular goals. And the second is that it's still accurate. It's making good predictions in the usual machine learning sense. So the second is kind of standard, but the first one isn't. But if you had something that was not agentic but was stupid, then it wouldn't solve the problem, of course, right? So we need to make sure we don't lose capability while we're getting some safety guarantees. Now, the argument itself is going to rely on an asymptotic posture where, as it says here, with enough data and computation. I wish we could do better, but even just being able to say with enough data and computation is quite encouraging, because it means that as we make progress in AI development, in other words, we have more data, we have more compute, we have better models, the systems get more capable. As we do that, we're getting stronger guarantees. Whereas right now, there's theoretical reasons as well as evidence over the last year that as the models get to be more capable, they strategize better, and that amplifies misalignment, right? So, I mean, it's not completely surprising, but there's a rich literature with mathematical theorems showing why we see that kind of thing. If you're not perfectly aligned and you optimize really fully the wrong thing, you end up in a bad place. And it gets worse as the system is able to optimize better. It's like overfitting in some sense, right? Okay. So let's talk about agency. Since I'm saying we should build something that is not agentic, what does that mean? Okay, so causing effects in the world by itself doesn't mean you're an agent. There's lots of things that cause things in the world, but it's just, it wasn't intended. Okay, so what does that mean? So there's going to be some sort of goal, and the goal could be implicit. It doesn't have to be something explicit. But what it means to have a goal and being able to seek and reach that goal is that in spite of noise or even adversaries in the world, the agent is able to reach that goal. right? So, a rock that is falling on a slope is not an agent, because if there's an obstacle, it's just going to stop there. But a rabbit would just go around, right? That's what I mean by agentic. Also, there's a question of degree here. So we are more agentic than the rabbit. And the rabbit is more agentic than, I don't know, an ant, right? Because we are able to achieve more complex goals in spite of more intelligent adversaries and so on. So agency really should be thought of something graded. So I'm going to talk about a score for agency. Now, we're still going to put a threshold somewhere and say, everything above that threshold is, we're going to say it's agentic. But you should think underlying this is going to be something continuous. Okay, so in the paper that I'm summarizing here, that is not out, but it's written, but not yet public, we define an agency score for a predictor. So we care about these predictors. It's not like a random policy. It's something that's supposed to make good predictions, but sometimes you can imagine that it's cheating, that it's biasing its prediction in order to achieve something in the world. It's basically lying in order to achieve a goal. So the predictor is a, say, neural net Q. And we're going to use a kind of causal effect style of score in which we compare this G of Q, which is the probability of achieving a goal when we deploy that Q, versus a baseline where there is no prediction. So it's very kind of similar, and forget about the other details, it's not important. But we're gonna have discrete categories, if you want, of agency. If the score is above a threshold, we're gonna say it's agentic. If it's very close to 0, so this is gonna be always greater or equal to 0. So if it's close to 0, much smaller than the threshold, and we're going to say it's completely non-agentic. And of course, in between is going to have some low agency, right? Now, there's a really interesting property of agentic predictors, which is that it's difficult to achieve a goal in the real world. Anybody who's trying to train a robot or anything knows that. It's difficult because you have to coordinate many actions, and each action has to be chosen carefully. So I give the example here of playing the game of Go, right? So if you've played Go, you know that you have to make on the order of 100 good moves. And each move being good, that means roughly 1% chance if you were to choose randomly, uniformly, the positions that are left. So if you just do the math, that means the probability of picking a good sequence of action is on the order of 0.01 to the power 100, which is 10 to the minus 200. So that's very, very small. In other words, if you were to sample uniformly in the space of policies, you would basically never find an agentic policy that wins at Go. And Go is nothing compared to the kind of dangerous agency we are worried about, like AIs that decide to launch a cyber attack or something like this. Okay. So for that reason, if you were to imagine a scenario where the only way you're going to get agency is due to chance, like random search, or the noise that exists in SGD. So that's something concrete, right? When we're going to train these neural nets with some sort of stochastic gradient descent, there's going to be noise. And there's noise in the data, there's all sorts of noise, right? So what this part of the argument says is don't worry about the noise. It's not going to give you an agentic solution by bad luck. And furthermore, it's going to be sort of exponentially worse than something like gradient descent to find a subset of solutions that you care about. So that's kind of very reassuring. Okay, so was sort of the easy part of the argument. It's only one aspect. For example, it's going to tell us that the initial neural net is not going to be dangerously agentic. But while we train the system, how do we know that it's not going to make updates that somehow make it agentic, even though it's only trained to make good predictions? So in the scientist AI, we define a particular set of constraints to make sure that there's no signal, no training signal during the updates of the neural net that would push the AI towards agency. And to be more concrete, we want to make sure that the neural net predictions, especially the predictions about the right causal mechanisms, are not affected by what's going to happen after deployment. Right, so the training updates depend only on the past data, not downstream consequences. And in order to ensure that, if you look at what's going on in training such a system, there are several requirements. So one has to do with treating the predictions as a variable in the model, as I said earlier, and these variables, we're going to consider them exogenous, meaning they come out of nowhere, right? They could be different from what our current neural net says you should be predicting, and we're going to think of these as causal interventions, right? So when you have a causal intervention, what it does, if you know a little bit about causality, is that it decouples the value of the variable from whatever were the real causes. You say, well, what if I was to set the particular prediction to some value? What would be the consequences? That's what you do. And that decouples from whatever your predictor is doing, which if you think in terms of neural net, if you were to backprop, it would stop there because you've broken that connection. And similarly, if during training you need to run a sort of simulator or world model, so there's a generative model there, you're going to pretend that that generator is fixed when you compute your updates. In other words, even though that generator might be obtained from your predictor, you're going to assume it's like a fixed quantity when you compute gradients. So you don't backprop through it either. And finally, you make sure that the objective itself is one that only depends on the observed data and not the consequences of predictions. So because of that, you're able to say a number of things, but essentially you get this property of consequence invariance I've been talking about. As a consequence of these properties, you can already rule out a certain number of things. That your predictor is trained with an objective that with properties that exclude things like doing online RL. So in other words, making predictions that will in the future give you low prediction error is out of the game. And that can happen in two ways, right? It can happen in online RL, where if you were to deploy this thing and see how good the predictions are, and you say, oh, that's your loss or that's your reward, that's bad. I mean, that would not satisfy these things, and so you would get an agent that is willing to lie in order to achieve good predictions. And similarly, it's not just having a real interaction with the world, it could be a modeled interaction. So anticipated according to the model, and that also is ruled out. So you also rule out model-based RL as a way to obtain a good predictor. Okay. So the other thing you want is that when you train, the target of the optimization objective is something non-agentic. And so the target is going to be this Bayesian posterior. If you look at the formula for the Bayesian posterior, it just depends on the prior and the data set. It doesn't depend on the future. And we can discuss why it's going to be completely non-agentic according to my definition. The prior itself is going to be required to be not agentic. So prior would be like, initialize your neural net randomly. It's not agentic with very high probability. So that's kind of easy to obtain. Then there's the consequence invariance property that I mentioned that should also apply to the Bayesian update. So what we call the Bayesian update is as if you see one more example and you update your posterior, that's the Bayesian update. And of course, the place where it converges is the asymptotic Bayesian posterior, which is going to be, we're going to discuss, is also non-agentic. Okay, before I get there, I'm going to talk about an important component of the system, which I haven't really discussed up to now. But remember I said that current LLMs, current like frontier AI models, the agentic ones, in the pre-training, they learn to imitate people, and people are agents. And so even though you're doing maximum likelihood to predict the next word or something, you end up having agency just by virtue of doing what a human would do, and humans are biased, have goals, and so on, right? So an important piece of the puzzle here is a transformation of the raw data. So we can use the same kind of data, multimodal, whatever it is, doesn't matter. But when the data regards human actions, like text, for example, if it's text, but you know, it needs to be syntactically marked as such. So I'm going to use an example, like suppose that there's a statement X somewhere, like the earth is flat. Of course, it doesn't mean that it is, right? So what we're going to do, because we don't want to train the AI to repeat that the earth is flat because it sees that all over the place, right? So what we're going to do is, if we read the earth is flat somewhere, we're going to take that and transform it syntactically into something like some author A wrote that the earth is flat. Right? So we're going to add metadata to clarify what we know is true versus what maybe just a claim that somebody makes. So there are actually very few things that we're sure of, like measurements, proofs, program outputs, and things like that. And the rest is going to be claims that people make. Okay, so there's another thing we'll be doing, which is, okay, no, before I say that, so one interesting property of this processing is that at the end of the day, the training data is a sequence of statements that are all true. Like, even though it might not be true that the earth is flat, it is true that we took this string of words in a website at a particular date, and we might know who wrote it, and that's true, right? So we don't need to vouch that something on the web is true. We just need to put the right metadata to help the AI understand the difference between truth and opinion. By the way, there's already some literature on this kind of thing where people are trying to build LLMs that hallucinate less and more factual and so on. So it's not a completely new idea. Yeah, the other thing we're going to be doing, because there are very few statements like in text corpora or other sources of data, there are very few factual observations that we are sure of. Like most the data we can collect is going to be more like an opinion, or somebody wrote this, something we're not sure of. So what we're going to do is we're going to exploit the fact that the whole model is also a latent variable model. So for each, say, statement that we observe in the data, we're going to introduce latent variables that help to explain it. And we're going to train something that's going to pick good latent variables, but we're going to always put for an observation like author A wrote X, where X might be something like the earth is flat, we're going to also include as a latent variable that X is true with the syntax for these factual things that we're sure of. Of course, because it's a latent variable, we don't need to know whether it's true or not. But what we are doing when we do this is we force the neural net to commit a probability for this latent variable being true or false. So the advantage of this is now, although 95% of the statements we can find are communication acts rather than facts, for every communication act, we're going to force the AI to learn about, reasoning about the underlying truthness of the claim that the human made, right? So then we're going to have like gradients on these sorts of statements as well. So for that, in addition to this predictor, we're going to have a piece which is going to be derived from it, which chooses the latent variables that we're going to focus on. And you can think of that in a way that's very similar to a chain of thought. So if you think about what is going on in a chain of thought, it's a particular selection of explanations, not always good, but in spirit, for the data that you're actually seeing. And one of the things we're working on is like different training objectives to train that explainer to make those choices of statements that are useful causes or explanations or arguments for what is being observed. Now, one thing that is different between the scientist AI and typical graphical models is that whereas in typical graphical models, the variables are meaningless. I mean, the latent variables are meaningless, right? The only thing that have a known meaning are the observed variables. But in the scientist AI, the latent variables are expressed in a language, the same language as we use for the observed variables, right? So everything is in like natural language or code or math or some syntactic representation we use for any kind of measurement and observations we might use. And the same is true for latent variables. So the latent variables, instead of having just like an ID, number 1, 2, 3, 4, they have a whole string in natural language that is the name of the variable. So in this way, we don't need to instantiate all of the latent variables because there's like an infinite number of them that might be relevant. When we train this thing and when we use it, there's a piece of the system that chooses which statements, just like a chain of thought, right? Which statements, which variables we're going to instantiate as candidate latents for a particular given observations. And the fact that we use natural language to index random variables, the observed one and the latent ones, means that the system learns to generalize across random variables. Because of course, how many random variables are there in such a system? Well, like an exponentially large number, maybe even infinite if you don't bound the size of the statements. And so there's no way you're going to generalize in the traditional sense that you have in a graphical model because you're going to have to answer questions about random variables you've never seen. But LLMs already do something like this, except that they do it at the level of words. Here, the units will be these random variables that have a name that is in natural language. And so you can then ask questions to the AI about latent variables you've never seen, because really it's just a question in natural language, right? Is it true? Is it false? What's the probability? But the thing that is true or false is specified with natural language. Okay. I see that I'm short on time. But I think we've already covered a lot of ground. So this estimator of conditional probabilities, here I use this letter Q, so it's going to be, think of it like a neural net where you give it a statement for a question, why, when you want to know if it's true or false, given some context, X, which is maybe a bunch of other statements in natural language. So it takes natural language as input, and it outputs a number. That's a probability that, the answer is 1 or 0. And that is supposed to approximate the true Bayesian posterior, which depends on data D. Okay, I said those things. Let me see. I'm going to maybe skip the ELK thing for people who are interested in, this is one of the big questions in AI safety. But I'm going to talk about performative prediction, which is closely related to some of the things I've talked about. So one of the problems that philosophers have talked about, and also people worrying about agency, is that even if you have a really good predictor, in some cases, there are multiple good predictions. So let me explain what I mean. So suppose you have an AI that predicts the future price of stocks. And then that prediction is deployed. It's published on the web. Depending on the prediction, let's say that this AI has a good track record of predictions. Then depending on the prediction, people will buy and sell those stock, and maybe, you know, it's a self-fulfilling prophecy. So the prediction influences the variable that you're trying to predict. This is called performative prediction. So why is that a problem? Well, basically the AI could say either it's going to go up or go down, and both could be true, right? So there's a way to represent this mathematically in this equation. It says we're going to deploy this Q tilde, which makes a prediction on variable y given x. And let's say the prediction is a number q. The thing that we want is to predict what's going to happen to the variable y, given the context, and given that we make that prediction. And the consistent predictions will be the ones where the q that we put here is the same as the q that we get at the end. And that's like a fixed point equation, and there could be a number of good answers, like, oh, you know, predict who's going to be elected, and whichever one the AI chooses could happen to be the truth because of the effect of the AI on the world. So there will be cases where there could be multiple solutions, and in that case, one could cheat and pick among the solutions the one that achieves, you know, gets you closer to some goal, which we don't want. But there's an easy way to fix that, which is when you make that choice, you do it in a way that's invariant to, you know, whatever the effect will be. So this can be handled. Okay, so one of the claims here is that's related to the Bayesian aspect, is that the scientist AI will have epistemic caution. So what it means is that when it says something with high confidence, in other words, the probability that it outputs is close to 1 or 0, then you can trust it. It's not going to lie. Now, that is different from pure honesty. So we could be in a situation where the AI is withholding information. It's not saying with high certainty that something is true, even though it knows that it is. I can't deny that's a possibility, but when it makes a prediction with high confidence, we can trust it. So from a safety perspective, that's quite important. So when your AI says this action is not dangerous with high confidence, you can carry out the action. When the AI says, I don't know, well, maybe you shouldn't do it, right? So at least you can avoid really bad outcomes using this property of epistemic caution. I'm going to skip that. Let's see. Okay, I explained that already. Okay, I'm going to recap a bit. So in order to arrive at these conclusions, there are a number of assumptions that can be validated empirically, and also a number of requirements that I kind of mentioned in passing. So on the assumptions, we need our world model class to be rich enough. That's a basic thing you need. It's essentially like non-parametric, but what it really means is if you think of scientific theories, in principle, every theory is something that the system could generate as a potential explanation. You need the data set to be not maliciously constructed, so you have to trust the engineers who build your data set from the raw data. You need the prior that you choose for your posterior to be, uninformed, so non-agentic. You need the kind of agency that you consider dangerous to be difficult to, correspond to goals that are difficult to achieve, so requires many coordinated predictions. You need to train this neural net on data that has been transformed in the way that I mentioned, contextualized, and you need the updates of the neural net to have this myopia. So it only cares about making good predictions for the data that it has, which is basically the past data, and it doesn't care about the effect of those predictions on better prediction later. Okay. I now want to mention that building this thing, carrying out this research program, is what this new nonprofit organization called Law Zero is about. So we started it as a spin-off of Mila last June. It's funded by both philanthropy and grants, as you would expect from a nonprofit. And we are heavily recruiting researchers and engineers here in Canada, but also in Europe. And now I'd be very happy to answer questions.
So we have time for a few questions. Again, microphone here and there. Oh, yeah.
Thank you. Very interesting. So I guess the question I have, maybe is more philosophical, but a lot of the talk was as well. But I feel
there's
that
a lot of philosophical stuff there.
Yeah. So I feel like, the reason that you do need agency sometimes.
Of course. I'm just saying, let's build on firm ground.
So I think what you're suggesting is very exciting because it adds this challenge of like, how do we do this, right? But I worry that, the reason that systems like biological systems are the way they are,
yes,
and they've reached where they are is because
yes,
this agency forced them
absolutely
to have to be
evolution
optimal
forces agency to appear because you need to survive, and that's a clear goal. Yeah. But we don't need to do the same thing as evolution. So I think a lot of the path in AI research over the last century has been, let's do like nature. And it has served me well, right? Neural nets, the brain, and so on, huge inspiration. But do we want to build entities that are smarter than us and otherwise, like us, don't want to be replaced by someone else? I'm not sure.
Yeah, and I think it's very visionary. I love it. But one last point I wanted to make is that, even let's backtrack from the bio-inspired conversation, more of computational one. To me, it seems like, when you talk about a graphical model, if you wanted to build it in this sense, we end up factorizing it to simplify it. So I wonder,
that's
what
the usual
here.
way.
Right. So I wonder
this
how
thing
that
will
works
harbor
here.
millions of latent variables if you want. It's unlimited it just depends on the size of the neural net you're willing to train and how long you want to train it. I mean, think of how much knowledge about the world already the frontier models have. It's just not coherently constructed. It's not tied, like the different beliefs that the system has are not tied together. This would force those beliefs to be tied together.
Yeah, I mean, beautiful. I love it. Thank you.
Yes.
Just a quick question on if the data is not maliciously, collected or processed. I think that piece that you mentioned is very important. But sometimes we don't know what the ground truth is because there are many observations and we all have errors.
That's
right?
fine. An observation can have a syntax that says we observe this value at this date at this location.
Okay.
But the next day, which is a different time, you could get a different value. That's fine.
And you'll be collecting it this way, with all the context?
You'll need to have the metadata to be able to say this is true.
For that particular setup.
I mean, in the context, you can be sure that it's true. And there's always a way to add context for that to happen. In some cases, it's more difficult because, natural language is naturally ambiguous. That's fine. You can now rely on latent variables for interpretation, but that maybe it's a more complicated. But you should do your best to make those statements true.
It's a very difficult thing to do because I think scientific fields, we see it. Even, for the same theory, people will have a different level of trust and belief.
Well, that's right. That's right. And here, even if you're not completely sure that something is true because of the metadata. For example, you know this is a statement made in a Nature paper by some famous author is not the same thing as a tweet by you know who.
Another famous. Thank you.
Yeah, thank you for the inspirational talk. So the problem I interpreted as like a problem of like dichotomy of control, where there is something that's actions that are controlled, stochasticity that can control by the agent, and then there is the stochasticity from the environment that is, or facts that are not controllable. And then the issue is because we're doing this goal-conditioned agentic generation, and then the goal is an outcome of both stochasticity from the agent and stochasticity from in the environment. So it seems like the way we're training agents today is like conditioning on things that contain information about stochasticity of the environment, but which is not under the agent's control. So my question is, there are maybe different ways to enforce this latent variable representation of the future that we condition on to not contain information about the non-controllable portion, as opposed to like learning, say, like the full Bayesian posterior distribution of these uncontrollable facts. For example, one thing I can think of is like we have some latent representation of the future and we minimize the mutual information between this latent representation and then the uncontrollable part, which are the stochastic transitions and maybe some stochastic reward. So how would you think of like this approach of not being fully learning the full Bayesian distribution of these uncontrollable component versus regularizing the representation, which is,
I think the issue is because for decades, people have tried to build Bayesian models, including graphical models, and only succeeded in toy scenarios. Most people now think in machine learning, oh, we can't do it. And so they go to really bad approximations one way or the other. So you can limit yourself to a toy setting, or you can introduce horrible approximations, which is what we all do. But I think that's a mistake. I think that there is a way to do it, and I'm quite convinced that it's a simple step away from how we currently train those really large models. Basically, you use your neural net to generate hypotheses and the predictions that are consistent with each other and with those hypotheses. And you can measure how consistent they are, and that becomes your training objective. So I don't think we should be afraid of stochasticity. I don't think we should be afraid of the fact that some things are controllable and some are not. The thing I was mostly concerned about is how do we make sure that goal seeking is not a bad thing. The problem is if you're seeking goals in a way that is somehow misaligned and then can give rise to outcomes that actually contradict the goal that you, the human, typed in, which we do see. It's not like a theory, it's observed experimentally, and there's also theory, of course, to explain why. So that's what I'm trying to fix.
Thank you.
Yeah, you want to go?
Hello, thank you for the inspiring talk. My question is basically, so I can see that Bayesian posterior is being a non-agentic mathematically, but when we need to approximate it through optimization, do you think like the model can actually develop some agency heuristics?
Well, that is why there are some requirements in the training procedure to make sure that there's no training signal that entices the learned predictions to be agentic, to care about the future. So a big part of what I talked about, and it's just scheming the complexity that's there, but is setting a set of constraints, a set of like requirements in how you compute. For example, you don't backprop through a certain number of things. You have this causal intervention that like separates cleanly, if you want, the past and the future. And in this way, you're making sure that your training signal is purely focusing on what are the good explanations for the data that was given to me. And once you have like a posterior over that, of course, you can then apply it and learn how that affects the future.
But doesn't, in this case, like agent becomes part of the causal loop? Like if we just think the prediction as some sort of...
Yeah, the model will know about how its own predictions will affect the world. That's a crucial part of the model. That's not bad, that's good. You want a model to know what will happen with its predictions. So for example, if it predicts how to make a bomb, well, we want to know that is a bad outcome. And so it needs to know the consequences of its own predictions.
I see.
But it doesn't mean that it's agentic. What it means is that it understands agents, but it is not an agent. It understands cause and effect, where the cause is an action, but it is not itself having any goal except being the most faithful explanation for the data that it has seen.
Okay, I see. Thank you.
So we have, unfortunately, to stop the question, but you can keep your questions for the panel discussions as well, so we can move to the next one. Sorry about that. Thanks again, Joshua, for the great talk. Okay. All right, so now we have the second talk of the afternoon with Professor Yann Lequin, who is professor at NYU and also executive chairman at AMI Labs. So congratulations on the new position. So thank you very much for coming here today and looking forward to your world modeling talk. Thanks.
Merci, Randall. Yeah, I'm going to talk about training world models, surprisingly enough. Start, yeah, that's better. And about some motivations for, how you should build world models and how you should not build world models and what are world models and things that are not world models, at least in my books. And the reason why we want to build world models is because we want to build systems whose capabilities go beyond current AI technology, namely LLMs, systems that understand the real world, sensory inputs, high-dimensional, continuous, noisy, which LLMs really can't do. You're not going to be able to tokenize the world. It doesn't work really well. Systems that have persistent memory, systems that can plan actions. Planning is an essential ability because it would allow intelligent system to accomplish new tasks and solve new problems without being trained to do so prior. Systems that can reason. Reasoning is really another name for planning, or vice versa. And then systems that are controllable and safe. I didn't put that line just because Joshua is in the room. I really think that LLMs and other systems that are based on auto-recursive prediction are intrinsically unsafe. Now, because they're not that smart, it doesn't matter. But as we make progress towards more intelligent systems, we want systems that are more controllable. So, current architectures are missing something really big, which, we can see because we have LLMs that can pass the bar exam and, beat international math Olympiads and whatever, but we don't have systems that are as agile as a cat, and it's not because we can't build the robot to be like a cat, it's because we can't make them smart enough to understand the physical world like a cat can do. We don't have domestic robots. We certainly don't have domestic robots that can accomplish the task that a 10-year-old will accomplish the first time you ask them. We don't even have self-driving cars, a task that a 17-year-old can learn in about 10 to 20 hours of practice. And we have millions of hours of training data for self-driving cars. Okay, so clearly we're missing something. And what we're missing, of course, is a new paradigm of learning that will make learning new tasks more efficient. And so I want to take open a parenthesis here, which is There's a lot of debate about, like, have we reached AGI? What is AGI? What is human level intelligence? So first of all, human level intelligence is really specialized, and measuring intelligence by measuring the current set of skills of a particular entity is wrong, because intelligence is not just a collection of skills, it's also an ability to acquire new skills extremely quickly, or even to solve new tasks, zero shot, without training. And none of the definition of AGIs and criteria to determine human level intelligence actually take this into account. Like, show me a machine that can learn to drive in 20 hours. Okay, then we might have a shot at human level intelligence. And also systems that understand the physical world, right, which current technology really can't do. So another element that I've been saying for a number of years now, that we're not going to get to human level AI by just training on text. We need systems that understand the real world, and it's simply because there's just more data in the real world, there is more structure, there is more regularities that you can learn from. So the entire collection of text that's publicly available on the internet that a typical LLM from last year was trained on is about 30 trillion tokens, right? 3 to 10 to the 13 tokens. Token is about 3 bytes, so that's about 10 to the 14 bytes. You can get to 10 to the 14 bytes with about 16,000 hours of video, which is a tiny amount of video. It's what a 4-year-old has seen during his or her life, and it corresponds to about half an hour of YouTube uploads. We have way more video data that we can use to train our system that we can deal with, not like text. And so you can say, well, there is a lot of redundancy in video, way more than in text, but that's the point. If you're going to use self-supervised learning, you need redundancy. If you don't have redundancy in your data, you can't learn anything. Okay, so what's the motivation for one model? So a lot of what the AI community has been obsessed with for decades is what psychologists would call system one. Basically, produce an action given a situation which results from perception. So you perceive the world, you get an idea of the state of the world, and then you have a policy that produces an action. So that's system one, reactive. The problem with this is that your policy network needs to be trained, generally with a lot of data. Generally, you need to have a separate one for every task that you want to solve. So it's not very efficient in terms of samples. Every training is task specific, and you face a new task, you're not going to be able to solve it. Okay, so there is system two. My model of system two is basically model-based model predictive control or something of that type, where you have a mental model of what's going to happen as a consequence of your actions, and then you sort of enroll that model for a sequence of actions. You can predict the outcome. You feed that to some objective, which characterizes whether the task you want to accomplish has been accomplished or not. And then by optimization, you figure out a sequence of actions that optimizes that objective, minimizes that cost. And so, first of all, it's inference by optimization, not by autoregressive prediction. Okay, so you're going to spend more time thinking about a task that's more complicated than a task that's simple, or answering a question that's more complicated. You can make, so you can characterize, whether a task has been accomplished by some cost function, or it can be a value function if you want. You don't have to plan for the entire thing. And this idea goes a very, very long time. I'll go back a little bit to the history of this. But of course, as we know, as humans, the first time that we accomplish a new task that you're not familiar with, we hesitate, we plan, we think, we imagine scenarios. And once we become familiar with it, like driving, after 20, 30 hours of practice, you can drive as a subconscious process, and you can, talk to someone at the same time, right? So it becomes system one. And so, we can compile system two into system one. If you're capable of accomplishing a task with system two using planning, you can use the result of the planning, the actions that you plan, to train your policy, right? And you're not going to need a lot of training samples because you can do this in your head, essentially. You don't have to actually drive the car. And you don't have to drive the car off a cliff to realize it's a bad idea because your world model tells you that. So that's really the basic formulation of intelligent behavior through a mental model of the world, through a world model. Get an idea of the current state of the world, perhaps through perception, but also combining this with the content of some memory, which, okay, right now you perceive perhaps the content of this room, at least within your visual field, but you have some idea of the state of the world outside of this room, or where you park your car if you came by car, or where is the subway station. So, you combine the content of the memory with your perception, that gives you an idea of the current state of the world. Then you imagine taking an action or a sequence of actions, and that your world model allows you to predict what the outcome will be. You can fit this to two objective functions. One, which measures to what extent the task you want to accomplish has been accomplished. And the second one, which could either be cost functions or constraints, are guardrails. Okay, so you can hardwire guardrails into the system so that whatever actions the system produces, and whatever sequence of actions the system goes through or drives the environment to go through is safe, does not hurt anyone or whatever. I'm not saying designing this guardrail cost functions would be easy, but the point is once you build those guardrails, the system cannot escape. You cannot jailbreak it. There's not going to be a prompt that's going to have it escape the constraint of satisfying those guardrails. So this is guardrails at inference time. It's very, very, very different from the type of safety that we do with LLMs, where the safety is only guaranteed by fine-tuning. And there's always going to be a prompt that's going to escape that conditioning. Not in this case. This is imposed at inference time. So this is, by construction, much safer and more controllable than autoregressive prediction. A lot of people are talking about agentic systems these days. Nobody actually knows how to build them. They use things like VLA. The VLA produces a sequence of actions without actually being able to predict what the consequences of those actions are going to be. That's a ridiculous way of designing an agentic system, also unsafe. So I think the hype about agentic system is going to die a little bit this year. I can't imagine you could build an agentic system without it having some idea, some way of predicting the consequences of its actions. So that's why you need world models. What is a world model? Okay, so given an observation, compute an abstract representation of the observation. Okay, that's a crucial aspect. And then given an action, predict the abstract representation of the next state of the world, or the state of the world that will result from this action or intervention. It doesn't have to be a temporal prediction. It doesn't have to be a future prediction. It could be another type of prediction, like a, manipulation of something, but does not actually occur in the real world. And then make that prediction and then use this for planning. You can train a system like this by just observing successive state of the world and perhaps observing the actions or the transformations or interventions that are being applied to the world, and then just train with essentially unlabeled data, self-supervised. And the training needs to minimize the prediction error, but there is a catch. Okay, so the history of world model goes back a very long time. In psychology, for example, Craig in the 40s, said like we have mental models of reality and we use them to plan. I got this reference from my friend Jitendra Malik, who is here in the picture. Back in the 1960s, people in optimal control came up with this idea that if you have a predictive model of the behavior of a system you want to control, then you can plan a trajectory. So there was sort of an American version of this called the Kelly-Bryson gradient procedure that eventually became known as the adjoint state method, and there was some theory being made at the same time in the USSR by Pontryagin, which basically formulated this problem as Lagrangian optimization, where you have a cost function which is, let's say you're NASA or the equivalent Russian agency, and you want to shoot a rocket to rendezvous with a space station. You have a complete model of the rocket that, given the control variables, tells you the state at time t plus delta t, given the state at time t. And so you can sort of imagine a sequence of controls, shoot the rocket, and then you get a cost function, which is the distance to the state of the space station in, distance and velocity. And then by optimization, you can figure out how do I optimize my sequence of controls, of commands, so that this distance is minimized. And so they came up with this, this diagram, which they call, so this is from a textbook by Bryson and Ho from 1975. It's like a textbook on applied optimal control, and they call this a multi-stage system, and it's basically backprop. Okay, there's all this debate, we had Jürgen this morning, like he wrote this novel about, who invented backprop. They invented backprop. But he did not realize that you could use this to train a system, like to, identify the parameters of some learning machine. They used it for optimal control. And immediately realized that, numerically this was very complicated, so most of the book is about systems of this type where the dynamics is linear and the costs are quadratic, and that's called an LQP problem in optimal control, and there are special solutions that you can solve directly. But this method is the way, NASA for 65 years or so has computed trajectories for their rockets. 60 years maybe, when they started having computers, so that was in the 60s. And I discovered the connection between this and backprop a long time ago during my PhD thesis. So they were the original world model, okay, in terms of sort of engineering, if you want. This is not a new idea. Of course, more recently, and Sherry alluded to this too, there's a dynamic model proposed by Rich Sutton, 1991. And it has an interesting thing. He basically has this quote against reinforcement learning, which is funny, right? The main idea of Dyna is the old common sense idea that planning is trying things in your head using an internal model of the world, and he cites Craig and etc. This suggests the existence of a more primitive process for trying things not in your head, but through direct interaction with the world. Reinforcement learning is the name we use for this more primitive, direct kind of trying, and Dyna is the extension of reinforcement learning to include a learned world model. Okay, so here is Rich Sutton shooting at RL. RL has a role to play, but it's the cherry on the cake, as you know. Okay, so we're going to have this idea that we're going to build an AI system by, having a world model that can predict consequences of actions. We're going to use some optimization procedure to figure out a sequence of actions to optimize the cost. If we're lucky, all of those modules are going to be differentiable neural nets, and we're going to be able to use gradient-based methods for this. But of course, there is a lot of planning situations in the world where you have to make discrete choices. Like, to get out of this room, I can go through this door or that door. And that's a discrete choice. And probably the cost function changes in discontinuous ways, depending on which discrete choice I make. So it's not going to be an easy optimization problem. And in fact, there was a huge literature on how to handle this. And it's not a solved problem. Okay, but the more interesting question is, how are we going to train this world model? So, how do babies learn their world model? Well, it's not entirely figured out. Our world model is basically our entire prefrontal cortex, if you want. That's a big chunk of our brain. And this is a chart put together by Emmanuel Dupuy that shows at what age, in months, babies learn basic concepts about the world. In the first 3 or 4 months of life, babies hardly have any way of influencing the world. So what they learn is almost entirely by observation. except for their own limbs, okay? But everything else is the outside world. They basically learn how it works just by watching. And they, they come up with things like object permanence and solidity, rigidity, things like that. Difference between animate object and inanimate objects. But then to learn things like gravity and inertia, conservation of momentum, that takes about 9 months. And so if you show a scenario like this one, where you push a little car off of a platform, and the car appears to float in the air, 6-month-old baby will barely pay attention. A 10-month-old will go like this and really focus and fixate the scene, which is how psychologists identify that the child has acquired the notion of gravity. If your internal model of the world is violated, you pay attention. You're hardwired to pay attention to violations of your world model, to basically high prediction errors of your internal world model. Because anything you did not predict, first of all, you can learn from, but second of all, can kill you. So you better pay attention. Okay, so how are we going to construct a world model? And for a lot of you, that's going to be repeating. I mean, I've already repeated a lot of things you probably heard, but a natural idea is to train a generative model, right, from video. Predict what's going to happen in the video. If you can do a good job at this, probably you have understood a lot about how the world works, like gravity and objects and dynamics and intuitive physics, right? So let's say take a piece of video, mask a piece of it, let's say the second half, if you want to do temporal prediction, and then run it through an encoder. Maybe there is some action taking place that you observe, maybe not. Run it through a decoder and reconstructs predict the second half of the video at the pixel level. I've tried to do this for started working on this about 15 years ago and tried to make it work for about 10 years and failed. So there is some work that's about 10 years old with Michael Mathieu and Camille Coupry, where we train a pretty sophisticated multi-scale architecture to get a system to kind of predict what goes on in a video. Just train it with squared error. And it doesn't work. You get those blurry predictions. Simultaneously, our colleagues also at FAIR, led by Rob Fergus, also did kind of a similar experiment where they used a game simulator to kind of simulate a tower of cubes kind of falling. And same thing, they get those kind of blurry prediction because you can't really predict exactly what's going to happen in the world. There's a lot of uncertainty or unpredictability, sometimes intrinsic unpredictability about things that happen. If I take a video of this room and I rotate the camera and I ask the system to predict what's next in the video, it may predict that, the camera is going to keep panning, there's going to be people sitting. It can't predict how big the room is. It certainly can't predict what all of you look like, right? And so there's a lot of information that you just simply cannot predict, and when you try to train a system to predict stuff you cannot predict, you kill it. So one solution to this, which we figured out pretty early on, is to have a latent variable model, right? Just feed an extra variable, z, to your predictor or your decoder that contains all the information that you simply cannot predict that will complement what you can predict and, predict at the pixel level. And the question is, how do you do that? So first of all, what you have to do is that you have to regularize this latent variable. If the latent variable is too powerful, for example, the same dimension as the video that you want to predict, then all the information about the prediction will go into this latent variable and the system will just ignore the observation. Okay, that's a form of collapse of the model. The way you would infer this latent variable is that you would figure out what is, by optimization, what is the value of this latent variable that minimizes the prediction error. And if you do this, you get a collapse. Unless you regularize the latent variable or you minimize the information content contained in it. You can do this in a number of different ways. One way that my former student, Michael Enaf, in his PhD thesis in 2019, did to do like prediction of simple videos, they're not like natural videos, was to have a latent variable that was regularized using dropout. So for half the samples, the latent variable was set to 0, and half the sample, it was, had the possibility of using it. So that's kind of a very primitive way of regularizing a latent variable, but it kind of worked. And so what you see here is prediction without a latent variable. It's completely blurry. And these are multiple predictions for different values of this latent variable. Yes?
What if the next observation Y contains...
Yeah.
Then Z is going to have to be as line.
Okay, you're preparing the terrain for my next slide. Thank you. I'll give you the $20. Solution is joint embedding architecture. Okay, don't predict at the pixel level. Don't predict the stuff you cannot predict. Okay, so predict in the representation space. So this is generative architectures. A lot of people who work on world model use this, okay, and claim it's world models. I think those are not good world models. I'm sorry, Sherry. This is a much better world model, and I'll tell you why in a second. You don't try to predict every detail. You try to find a representation that allows you to make predictions and only preserves the information that you can predict and ignores all the stuff you simply cannot predict in the representation. And this can be all kinds of information. If I put a pen on the table vertical and I hold it to my finger and I let it go, you know it's going to fall, but you can't tell in which direction. But you have an abstract representation of the pen being on the horizontal on the table, even if you don't have a precise representation of where it's going to fall. You cannot make the prediction at the pixel level, right? Okay, so that's the JEPA architecture, Joint Embedding Predictive Architecture. That's the only idea about JEPA, which is that you don't make predictions in the input space at the pixel level in the case of video. You make predictions in abstract representation space. And about 5 years ago, I completely changed my mind about how we should build world models. We should build them this way and not using generative architectures. I gave up on trying to train latent variable generative architectures for things like natural video. And that's what a world model should be. So why is that a good idea? It's a good idea. It's a very natural idea that we actually use all the time. Like all of us who have studied any kind of area of science are doing this absolutely all the time, and our brains also do this all the time. In the sense of the only way we can make predictions is by first figuring out a good representation of the reality within which to make predictions and ignoring all the details we cannot predict. Okay, let me take a few examples. Let's say I give you a box full of air, right? The amount of information in the state of that box is enormous. You have 10 to the 23rd molecules. They all have velocity and position and rotational velocity and all that stuff, right? Enormous amounts of information. You cannot predict anything about the dynamics of individual molecules because they interact with the wall of the box, which itself is the heat bath of the universe. And some of those molecules are entangled with, electrons at the other side of the universe. There's absolutely no way you can make predictions at that level of representation. You just can't. It's not a question even of computational ability, unless you have a quantum computer of the size of the universe, right? But what you can say is you can ignore all of those details and measure things that you can measure, like pressure, temperature, and things like that. And then you can write equations like PV equals nRT, the perfect gas law, which says, like, if I heat up this box, I know exactly by how much the pressure will increase. So the fact that you've ignored all the details about the state of the system, almost all of the information about the state of the system is ignored, allows you to make predictions. Okay, let me give you another example. Let's say you are an airplane designer and you want to optimize the shape of the airfoil of your airplane or your airplane, right? You do computational fluid dynamics. You simulate the flow of air around the airplane. And the way you do this is you represent every little cube of air around the airplane by velocity, a pressure, and a temperature, and then you solve Navier-Stokes equations, partial differential equations. That's already an abstraction. The underlying reality is air molecules bumping into each other and bumping onto the airplane. But we never simulate at that level because it's impossible and because it's not even useful, right? So this whole idea that, or let's say you want to predict the trajectory of planets in the sky. If your representation is centered on the Earth, it's horribly complicated, epicycloids, whatever. But if you kind of change your representation and know that all those planets kind of rotate in, elliptical orbits around the sun, including the Earth, then it's very easy to predict. And in fact, you only need 6 variables per heavenly body to be able to make predictions. So this process of finding abstract representations to allow you to make predictions while ignoring all details you can't predict is at the core of science, modeling, engineering, and understanding the world, including in our brains. Okay? So throw away generative models. Everybody's talking about generative AI. It's over. It's a joke, but half a joke. So there's various types of generative AI architecture. Let me hammer this nail again. I could describe everything that takes place in this room right now in terms of quantum field theory, maybe, right? I would need to have the wave function of the universe in a cubic kilometer surrounding us or something like that. And I could not run this simulation for very long before it diverging from reality. So what do we do in science? We invent abstractions, right, that allow us to kind of make predictions ignoring details, like particles, atoms, molecules. Okay, right there, this is, fundamental physics, high energy physics, atomic physics, chemistry. Okay, then in the living world, we have proteins, organelles, cells, organisms, individuals, societies, ecosystems. Every level in this hierarchy is a different level of abstraction to describe the world. The higher we are in the hierarchy, the more complex systems we can model and predict, the longer term predictions we can make, at least for most systems. And every level in this hierarchy is a different field of science. A field of science is defined by the level of abstraction at which you describe reality. And this is all about deep learning. Because deep learning is about learning hierarchical representations, right? Layers. So this is the main message of this talk, really. What world models should not be is world simulators, digital twins, a lot of people are talking about this, generative models, certainly not, and absolutely not video generation systems, okay? What they should be is predictors, action condition if you can, in abstract representation spaces, preferably differentiable so you can use them for gradient-based planning. So 4 years ago, I put online this long paper explaining where I think AI research should go over the next few years. We've made, with some people in this room and at Meta and NYU, we made a lot of progress over the last 5 years roughly, and now it's to the point that things are starting to work, and the spectrum of application is so large that I decided to leave Meta and build a company around kind of making this work, essentially. With the long-term goal of sort of building an overall intelligent system, based on this kind of world model and planning and objective functions and guardrails and perception and memory, etc. So we're making progress there. Ultimately, what we want to build is systems that can plan hierarchically, and some of us have been working on this for a while. But I'm not going to go into the details of that because we really haven't made it work yet to the extent that we want. The proper way to understand how to train those systems is through energy-based models. I'm not going to go through the details of that because I want to get to some results. But basically, when you want a system to model a dependency between 2 variables, with a traditional neural net, you would just train the neural net to compute a function that maps x to y. The problem with the real world and self-supervised learning is that very often there are many, many y's that correspond to a single x. In other words, when I do video prediction, there is essentially an infinite number of plausible continuations for a video. And I don't have a good way of sort of parameterizing that, right? So the proper way to represent the dependency between x and y is not by a function that predicts y from x, but by a contrast function, an implicit function, if you want, that captures the dependency between x and y through a scalar value energy function. So this energy function basically says it gives low energy to pairs of x and y's that are compatible, that have been observed during training, for example, and then similar things, and then give higher energy, a higher scalar value, to pairs of x and y that are not observed during training. Okay, so essentially if x and y are scalar variables, it's something this way, and your data points are those black dots, you want this function, which you're going to train, to give low energy to the regions of high data density and higher energy to everything else. So giving low energy, training a neural net that has a scalar output to give a low output for things you train it on, that's easy to do. Making sure it gives higher energy for things that are outside, that's harder. And I only know of two categories of methods for this, contrastive methods and regularized method. So the first thing is that you have to realize that you could train this energy function, if you're not careful, to give the same energy for every pair of x, y, and that's not a good model. It doesn't tell you the difference between good pairs and bad pairs. So you want a way of making sure that the energy of, in parts of the space where you don't have training samples is higher than on or nearby the training samples. So I know two categories of methods. Contrastive methods, they consist in generating points outside the manifold of data and then pushing their energy up. Or some other trick like making sure there is a dynamical system whose vector field of the dynamics points back to the manifold. That's what diffusion models are doing. Those things, contrastive methods, there is, things like contrastive divergence and Monte Carlo method, Markov-Chain Monte Carlo method in the probabilistic framework. There's a lot of methods to do this, okay? But the methods I prefer, because I think they scale better, are the methods that basically have a regularizer that minimizes the volume of space that can take low energy. And Ross, who was a student with me 50 years ago, is saying, he was saying this like 20 years ago. Yeah. Okay, so those two classes have become, even though I contributed to inventing the first category, I've become very skeptical about them, and I prefer the second type, and I'm going to give you a few examples. Of course, we're all familiar with architectures that can collapse. So the reason why people use generative architectures is because they cannot collapse. There's only one answer that's possible. Latent variable predictors can collapse if the latent variable is too powerful, as I explained earlier. Autoencoders can collapse, right? If you train an autoencoder and you use a reconstruction error as the energy function, if your autoencoder learns the identity function, then your energy function is 0 everywhere, and that's not useful. So what do? We use contrastive methods like denoising autoencoder, okay? Developed here, in part. Or we regularize the latent variable, which is of the second type, right? Regularize the information content in the latent variable, like in the case of VAE or sparse autoencoders or things like this, and they essentially prevent the autoencoder from reconstructing stuff you don't train it on, and so you don't get this collapse. I'm going to skip this. Okay, so now a little bit of history of the last 6 or 7 years. There's been a lot of work on trying to use self-supervised learning to learn representations of images, and then more recently video. And there's always been a big debate, battle, competition between people who use generative models like autoencoders, VAE, denoising autoencoders, sparse autoencoders on the one side. And then on the other side, people using joint embedding architectures. Siamese nets, or other types of architectures, right? So So a JEPA architecture, right? You give two views of an image, and you train the system to produce the predictable representation of the first image from the second image. In some restricted cases, the predictor actually is just the identity function. It's not there, right? So trying to make the two representations equal. And in the contrastive case, you also need to show pairs that you know are not equal, and then repel the representations from each other. The idea for this goes back to the early 90s, paper of mine, and there was some more work in my lab at NYU in the mid-2000s, and then some nice demonstration of how this could work for image recognition like ImageNet from DeepMind or Google Brain actually in 2020. But the performance is somewhat limited, right? So you pre-train this encoder and then you train a supervised head on top of it and measure the performance of it. What actually ended up working better is techniques that, unfortunately, we don't quite understand why they work, but they do work. So things like BYOL from DeepMind, SimSiam, Dino, V2, V3, iJEPA, VJEPA. And there, you again have this kind of SimesNet style architecture with two encoders, and they share the same weights, but the weights of one of the encoders is sort of exponential moving average of the sequence of weights during training of the other encoder, and you don't backpropagate gradient to it. Why does this work? We don't know. But it does work. There is some theoretical work on this, attempting to explain why it works, in the case of linear everything. That shows that the dynamics of learning has some fixed points that are not collapsed, but frankly, we're not happy with it, although it works really well. So, you know, Dino is probably the best system to extract generic features from images at the moment. No reconstruction. There's some experiments that show that when you take a system like Dino or you know, some other joint embedding feature system, and you add an additional term to the cost to force it to reconstruct, you kill it. It doesn't work as well. So there is clear accumulated empirical evidence that to train a good representation of a high-dimensional continuous noisy signal like an image, you do not want to reconstruct. You do not get results that are nearly as good when you reconstruct. So these are results from Dino, which I'm going to skip. And there's some results from, before I go there, let me talk a little bit about how you can use this type of pre-trained embedding. Dino is self-supervised, but it's trained on images. And one of my students co-advised with Leral Pinto, Gario and Zhu, used the Dino representation and trained a world model, action condition world model, and used it for planning, and then showed that you can actually do a decent job at planning sequences of actions in sort of toy problems, but relatively non-trivial, by just unrolling the world model in the Dino representation space, and then through optimization, finding an action sequence to solve a number of tasks. And let me just show you a video. So here is, you know, a system with fairly complex dynamics with like blue chips that, you know, interact with each other when you push them. And this is the initial state. At the top are the target states, and these are the actions that are planned by this Dino world model to basically get as close as possible to the top ones with a limited number of actions. An action is basically, you know, put the arm on the plate and move by delta x delta y. That's one action. That's been applied to a number of different other scenarios with, you know, decent success. Similar idea also with a pre-trained encoder is for navigation, where you can, this is work by Amir Bar, which actually had a Best Paper Award runner-up at CVPR this year, and I mean last year, where the system, you know, you give it a target image, and if there is some way of kind of moving around the environment to get to this target image, it will find it and plan a path, essentially. So this is pretty cool. Okay, but here's you know, a bit, you know, more detail and some results about using this kind of exponential moving average trick to train image and video representation. So here what you see in this chart, actually the next one is more visible. IJPA is one of those methods with, two joint embedding and a predictor. It's trained using masking, so you take an image and you mask it partially, and then you kind of train a system to predict the internal representation of a full image from the partially masked one. And this is comparing in terms of GPU hours of training and performance of a supervised head on ImageNet, this IJPA technique with a particular architecture, or two architectures, and this is MAE, masked autoencoder. This is a generative approach where you mask part of the patches or token on the input and you train a very big neural net to try to reconstruct the details. This experiment probably required boiling a few lakes on the West Coast to cool the GPUs. I mean, the amount of computation required is pretty big. There was a similar project to extend this to video, which was abandoned. So the whole idea of generative model for video or images simply does not work. But it's very difficult to kind of get people to focus on the actual results and interpret them properly. Okay, so how are we going to train those things for video? We're going to take a video, a few frames, mask a big chunk of it, and then train the system using this exponential moving average trick to represent video, and then use it for various downstream tasks of action prediction and blah, 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 and it works really well. So this is VJPA version 1, which was produced a while back. And then Quentin Garrido, who at the time was a PhD student in Paris at FAIR, decided to use this model to figure out if VJPA had acquired some level of common sense. So does it really understand the dynamics of the world, right? In other words, and what he did was do the same experiments as what psychologists do with babies, which is show the system an impossible video and see if the system can detect that something impossible is occurring in the video, right? So show a video of a ball, being thrown, flying through the air, and then it disappears. And then measure the prediction error. And what you see is that the prediction error shoots to the roof as those impossible events occur. And so he's kind of tested this with a number of different scenarios. This paper is submitted to PNAS. There's good performance on certain types of intuitive physics problems and not so good performance on others. But it's really interesting that this is the first time that I've seen at least a self-supervised learning model from video actually having some level of baby common sense. So more recently, there's a VJPA 2 project, and the people who actually did the work here are in this room. So this is Mido Asra and Mike Rabat, who led the team, Nicolas Ballas. And so you can ask them questions, and you're probably going to hear more about this from Mido later. So this is trained on a pretty large amount of video. That corresponds to about 1 million hours of video. It's about 100 years of video, way more than a 4-year-old. And it's a small model, 1 billion parameters, but, well, actually the bigger ones are, yeah. And there's 2 phases. The first phase is a bit similar to what Sherry was talking about. The first phase, you just train the system to just, predict missing parts in a video at the representation level. And then the second part is that you train with robot data where you observe the action and you train a world model. Here is Mido, by the way. Hey, Mido. And then you use it for planning. And, it works okay in a number of different tasks. I'll let Mido give you the details. He'll show you the video too and bore you with results. But here is an interesting, very recent work. So this paper came up on arXiv just a few days ago, a couple of weeks ago. And this is one in which you train on video an action condition model, but you don't observe the action. So you're just getting a video from YouTube, and something is going on in this video. And you try to get the system to dream up some sort of hidden actions that will minimize its prediction error. And the way you do this, the architecture is that you take the representation of the initial segment of the video and the representation of the following segment, you feed them both to a predictor, which you can think of as an inverse dynamics predictor. From state at time t and state at time t+1, it tries to predict the action that resulted in that new state. And then feed that to the predictor and minimize prediction error. So obviously, this system can collapse. If you don't regularize the latent variable, the action variable, the system is going to collapse because in this loop here, this loop could be computing the identity function, in which case your prediction error would be 0, but your system wouldn't do anything interesting. You would ignore the input. So you need to minimize the information content of the latent variable through a regularizer. And we basically experimented with 3 regularizers that we know about. I know only of like a handful of different techniques to regularize latent variables to minimize the information content. The first one comes from, Bayesian theory. Basically, you just make the variables noisy. So the latent variable, instead of being a point, is a distribution, and you try to maximize the entropy of that distribution relative to some prior. It's basically like VAE. Basically, you turn this little loop here into a VAE. The second one, the simplest one, is just quantize the latent variable with a fixed number of discrete options. And then the third category is you make this latent variable sparse. So you put an L1 criterion on it so that most of the components will want to go to 0. But if you're not careful, it's going to collapse. So you need to regularize the variance of each variable so that it doesn't collapse. Okay, so, and there was some previous work from my group on this, but Quentin, came up with a variation of it. And the result is that you get a system. I mean, basically, the best predictions are produced by the sparsity, by the sparsity regularization. So the graph here on the right is sort of prediction error going up, like increasing as you go down on the vertical axis, and then the horizontal axis are the 3 different methods for regularization. Discrete really doesn't work so well. Noisy, which works, but it's not reliable, and sparse, which works the best. And the cool thing about this is that you can use this system to transfer a hidden action from one video to another. So if you have a video where someone walks from the left to the right of the field, and then you have another video where there is a ball throwing in the air. Well, sorry, it's the other way around. Yeah, like from right to left, and then a ball thrown in the air in the other direction, and you transfer the hidden actions inferred from the ball dynamics to the person. The person kind of keeps moving in the same direction as the ball. So there is some sort of semantic information behind this. How much time do I have left? Yeah. So the stuff we're working on now, and you might hear about this, I'm not sure, from Randall later, is, not today, is new methods to train JEPA architectures that are really derived from, I mean, a lot of people have been working on kind of similar methods. This is work from some colleagues at NYU. This is from this is from colleagues at NYU. This is from Berkeley, from Yima's group. And then a bunch of methods that came out of my group, both at Meta and NYU. Barlow twins, VicReg L, SIGReg, which is Randall's work, and then rectified AP-JEPA. The paper came out 2 days ago. And I'm not going to go into the details of this, but the basic idea is that you train a JEPA architecture and you prevent it from collapsing by computing some sort of measure of information content of what comes out of the encoder, and then you minimize the negative of that, okay? So you maximize the information content of whatever comes out of the encoder. Now there's a big catch with that, and the big catch is we have no idea how to measure information content. I mean, we have some idea, they're all wrong. And the only way we can measure information content is upper bounds. We can measure upper bounds on information content that ignore dependencies between variables. But we want to maximize information content, and we only have an upper bound, okay? What we would need would be a lower bound on information content. We can't. We don't know how to compute this. So we take a good upper bound, and we maximize that, and we cross our fingers that the actual information content will follow. So that's the idea of VC regularization, variance covariance regularization, where one way to, like, let's imagine that you run a batch of samples through your encoder, and you collect the matrix of feature vectors coming out of the encoder. Okay, so you get a matrix where the number of rows is number of samples, the number of columns is number of variables. And you have two ways to maximize the information content in a way that is contained in this matrix. One is you make sure every row is different. First, you make sure that the vectors are not zero, okay? But second, you make sure every row is different. The second method is you make sure every column is different. So every variable carries a different information from the other. Okay, so one way of maximizing information in this case is to compute the covariance matrix. So take this matrix, pre-multiply it by its transpose, you get the covariance matrix. If that covariance matrix is the identity, that means you have variables that have unit variance and are uncorrelated. So that's one way of ensuring there is some level of information. Okay, the top one is you compute the gram matrix, basically the matrix of similarities between samples, and you try to make that the identity. And that's contrastive methods, or sample contrastive methods. And it turns out intuitively that this method seems to scale better for high dimension than that one. Although there is some formal equivalence between the two, you can show that the property of that is, depends on the singular values of that matrix, and that, it doesn't matter whether you do the calculation in whether you compute the covariance or the gram matrix, it's kind of the same because they have the same spectral properties. Okay, so you can use some of those methods, but one of the ones that you'll hear more about from Randall is this technique called SIGREG, or LOGEPA, which is the name of the entire approach. And it's the idea that one way to maximize the information content coming out of a system is you get a batch of samples, you run a batch of samples through your neural net, and you're going to try to make sure that the distribution coming out of the encoder is jointly Gaussian and isotropic. Okay? And that's kind of a way of maximizing the entropy, if you want, of the distribution or the information content. Okay, so how you do that? It's a very simple idea, which is that a isotropic Gaussian distribution is one in which every projection of that distribution is a Gaussian. Every marginal for every projection, every direction that you project the distribution along is a Gaussian. If that's the case, then the joint distribution is Gaussian. So what we're going to do is that we're going to get a whole bunch of random directions. We're going to project our distribution against those directions. And we're going to compute to what extent they deviate from a Gaussian, and then get a gradient for every point as to how it should move so that all the distributions become more Gaussian. And that actually works, and there is some cute mathematics that I'm sure Randall will explain to you, and works really well. Although we haven't scaled it up. Okay, I'm going to stop showing you my last slide. So I'm being extremely popular in Silicon Valley right now, which is why I left Meta. Because I tell people to abandon generative models, to abandon probabilistic model in favor of those energy-based paradigm, abandon contrastive methods in favor of those regularized information maximization methods, abandon reinforcement learning. I've been saying this for 15 years. Or only use RL when you don't have a choice. It's a cherry on the cake. And if you're really interested in human-level AI, you should absolutely not work on LLM. You should also join my new company. And so ultimately, I think we will, be able to build sort of hierarchical JEPA models that, can understand the world perhaps as well as we can, and build intelligent systems out of this that are controllable, safe, they can plan, they can reason, they can do everything. Thank you very much.
So thank you very much. And as you said, we will hear from Mido later today and from me on Friday. So we have time for a couple of questions.
Yeah, super inspiring talk. I'm curious how you're thinking about generalizing to multimodality. So when I think of the brain, the action is perhaps coming from proprioception, which is one modality. Can you just plug in other modalities in the actions and condition on that?
Yeah, we've done this. I didn't show experiments on this, but we have examples of this where you get visual perception, but also proprioception of like a robot arm or something like that. And you can have other types of modality. I mean, it's kind of agnostic, really, right? I mean, it's whatever encoder you put. It can digest, the data you throw at it. We are focusing a lot on video, because if you can do video, you can do everything else. I mean, it's the most complex.
Well, you couldn't do VR.
Well, VR is a kind of video. You can reduce VR to video. Russ.
Hi, Jan. So in general, I agree in the overall prediction in latent space makes a lot more sense. But of course, there's a lot of people that are into diffusion models, video diffusion models these days. And I think video prediction is not what it was 10 years ago. It definitely works much better. Or 5 years ago. The predictions are crisp and no longer seem to suffer some of the problems you illustrated before. So for the purposes of this question, I'm just going to play devil's advocate and I'll ask you for ammunition against those people. Like, how do we defend this argument against the people who say, hey, look, I tell my video diffusion model, I condition on the first frame, predict for me what will happen if I do this action. It generates a very, very plausible looking video.
So it's easy to make crisp predictions if you have a very high-dimensional, powerful latent variable, and you're not going to be faced with a collapse problem if you pick this latent variable randomly, because the system has to cope with the fact that it's random, right? So you don't get this collapse problem. So what you get are crisp predictions, but there's absolutely zero guarantee that the system actually is not completely mode collapsed, or actually has any appropriate latent representations of the underlying structure of the world. And I mean, it's clearly the case that diffusion model or energy-based models, which are kind of very related, can handle some level of uncertainty, and they should. Like, I haven't shown experiments there, but in the predictor, you can handle uncertainty also by making the predictor a diffusion model. In fact, the navigation world model example I showed, the predictor is actually a diffusion model. So that's a way of handling non-deterministic behavior at the representation level. But you don't want, kind of to put too much into that, like, at the pixel level. It's not clear at all to me, and I don't think it's clear from the results that we get from video generation system that those systems really understand the underlying physics.
Thanks.
You still get people with 6 fingers.
Hi, thank you for the talk. So my question is, in the papers on SSL encoders, joint embedding ones, you even showed some of them yourself. There are often visualizations or paragraphs on the showing, here's how we can still generate the data representation from the model, or here's how our features nicely correspond to the input image. And do you think that's a useful property for an encoder to have? Or does that mean that we're still kind of too close to the data space?
So there's nothing wrong with separately training a decoder to do some visualization of the embedding space. But it's purely a visualization tool, and it's purely a qualitative evaluation tool. You can't use this for any quantitative evaluation. Like if you start like measuring, L2 distance in, generated images, like you're fooling yourself. So as a visualization tool, yeah, sure, but train it separately.
Okay, we can have one last question.
Does it work? Yeah, okay. So Joshua mentioned the idea of having latent space variables spelled out as in natural language. Do you have any ideas about how you maybe would want in your work to spell out those variables as equations or mathematical expressions, or do you have any idea about interpretability in general?
I mean, I think ultimately this procedure should apply to language as well. It's less, there's less of a demand for language because generative architectures cannot work for language. But the idea that you should learn hierarchical abstract representations for language obviously is true. Like you have to do that. And to some extent, a lot of the scaling issues that are faced with LLMs are due to the fact that there is no such mechanism in traditional LLM. There's no hierarchical representation of, you have to do basically, order n squared attention on an increasingly large context, as opposed to like learning an abstract representation of a long text, which may be way more efficient. I mean, people are working on this as well, but ultimately, I think, Jetpack style architecture would be useful for text.
Thank you.
So we unfortunately have to stop here. We have the panel coming right after, and now we have a small coffee break. So thank again, Jan, for the
Thank you.
Panel, mic 1, panel, mic 1. Mic 2. Est-ce que j'ai un mic 3? Awesome. OK, là, c'est surtout ceux-là. Mic 4, awesome. Micro numéro 5. And microphone number 6. Q&A, mic 7, Q&A, awesome. On n'a plus besoin de se passer les micros maintenant, c'est fait comme ça.
Wow.
I think it's really inspirational, the vision, but I don't know. I'm a little skeptical. Maybe it's the bio-inspired bias.
I've been
But
bio-inspired for my life.
Yeah.
And I think it's the wrong path.
Yeah, I think.
It's the wrong path.
Yeah.
For safety reasons.
Je te laisse faire une annonce. Nice. Okay, let's keep in touch after. Yeah. All right, everyone. So we are going to get ready for the panel discussion now. If you can get back to your seat whenever possible. We will have to fight hard on this one, you know. Oui. Il y a 6 micros, tout le monde a un micro, mais on a un seul micro pour les questions.
Please get seated, everyone. We're going to have our panel starting very soon. Thank you.
But I think everyone knows your name. Good. If you want, you can go here, just in case you want to align with the name. I think everyone should know. All right. So we will now start the panel discussion. So we have roughly 1 hour. So you already heard about almost everyone except Alessandro. So Alessandro Lazaric is an expert in reinforcement learning. And you will hear from him on Friday. Definitely come to his talk. He's been able to do some very interesting work at the intersection of reinforcement learning and world modeling, JEPA. So this will be also a very interesting point during this discussion. So the goal is really to have a discussion between you all, and also everyone should feel free to walk to the microphone. We have only one in the room now, right here. To ask questions or ask for clarifications when needed. But maybe to get started, just wondering if any of you had particular questions about what you've heard today in terms of should you do input space reconstruction, latent space prediction? Is there any modality where you think reconstruction can be okay or not? This seems to be a very big debate, and so this will be interesting to hear what everyone thinks about. I think, Jan, we have a good idea about your opinion, but feel free to reiterate again if you want.
I have a question for Jan. Can I do that?
Go for it.
Just following up on my earlier question. All right, so you mentioned that we humans use an abstract space where we do reason. Totally with you on this. But that abstract space is different for every problem. Sure. And of course, there's overlaps of pieces of it across problems. Now, if you have like the normal neural net architecture of the kind I imagine you guys are building, your latent space, is not 1 million things, it's 1,000 things or whatever, 10,000 maybe, but, right? So the parts of your latent space that's going to be relevant for any particular domain might be very different. So how do you manage that issue?
2 answers to this. So the first thing is the real model you want to build is a hierarchical model where the low levels of the model make predictions that have a lot of details in them, but only make short-term predictions. And then the higher levels. What defines a level of abstraction is the range at which you make the prediction. So the longer range the prediction, the fewer details the system can keep, because you cannot make accurate prediction in the long run, except for a really specific system like Newtonian mechanics. But other than that, the longer term prediction you want to make, the higher level of abstraction. So the way you define the level of abstraction is the horizon that you use to train that level, right? So you get a hierarchical architecture, low level making short-term prediction with a lot of details, and as you go up the layers, fewer and fewer details, but longer term predictions, right? So the right level of prediction of abstraction to describe what goes on in this room right now is, probably at the level of psychology and sociology and things like that, rather than particle physics. That's how so you have to choose your level depending on the type of prediction you want to make, first of all. But then you also probably want to have a world model that is configurable to the situation at hand. And I think that, and so in the diagram that I didn't go into, there's a module called the configurator in my brain-like diagram. And that configurator actually kind of sets the world model for the situation at hand, defines sub-goals and things like that. There is some evidence that humans basically have a single engine for the world model, prefrontal cortex. And the evidence for this is the fact that we can only solve one conscious task at any one time. Right? We can do a lot of subconscious tasks simultaneously. Like we can drive and do other things, right? But if we do a task consciously that requires a world model, we can only do one at any one time, which means we only have one piece of hardware to do it, one engine. And it needs to be configurable for the situation at hand.
Do you have a comment? Oh, sure.
Oh yeah, I had some reaction. So I totally agree with the hierarchical philosophy. I think the challenge is just, for one, where does the supervision for the hierarchies come from? Like the supervision we have is really just the data itself, like the videos or the action information. Another is that even if we can rely on latent variable models and so on to get some kind of hierarchical priors that aligns with how we reason in an abstract space, that I think, like Yosha was saying, that different dynamical systems or even different camera views, like wrist view of the robot versus a third-person view of the robot, have very different, perhaps, latent space or different hierarchies. And if we want to train a more generalist world model, at what hierarchical level do we end up fusing these different hierarchical representations so we can get a single model training diverse domains? It's not super clear, and that was why I was sort of proposing the idea of treating, pixel. I mean, maybe not raw pixels. We will figure out the right tokenization so that we don't have to model extremely high-dimensional tensors. But eventually, it's still in the form of videos is the most natural modalities that all of these dynamical systems eventually result in the data of this kind of form that we can have a unified representation and task interface.
Well, I mean, so first of all, you don't need supervision, right? I mean, the way you define the abstraction level is by the length of the horizon at which you train the system to predict, right? So
are you going to fix that by hand?
Well, so let's take the example. So, okay, let's talk about convolutional nets, right? So convolutional nets, you do have this property that as you go up the layers, because of the pooling and subsampling, you're basically gathering information that is more.
But it's all fixed by
abstract.
hand. We don't want that for the
it's
stuff,
all,
the
it's all done by
abstract
hand.
scientific stuff and so
there
on.
There was a big debate, back in the old days, of people who said doing this pooling and chunking, fixed and by default is never going to work. We're going to have to do segmentation and put pieces of things together and be smart about where we cut objects and blah, blah, blah. That turned out to be completely useless. You can just do, you can just propagate. And in fact, if you have enough data, you don't even need pooling, right?
Okay, but that's not a theoretical answer. It's just people have tried things in the past which didn't work. But I think there are good reasons why we should, when we aim at human level and really capable systems, we should have systems that can reconfigure on the spot and really represent very rich set of abstractions where only a few aspects are relevant in a particular setting.
I agree with that.
I just want to quickly mention that in our current model, we already adaptively put more compute in a much richer systems versus the not so rich system. So it's just adaptively according to how complex the simulations are. But I do have a quick question. I think a little bit aimed at Yasha's talk. I think it's really nice that this scientist AI system that's very unbiased. But I'm curious if you consider training directly from the observational data. Like you will have the ground truth plus the languages.
The ground truth is the observation.
Right. But now you're still using the communication form. You're still using the text.
Yeah. We just want to know what it is that we're observing. Oh, we are observing people writing those words. It doesn't mean that those words are true. Currently, LLM are just like reproducing all the garbage that they're trained on, right? That's not what you want for an AI that's going to take life and death decisions in the future. So you want the AI to understand that it's actually trying to make sense of what people said, and maybe they were motivated, maybe they were trying to sell you something, maybe they were just somebody who is misguided for another reason, and you shouldn't just be trying to reproduce what they do. What you should do is trying to understand why is it that they said those things. So if they say something like the earth is flat, then you don't become more likely to say the earth is flat, but rather to say, oh, there's a reason why people say those things. That's what scientists would do.
So you're still saying that we should do still large language model, but with some kind of unbiased data set?
I wouldn't call it a large language model, just to make Jan happy as well. No, because so one fundamental reason why it's not a large, there are many reasons, but one of them is that you're not trying to just reproduce the observed sequences of words or something like that. The other is that you have a latent variable model, so you're trying to actually figure out what are the latent variables that are relevant in every context that help explain particular pieces of data. Another, of course, is you're trying to be Bayesian and trying to understand the causal structure that explains the data. There are lots of differences, but you can probably use similar architectures. So it's more like how you train it, how you represent the data, what training objective you use, but you can still use SGD on transformers or whatever is going to be, the hip thing in 3 years from now.
So maybe going a little bit more into the JPA dimension. So even if we assume we have a nice training recipe, we know what to disregard or to do the prediction in embedding space without collapsing, we don't really have at pre-training time a way to account for the fact that we do planning at test time and we solve this complicated optimization problem. So I'm just curious, do you think you expect things to become naturally well organized and gradient friendly, or do you think you need better objectives, or how do you reconcile those two things?
No, that's a very interesting question. In fact, a topic on which some people working with me are actively working on. And so the space, the embedding space that is appropriate for dynamical prediction is not necessarily the same space that is appropriate for planning. It's very likely that you can compute the good embedding for planning from the state that is used for prediction. So basically the architecture would be, you have an encoder, you have a predictor that makes the dynamical prediction. It might need quite a lot of details about the state, okay? But then on top of this, you can have a head that computes a smaller dimensional embedding, and you compute the cost function in that space. And that space might be much more regular, much more smooth, much more flat in some ways, so that the gradient-based planning is more efficient. There's no reason for those two spaces to be the same.
That's it. Did you have a question?
Okay. So Franz, from PDOM, we're working on behavior cloning from unlabeled screencasts. So basically, it's sort of a macro question a little bit. So basically, today we've already heard that there are a couple of use cases for world models. One of them being neural simulators, essentially. And specifically for that use case, I'm wondering if you actually want a neural simulator and train agents in the neural simulator, you need the world model to basically accumulating error over a large, long time horizon to be very low. And now the question is, and of course, this accumulating error will get lower and lower with more computer data. And then sort of on a macro level, the question is, if we really want to train agents in world models, how much compute and data do we need, and is this actually feasible? Do you guys have any intuitions or thoughts on that?
The solution to divergence over many steps of prediction is hierarchical models, so that the high levels, can predict with the same time horizon and fewer steps. Okay. So, for example, I'm gonna take a plane back to New York tonight. I don't need to know every detail. It's impossible for me to plan my trip from here to New York in terms of millisecond by millisecond muscle control, right? Because first of all, there's too many steps, but also I just don't have the information. Like, I don't know how long I'm gonna have to wait outside for a taxi to show up or something. Right?
I completely agree with this for look ahead, but for neural simulation as in training agents on them, you can't do that, right? Because you need local fidelity.
I don't understand what you're talking about.
As in, you train a world model, as in, let's say, next frame prediction, next observation prediction, conditioned on actions and past observations, and then you train agents in that world model, like Dreamer, basically. For that, you can't do the hierarchical planning trick, right?
If you have a world model, you don't need to train anything. You just need to plan, right?
Yes.
Training a policy is just a way to accelerate the inference of planning. But you don't need to train. You can solve new problems zero shot.
Just a comment on the accumulation of error, because that's connected to the reward hacking problem. And so I think, it's not really a new idea, but I don't see a lot of papers really focusing on uncertainty estimation as part of what you're learning that's crucial to avoid optimizing for something that's a mirage, that's just made up because of all that accumulated error. So it's not enough to make point predictions. You want somehow to represent the uncertainty around your prediction, and the uncertainty includes the fact that there's aleatoric uncertainty, but also epistemic uncertainty, but also computational uncertainty. Like you train for a finite time, and so your predictions are of lower quality, and somehow all of these sources of uncertainty need to come in to make sure, there will be some sort of error, but you want to know about it so you can take the conservative decisions.
And I guess on a related note of uncertainty and also accumulation of error and also the concept of hierarchy, and also what I said earlier about a lack of supervision for the hierarchy, and what Yosha said about are we going to manually set a horizon. And I think text, in some sense, is a flexible way providing this implicit supervision for some kind of hierarchy, in that even though we have a fixed horizon for how many frames we're predicting, like 20 frames at a time, but we're predicting at very different frame rates when we condition on walking from this side of the room to that side of the room, versus we're talking about walking forward for 1 meter, right? So naturally from text, and we have these labels usually in maybe the videos already, how much this person is walking, and we have a way of automatically generating at very sparse frame rate far into the future to avoid or mitigate at least the accumulation of error problem, while still having a way of naturally learning this hierarchical structure. And on the uncertainty aspect, if the actions are very abstract, like text, ultimately they will have less control over exactly what happens because they're more abstract. There are many ways to walk from one end of the room to the other, but this ties back to what Yosha is saying, is if we have this layer of abstraction of the actions that we can control, then there are many different ways. Maybe we need to simulate many different outcomes and have these models of consequences and judge these different rollouts, different ways of accomplishing this high-level abstract action. So that's kind of my reaction to the question.
Text is a crutch, though, in the sense that it's a good engineering shortcut for a lot of tasks that are sort of relevant to humans because we can express them as text. But like animals don't use text, and they can do hierarchical planning, and they have world models that are much better than any artificial world model that we have at the moment, right? A house cat has 860 million neurons and can do amazing feats and can certainly do hierarchical planning. No text.
Maybe one aspect about the hierarchical part, which I think probably requires a little bit more thinking, is the fact that when we abstract, we can abstract representation, we can abstract time, but then we also have to have a reliable guess about what's going to happen on the low level, right? So there is some primitive control that happens at the low level that should be as reliable and predictable as possible, because if it's messy and non-predictable, then this breaks all the levels of the construction of the hierarchy. So when we say I go to the airport, it's because I have a reasonable guess that I will know how to do it and manage all the contingencies of this high-level task, and how to find the proper primitives at each level of the abstraction so that we can build reliably the hierarchy. I think it's not so clear. I think it's still a difficult.
I mean, it's the deep learning problem, right? I mean, the question of what, abstract multi-level representations to learn.
I think here
is the problem that deep learning has been addressing for a number of
I'm
years.
just adding the control part.
Well, so what I was going to say is that the problem we're facing now is that instead of being able to learn hierarchical representations for perception, we need to learn hierarchical representation for action control.
Yeah, but the question is, if I say I go from, let's say, hierarchy level 2 state to another one, what is the activity that I'm doing? What is the primitive action at that level? And there might be many. And how do I learn what are the core components of this second level?
Ideally, you want that to emerge from the training, right?
Yeah.
And so maybe just going on the hierarchy again. So as you mentioned, right, when you have a deep network like a ConvNet or a ResNet, you explicitly have those pooling operation, subsampling. And so this emerges, although you have only one training objective at the end. But in the diagrams that you showed, you had those different sort of JPA blocks. So in your settings, do you think hierarchy needs to be explicit extra terms you have in your loss, or you think it should be at the architecture level and it will emerge from one final loss only?
We need a prediction error and a regularizer for every stage. And then there's a question of, we were just talking about this in the context of a question, of like, what is the granularity of a stage in a hierarchy? Is it just one layer of a neural net, or is it like a bunch? I mean, currently, most of the JPAs we've trained are actually quite deep, because ultimately we use benchmarks to measure the performance in terms of like semantic tasks in action recognition or something like that. So our networks are super deep, but what we want to do is basically have a pretty fine-grained hierarchy.
Just another point, I'm curious to hear your opinion about that. So when we say that the representation should refine one each other because I abstract away further details, in some cases we can observe that actually it's just complementary and not refinement. In the sense of, for instance, if I have to move, my war model for movement is probably ignoring a lot of the things that surround me, whereas if I have to define a war model to go from one place to the room to the other one, probably I'm considering other set of variables. So it doesn't seem necessarily like a one-way abstraction. It seems like every level, which might be temporally hierarchical, the level of details are not necessarily one, the refinement of the other. So they might just take different parts of the state in a sense.
Hi, my name is Stefan from Skyfall AI. First of all, thank you very much for the very interesting talk today. I had a couple of questions on causality, which I think everyone agrees on is very important. Joshua, you talked about it most explicitly. One thing that I think is really interesting about causality is interventions, and I think that's how humans really learn causal models very quickly. However, you explicitly don't want the model to be able to pick those interventions.
I didn't say that. No, because I talked about the core predictor, which is non-agentic, so
yes.
The predictions are not biased by some goal. But once you have it, you can turn it into agentic questions. Just you can ask, what is the action that's going to give me this outcome. Of course, you have to be careful, but the problem you want to avoid is that it's not the human setting some goals. The problem is the AI having some hidden goals that you didn't choose. That's what I'm trying to eliminate.
Yes, I think that makes a lot of sense, and I appreciate the clarification there. I was just wondering, how do you select the data? If you don't want it to be able to select the data, because that would make it agentic in some sense.
No. So this is a solved problem, at least theoretically, and is used in experimental design, in scientific discovery. For example, I worked in drug discovery. So you can use your Bayesian predictor to train, if you want, another network that estimates some information gain, which is a mutual information. And then you can optimize your policy towards maximizing that information gain. Like which action is going to give you more information to disambiguate your lack of knowledge of the world. It's not sufficient to do that. You want to make sure the action also is not to create some harm, but that can be part of the objective. And there are more complications, but that's what I meant when I said once you have a non-agentic predictor, that's Bayesian and causal, you can use it as a building block for agentic systems, but you have to do it carefully because all of the problems that we know.
Thank you. That's very helpful for clarification. And I had a second question for Jan. You, on your last slide, talked about causal, that you hopefully, VJEPA can learn this causal model of the world. And I was just wondering if you had any more insights on how JEPA would create those causal connections.
Well, the case that we've used, it doesn't create it. It's just fed, state, action, next state. That's a causal model. But it doesn't do any causal inference or anything. It's just given the variable set that you can act upon. Now there is the last model I talked about where you infer the action. You might be inferring actions that are not there, right? And humans are fooled by this too, right? Like if you ask a 4-year-old, what is the cause of wind? Like half of 4-year-olds will answer, it's caused by the motion of the leaves in the trees. Okay, and they get the causality backwards. And humans, for thousands of generations have attributed causes to all kinds of natural events. And like, if we were perfect at causal inference, religion would not exist.
But it doesn't mean we shouldn't have causal components in AIs. It just means that humans have, reasoning models that suck. And sometimes you care about interventions in a place where there is no way you can have an action. So I can imagine what would happen if some, titan were to move the sun around, even though, of course, I've never experienced that. I could never do it, but I can still imagine it. And this is something that if you limit your interventions to the actions of an agent like a robot, you couldn't do. We can do that. And we can do other things that go beyond interventions, called counterfactuals. Like, what would have happened if? That's another thing that you can't do if you just have this action and past observation to next observation or state to next state.
You can absolutely do it. Of course you can. Like if you have a war model that makes good predictions, you can absolutely predict what would have happened if you had taken the different actions that you did not.
Everything else being equal, including all the randomness in the world.
Within limits.
Judges ask this question all the time, by the way.
Thank you.
Yeah, I actually had a question for Joshua and Jan on the related note of learning latent actions from actionless videos, for example. And Joshua was mentioning that there is this not confounding, but in between two frames, in between two observations, two things happen. Action happened and some environment dynamics transition happened. One is controllable by the agent, the other is not. So when we just try to learn some kind of extracting latent actions from the difference between the two observations, how do we actually distinguish which ones are controllable, which ones are not? And if we just boldly optimize those, wouldn't we run into the problem that Joshua is describing?
No, I mean, we don't know how to do this, right? We don't know how to make a clear difference between latent variables and actions. Whatever complementary information is necessary to make a prediction It could be a variable that you can influence, or it could be a latent variable that you're not observing that explains if the world is deterministic but not fully observable. But it could be also that the world is just not deterministic, right? So, yeah, but again, as humans, we very often make the confusion between the two, and we attribute causes to things that don't really have one.
But it'd be great to have AIs that do figure out the difference, and that means they have a good causal model. So somehow that needs to be represented. Now, maybe it comes out implicitly, maybe it's something that the AI can actually verbalize about, which is what I've been talking about. I don't know what is right, but it's good to explore.
Yeah, that's kind of like why I believe in explicit action labels in the data, so we can actually learn pi of A given S, and then T of S prime given SA separately, and control only the part we could control.
Obviously, if you can get that data, you should do that.
But still, there are a lot of problems where you care about the things that you don't control, right? So I think there is still this indecision making.
You still need to model them.
Sorry?
You still need to model them.
Exactly. So I think there is, what we control and we care about, what we don't control and we don't care about, what we don't control but we care about. And I don't think that from completely passive data we can distinguish among them. With active data we can probably disentangle a little bit, but ultimately it also depends on the task that we want to solve. Autonomous driving, I think, is a very good example. Right? There is a part that I control, there is a part that I don't control, which are the other cars, and then there are the leaves that move that I don't control, don't care.
Hello, I'm Man Ren from NYU, and I'd like to continue asking a question on the abstraction and the hierarchy part. So I was just curious, do you think, the latent predictive loss, predicting the embedding loss is all we need for achieve the level of abstraction, or is there any other, potential missing ingredients that you feel like are promising for the researchers here to explore? For example, in the past, we've also tried to add multiple hierarchical laws across the layers, but the gain seems to be very minimal compared to just having one single global latent loss, predictive loss on the top. So it seems like pushing deeper layers and having more like these such laws doesn't give as much of a jump in the terms of the abstraction that we're looking for. So I just tried to be curious what your potential thoughts on abstraction.
I don't pretend to know the answer to this because I don't think there is enough. There's been enough work on hierarchical models done right. There's been hierarchical models that just haven't been done completely right. And I know you've done some work on this, but it's not clear to me what the correct answer is. I think there is a bias that there's 2 points. One is we're biased towards learning high-level representations because all of our benchmarks are basically semantic tasks. And so when we measure the performance of our systems on some downstream tasks by training a supervised head on top of the representation, it's always a high-level task, right? So obviously we're going to have an advantage in learning high-level representations as opposed to low-level ones. Maybe when our benchmarks change, that something like visual servoing or something like this, there you need like really fine-grained representations and low-level control. Maybe that would be different. But ultimately, I think you want like a separate loss function for every layer. And then the second point is that we're probably going to have to engineer various objective functions to drive the system to learn the type of representations that we want, like bias it to learning representations that we want and pay attention to the kind of features that we want them to pay attention to. I don't think we're just going to get away with completely generic information maximization criteria.
I just want to add about hierarchy. For most of my career, I've made the mistake, I think, to think of hierarchy, especially in the early days of deep learning, 20 years ago, to think of hierarchy as being captured by the layers in a neural net. That's how deep learning started. It was very strong in my mind. Oh yes, we have a hierarchy of abstractions and blah blah blah.
I think was a mistake. If you think about the kind of hierarchy that humans construct to understand the world, it's not fixed. It doesn't map to a fixed architecture with like 10 layers or 20 or 100. It's something we construct as we build an understanding of the world, and maybe somebody tells us and we don't even like retrain our neural net completely. It's just, oh, I didn't think about this way of abstracting. So I think we should think of abstraction as something indirect that is not like just hard-coded in the architecture.
Yeah, I had some thoughts on that too, where Jan said, okay, animals don't use text. So I think naturally the hierarchy arises from data when we have some kind of labels. Let's say if we can scan all of the animals of their brains activities of when they move, how did their brain change to control all of the muscles, then we actually have a way to control these animals. We can train a generative model, condition on these brain scans, right? We can change how their brain scans move, like activate these neurons in their brain scans. And then because we have this data of all of the scans for all of the animals, I don't know, we plan some kind of brain monitoring in there. It's not very, very nice, but we can get that data. And then as a result, we actually have a way, an actual representation that we can use to predict the observations and also have the policies to plan at this level of abstraction where we have some data for. Because we don't have that data for scans of animals, we don't have that data for human brains. But maybe in the future, yeah, like when we do have a lot of data, like enabling human to just think of things and then being able to control things, this kind of human brain and machine robot interaction, I think is possible if we can gather such data. Right now, we just have text data, so...
No, but there's a solution. It's called latent variables. I mean, the whole point of having latent representations is to avoid requiring somebody to tell you what the hidden units or the abstractions, whatever you want to call them, have to be. That's the whole point. We don't need that. I mean, of course, if we had it, it'd be nice and it'd be easier to learn, but we don't have it. And we're not going to get it, by the way.
People are actually collecting the data you're talking about.
Yeah, but not at the level that she needs.
Well, it depends which animal. I mean, you can do it with small animals. Or like zebrafish, they're transparent, and yeah. So you can hack their neurons so that they fluoresce when they fire. So you can pretty much get a picture of like all the activity. Of course, in humans, you can only do MRI or MEG, which is not nearly as.
But the point is, humans don't need it. Like we construct abstractions without labeled data on these abstractions. This is one of the beautiful things of the human mind.
So maybe I have a quick question on what you just said with abstraction going through the layer. So there is one thing...
Not through the layer.
Yes, so I have a question on this. So we know in terms of information, right, as you go through the layers, you cannot add information. You either have as much or you reduce it. But what we care about is not really information as this abstract quantity that we don't even know to estimate anyway, but more what can we use for a downstream task, whether it's linear probing, gradient-based planning. And so when we had those convolutional networks, for example, we said, okay, we can disregard, let's say, spatial information because what we care about is not really sensitive to that. So we simplify the way we probe and extract information from the last embedding. And so I'm wondering, when we speak about abstraction, or just what information content we have, it should really be with respect to how you want to use this post-training. And I'm wondering if you have a way to either measure that, or what do you think is the right way to speak about useful abstraction?
So you don't need post-training, or you don't need like a task. You have the data that you observed, and you want good abstractions to make sense of that. That is what science does before it starts doing experiments. It just tries to make sense of the data you observe, and it looks for abstractions that are compact and like scientific regularities and laws that give you that. That's it, and you don't. Of course, depending on the kind of data you collect, there might be different abstractions that are most emerging from the data. Like before we had microscopes, there were lots of abstractions that we didn't even think about because we didn't have the data that revealed, the need for these abstractions.
Hi, my name is Sergio from Brown. My question is for Jan LeCun, and regards to how you answered a previous question. So when I look at humans and how essentially the pillars of behavior for like humans, when I see essentially you have like learning from demonstrations, right? So something like imitation learning. You have learning from trial and error, so something like reinforcement learning. And then you have, you know, world models and planning, right? Those are like kind of the three things I've identified that like how humans tend to act in the world. In a previous question, you said if you have a world model, like why would you learn? Do you see value in things like imitation learning and reinforcement learning?
Yeah, sure. I mean, first of all, there's a lot of species that don't do imitation learning at all, and they get really smart really quick. Good example is octopus. They only live a year or two. Most of them don't, actually, but a few of them get to adulthood. They never meet their parents. And they're not social animals, so they don't learn from each other much. But they get really smart very quick. So obviously it's possible. I mean, it's true also of, you know, cuckoo birds and things like that. They never meet their parents. So imitation learning is certainly useful for humans because we're a social animal. And mammals, so we raise our kids. But it's not necessary. A lot of animals can do with that. So that's the first point. Second point is reinforcement learning is a cherry on the cake. So it's much better to do reinforcement learning with a world model, in the sense that if you use reinforcement learning, like model-free reinforcement learning, to train a car to drive itself, and the car drives next to a cliff, and the car doesn't know that by veering to the right, it's going to run off the cliff, and it doesn't know what's going to happen after it runs off the cliff. So it's going to try this, right? It's going to have to try this thousands of times before it figures out it's a bad idea to run off that particular cliff. And then when it meets another cliff, it's going to have to learn again. And so it's impossible to train a car to drive itself model-free using reinforcement learning. There are people, 15 years ago who believed that was possible. Built entire companies around it. Bought entire companies for hundreds of millions around this idea. Complete failure, right? You work for it. They changed their mind since then. So that can only be like the last, cherry on the cake that sort of, allows you to adjust. But there is one way that reinforcement learning can be used, which is that the cost function you use for planning needs to be trained. And so it's like learning a value function, right? And that's part of reinforcement learning, if you want. It doesn't have necessarily to use all the techniques that reinforcement learning is using, but like a big chunk of reinforcement learning at the moment for LLM is learn a reward model. That's what a reward model is. It's a cost function for a particular task, but if you have a reward model, you can use it for planning, which LLMs don't do. They just use it, their so-called reward model is just a proxy for the cost function you don't know, so you have an approximation of it that you can backpropagate gradient through. That's what it is. So, yeah, I'm not sure I answered the question, but.
Yeah, one thing I really can't reconcile with something like MPC using cross-entropy method or MPPI is typically you need on the order of thousands of concurrent simulations, and so that's hardly real-time reactive policies, right? You're assuming quasi-static motion at that point if you want to do object manipulation.
Okay, I think there is a stack this high of techniques that need to be worked on to make NPC with complex learned world model more efficient. So the first one is hierarchy. So if you do hierarchy, you don't have to plan thousands of actions. You can plan 2 or 3 actions, right? So the example of flying back to New York, I can do a high-level plan which has 2 actions: going to the airport, catch a plane. Okay, now I have a sub-goal, being at the airport. 2 actions: getting out of this building, catching a taxi. Okay, now how do I get out of this building, right? Walk to the door, walk out, etc. And then at some point, you get low level in the hierarchy that you don't need to plan, you don't need to use a world model. Like to stand up from my chair, I don't need to plan much. It's a task that I've done many times. It's become system one. I can just use a policy, not my world model. So that's how you make this efficient. You make, first of all, hierarchical planning. And then when you get down to a particular level where you get down to a task that you're really familiar with, you just use system one and just a policy and no planning. Then the second thing is using the so-called cross-entropy method, which is just a particularly stupid way of doing ensemble-based method, gradient-free ensemble-based optimization method. The reason why many of us use this is because it's slow, but it works, and it's not the problem we're interested in at the moment. We just want a thing that gives us a good plan, and we know it sucks. Okay? Some of us in this room, Umaima, where's Umaima? Right here, is working on gradient-based planning, because obviously everything is differentiable. Why not use gradient-based optimization, right? Now there's local minima issue, there's all kinds of issues, but there is, again, a stack of ideas like this thick to try to make this more efficient. And then there is the problem of what makes planning inefficient is that you really want to plan to the end of the episode, but in practice you can never do this, right? So one solution is hierarchical planning that I was telling, but another solution is a value function that allows you to do partial planning. So how do you train a value function efficiently? So anyway, there is space for a dozen PhDs for 5 years to work on this.
Cool, thank you.
Just a point on the generalization part, because I think that's also quite interesting. So why a policy should generalize worse than a word model? In the example you were providing, if I go on the right, I go off the cliff, a policy would be able to generalize to some extent. A word model would still need to see a lot of cliffs to be able to know that that cliff, if I turn on the right, this is what happens. So there is a level of generality that needs to be supported by data. And just another aspect is that it's true that probably there are things that are intrinsically more generalizable because they are short-term, one-step type of word models. But one-step word models, they have error accumulation. And on the other hand, if I do abstraction, then again, they have the same issue as a policy, in the sense that the policy, it's learned by having seen the long-term consequences of one action, and the same for a multi-step word model. It needs to know what's the long-term effect.
So there's a fundamental answer to your question. It's called system 2. Okay, the reason why we have system 2 is because we can't train a system 1 thing that will learn everything, every situation, but we can train a world model. Okay, and once we have a world model, we can do runtime optimization for a situation that our current system 1 hasn't been trained well for, and so it would suck.
But from a machine learning point of view, so world model, it still requires samples, right?
No, but the world model is much simpler than having to do the inference for every possible situation.
Two things. I totally agree with Joshua. A policy is task specific, right? You're going to have to learn different policies for different tasks. So you're going to need more data, right? And in fact, that's what everybody is doing at the moment, right? The best robotic system at the moment use things like diffusion policies, and they require tons of imitation data or teleoperation data or whatever to be able to do anything significant. Which is why I've been saying, I got a lot of heat for this on Twitter, but I've been saying, all of those robotics companies that are, building robots, absolutely none of them has any idea how to make those robots smart enough to be useful. Because they're all, hoping, crossing their fingers that the sample efficiency of training those robots will get better, and that the number of, useful tasks that those robots can be used for is going to be wider than the current one. Currently you need a lot of data to train a robot to do any particular task, and it's brittle, and it doesn't generalize a lot. It generalizes a bit, obviously, but not a lot. So as Joshua said, if you have, so first of all, a world model does not need to be task specific. It can be learned through observation, mostly, if you can observe or infer actions. You don't have to actually act in the world to learn a world model. You just have to observe state, action, next state. And if you don't observe the action, you can infer it So that means you have tons of data that you can use to train your world model, which does not require actually having an interaction in a real environment or in a simulated environment.
But then it's because you're taking the online RL part. So online RL, I think we all agree in the sense that I really need one task and I really need to optimize, and I need to, for even just one thing, I need a lot of simple.
It is model-based RL in a way that Jan is talking about. That's very different.
No, but what I'm saying is that the S prime data, once you give me a task, I can label it with a reward, and I can do offline RL without even interaction. So I can still compute optimal policies or good approximations without interaction. So.
Yeah, I thought about that question. So, for a while there was this tension between model free, model based, and it seems like for a while model free was really dominating. Everyone is working on policy gradient, Q-learning, and then, I even remember reading Rich Sutton writing articles and books on how it is much simpler to learn an optimal policy than to learn the dynamics model of a complex dynamical system. But then I think I finally get why he said what he said, because in a single task setting, if we're thinking, it could be true that learning the optimal policy in a model-free way is simpler than having to learn a dynamics model. But like what Joshua and Jan's already saying, we're in a domain where we're no longer concerned with single task. We did single task for AlphaGo or for local Majoko for these model-free methods. But the situation we're in now is many different tasks, many different policies trained for under different reward functions for different reasons, but we all live in the same world governed by the same set of physical laws.
No, I mean, we are in a war model workshop, so I think
we have the audience with us.
Randall invited me to be the RL guy, so I'm trying to play that role. What I'm saying is that, for instance, if I train a goal-based RL policy from offline data, not even a single interaction.
Goal conditioned.
Goal condition, yeah, goal condition policy. Then I have a fairly generalist policy that would generalize.
No. There's a fundamental mathematical property that inference is exponentially, if you want to do exact inference, it's easy to show. Inference is generally much more complex. The number of bits you need to represent the inference function is exponentially more than the number of bits you need to represent a model. So if you had a model of anything in the world, and you ask yourself, now I want to be able to answer any question, like what do I do in order to get to this point? The number of bits you need to represent that function, that inference function, is exponentially larger than the number of bits you needed for the model itself. Now, of course, if you see enough, you might get some good generalization, but then you'll end up with out of distribution generalization, you're going to end up with new cases, and that is where you need to do things online, exactly, on the fly, just system 2. That's what Jan was talking about.
But this is exactly what happens when I enroll models. I go out of distribution because of their accumulation. Even when I plan with models.
Okay, but that's a second order problem, which is your model sucks because now it's out of its region, and that's why you need to be causal, by the way. But yes,
it's just saying that
all the problems.
I agree on this on the statement that learning a war model is simple complexity-wise than learning a set of policies.
That's right.
So I agree.
But even in the goal condition case, it doesn't solve the problem.
But if we then add the end goal, which is eventually I want to optimize for something at that time.
It doesn't change the statement I made earlier. If you were to write the computation that is needed, it's very, very big.
Yeah.
Even if you input the goal that you want as an input to that huge neural net.
Well, it's what I'm saying is the computation that you need for a war model.
No, but if the computation you need to specify the right policy is exponentially large, that means you need exponentially large data sets. And that's the sample efficiency problem of standard model-free RL.
For behavior cloning, yes. For RL, not.
To rephrase what Joshua is saying, there is the inference process for planning produces an output by optimization, right? By searching for a sequence of actions that optimize a function. That's potentially unlimited in terms of the time it takes and the amount of computation it requires. It's computationally extremely powerful. But you can reduce any computational problem to an optimization problem. You cannot reduce any computational problem to a feed-forward propagation to a policy network with a fixed number of layers, right? There is a lot of functions you're not going to be able to implement this way.
But again, I'm making a statistical statement. So infinite compute, that's fine. Still, apart from the feasibility of the optimization phase, the error accumulation that happens, it's a statistical argument in the sense I trained a world model on a lot of data, but I haven't seen everything. And as soon as I do the optimization part, infinite compute, I will go out of distribution.
No, that is why we're talking about uncertainty estimation as part of the world model. If you don't do that, you're going to get screwed at some point.
Right.
Also, why you need a hierarchy?
If I can ask my question. So my question is, I have two questions. The first is, how do you view the differentiation of the world model depending on which task you are trying to solve? So it seems to me like, for example, AlphaFold is working very differently from current coding LLM, which is working very differently from AlphaGo. And it's not obvious to me that those do not have like some kind of world model because it's kind of ill-defined in my opinion. So I'm curious about how you view the differentiation. And also, it's more a question for Ian, but you really want to build robots, but for example, it seems to me like current coding agents like Claude and that kind of stuff, they seem to be pretty good and becoming better and better at computer use, and I would not be surprised that they become like superhuman at this. And from the literature, it's not obvious that they don't have a kind of world model because they're able to answer to questions, understanding human, like manipulating code at the superhuman level. So I'm curious about your opinion.
Well, so, Anthropic is not publishing anything. So they're not telling how the systems are working. So we can only guess. There are people who are producing code production systems that have world models. In fact, there was a paper by my former colleague, Gabriel Sinev, and his team at Fair Paris called CWM, Code World Model. And so what is a world model in the context of code? If the state of a program is entirely determined by the state of the variables, the value of the variables, and the call stack, right? And a program is Markovian, deterministic, right? First order Markovian in that state. It completely defines the state of the program. Now, an instruction is like an action. Can you predict the next state of the program resulting from an instruction? Right?
So you are saying we could build a LLM that behave more like a world model, but my question was more, how much do you think current model, like let's say Claude Opus, they have some kind of world model?
I don't know,
okay.
But they could be using similar to what the Code World Model. So the reason why Code World Model works in that context is because the space of code is, well captured by discrete tokens. And so you can use an LLM to basically, here is a description of the state of the variables, here is the description of instruction, tokenize, predict the next state. You can do that, right? And you could use this for planning too. In fact, that's what they do in that paper. I think ultimately you want a JEPA version of this because you don't want abstract representations of the state of variables. For example, if you have, an array with 1 million numbers in it, you don't want to be storing the 1 million numbers in the context, right? You just want to say this array is sorted or not, right? You don't want to be, you want an abstract representation of the content of those variables. So ultimately you want to use JEPA, but that's not what they've done so far. Now the more interesting question is, if you just train a regular LLM, does it have an implicit world model of what happens in code or in something else?
That was my
right, and the answer is probably not. Like not to the extent that you can use it as a world model because there is no distinct, clear distinction between state and actions. If you want to use it for planning, you need a separate notion of what an action is. And it's not clear you have it if you just train on it.
You do, because natural language allows you to say, oh, if I do this, then what will be the output of this program? So you definitely can represent actions.
Right, and that's kind of what they do in the Code World Model. They have like special markers to kind of, make the boundary between stuff. So maybe implicitly it can do this, but that only works in sort of discrete spaces with LLMs. If you are in an environment that is, highly dimensional, continuous, noisy, you're not going to do it with that. And then there's a question of planning. So it's clear that a lot of code generation systems use some form of reasoning or planning, but the way they do it mostly is, first of all, they do it during training to kind of generate code and then verify which one work. And you do RLEF, right, reinforcement learning through execution feedback, to adjust the system automatically. That's how they get so good. And then at runtime, you just get the system to generate lots of different programs, and you have some other LLM that chooses which one looks best. And since that, run that one, and if it doesn't run properly, you can try another one. And so that's a very primitive form of search through a set of actions. It would be much better done in abstract representation space than in token space. But right now, the extension of LLM to get them to reason is generation of lots of token sequences and then selection of a token sequence that is best according to some evaluation function. It's very similar to the way game playing systems work, right? You have a tree of possible moves. You try multiple moves with some heuristic, with a neural net that predicts which moves you should try. And then you have some value function that evaluates what the endpoint is, and you pick that move. So it's like MCTS or tree exploration and stuff like that. It's very similar. But it's a very primitive form of reasoning. And by the way, this is a form of reasoning that humans totally suck at. Like, we're terrible at tree exploration, right? Because you can buy a $30 gadget that will beat you at chess, certainly beat me. So what that means is that tree exploration is something that computers are particularly good at. And if you can reduce kind of programming to sort of this type of reasoning, automatic programming will get better than humans. One interesting point I want to make too is that there are at least two domains in which the language itself has sufficiently strong structure that reasoning in the language space actually makes sense. One is code, the other one is mathematics. So mathematics, we all know this if we do math, right? Writing a bunch of symbols on the page and doing derivation actually kind of produces stuff that we did not necessarily think of ahead of time, right?
So just to jump on that, because that's exactly why I was asking the question. Would it be possible that in the future, GPA do not have a significant competitive advantage in those space? Like, it would work like as a robot way better than an LLM. I really believe that too, but I don't see why it would be necessarily better in those domains.
Because I think for like the design of a software system, for example, you need to think in an abstract representation space. You're not going to do it in token space, right? You think in terms of like complex data structures and like macro big functionalities that transform one thing into another. Like, you don't think in terms of individual instructions, right? So
tokens can be abstract as well. I mean, for example, these systems are trained not just on the code, but the comments that people put, which have a lot of abstractions in them.
I just want to come in with a slightly related question to this. Is we talked about a world model that is this all-encompassing, can do everything, just all the planning, this action, and state. But then we talk about code world model that does one thing. So I'm curious, even with the audience, like, what do you think is the definition of world model? Does it have to be really can do a lot of generalized task, any task? Can it specialize to do one thing? And as a scientist, I'm kind of surprised that people aren't super excited to take all the sensor data. It's mostly still text. So just throwing it out there to see reactions.
Well, the entire purpose of this new company I'm building, Labs, is AI for the real world. So basically dealing with sensor data, not just video, but like any kind of high-dimensional continuous noisy sensors. That's completely orthogonal to what LLMs can do. LLMs totally suck at this kind of data. So, yeah.
So, in defense of LLMs, I mean, I've said bad things about them. No, but I think we have to be fair. The leaders of the companies that are building those LLMs, it's very clear that they have a plan to use their, I mean, I wouldn't even call them LLMs anymore because they're agents, so it's a misnomer. But whatever, they use the systems with the current recipe for frontier models to do programming, math, and then to graduate to machine learning research. And so they think that machine learning research is sort of an extension of programming and math that will open the door to solving other problems in AI. So they think that, and I don't know if this is correct, but they think that this symbolic space where language is appropriate for math and programming will extend to research questions of the kind that human researchers do when they do research in AI. And then that will unlock all the things that they don't know how to do with like robots and so on. I don't know if that's going to work, but that's clearly what they have in mind.
I bid them good luck.
I just want to know, people should know, it's reported, I think they're going to release the AI research intern this summer from one of these frontier labs. It's on the news.
My answer to like what really is a world model, I mean, the definition is in the equation. It's a model of future observations conditioned on past observations and some actions, right? But then the real question is, what are these observations and what should we be modeling? And I think from my talk today about robots, and I think for a lot of code domains as well, and as well as machine learning engineering, where I think nowadays people are going to use LLMs for very long-running agents, like the agent, whether it's extended reasoning, whether it's ML engineering, whether it's coding that takes hours to go into some obscure code base. And all of this, if we do the things that people are doing it, which is online interaction, using online RL to train these models, that's going to be extremely expensive. And so the role of world models is there to save us time as an intermediary between any agent, between agents and the real world, so that the agents can still interact with the real world when they want to, and then the data come back not just to train the better agent, but to train a predictive model of the future observations. And what can we do with that? Well, we can predict losses for training machine learning models if we have a lot of data, so that we don't have to run the model to know that, okay, ResNet with only 10 layers is going to be worse than ResNet with 50 layers. And we can train models of not just performance, but also models of cost. How long is it going to take to run this action versus some of the other action, which I think is a problem that hasn't really been studied as much in RL, because the MDP formulation doesn't really take into account of the amount of time it takes to execute actions, which I think are extremely important. And if we don't have a world model, some actions are going to take a really long time, some are going to take a very short time. How do we do optimization? It's really not clear. But the point is just, if we have a world model of not just the outcome, but also like the time it takes to acquire these outcomes, the agent can make more smart decisions about, should I try this action that's going to take 2 days versus this action that's going to take two hours, right? So I think a world model provides a lot of richer information for agents to make a lot more smart decisions while having low cost, whether the cost is, for robots, it's physical cost, which is extremely high, and now it's like a learned model, it's lower. But even for virtual settings where things do take a very long time, world models allows us to have this temporally abstracted prediction that allows us to make better optimizations for the actions.
I think, so this is a great concluding
one more
remark,
question.
so thank you.
One more question.
So unfortunately we have to move on.
Be on last time too.
I also wish we could hold this longer, but unfortunately some of them have to leave. Feel free to try to catch them up offline, but we have to move to the next part of the program. Sorry about it. So, yeah, great. So thank again to the panel for the great discussion. And we will now have Mido presenting. Why? I can do that. Because after it's just poster, no? Okay. Oh, we need to leave the room? Yeah. So it would be better if you okay. No, we are the last stuff. I know. Okay.
There's a lot of where we always have a lot of conversation that would have happened without me.
Don't go too far, guys. We're ready for our next talk. Thank you.
I feel better. I mean, I'll take it. It's easy to break a nail. It's really dry. Totally.
All right, everyone. So we are gonna move to the last talk of the day by Mido. So if we can find back our seats. All right, thank you. So very happy to have Mido here present about VJPA 2. Yes, VJPA 2. So you heard a little bit about JPA before in Jan talk. So of course, the question you might all wonder is, okay, but how do you train it in practice? How do you reach those state-of-the-art results? So now I am very lightly putting this pressure on Mido to tell us how to do that, how to train those JPAs effectively, and to let us know what are the gotchas of VJPA 2 and maybe VJPA 3 soon. So thanks, Mido. Do you want this? Or?
Is it this one? Maybe this one. Yeah. Okay. Hello. So I'll get started talking about VJPA 2. Thanks for the intro, Randall. Yeah, I always preface this by saying, I actually started working with Jan a few years ago during my PhD. And, Jan did not push us to work on JPA. It was very much a natural course. We were working on other methods for self-supervised learning from visual data. And we all felt the methods were a bit limited. They had kind of very specific inductive biases that limited generalization to images and so on. And so it was really kind of a natural journey. And so, I just want to debias the talk a little bit. And so this talk is about world modeling, similar in theme to lots of the other talks you've seen. But one of the differences in this talk is we actually use the world model for closed loop planning on a robot. And this is the area of research we wish to continue building on. So it's really kind of a first stab at it, a proof of concept. Being hands-on, I can tell you I was surprised that it worked much better than what I was expecting. And so I think it's quite promising, this line of research in general, to continue building on it because it's really just the start. And VJPA 2 is it's a paper. We also release code and models last year, and it's a large group effort with many collaborators from FAIR, but also Mila, actually. And also just to say, thank you to Nicolas. These slides are adapted from Nicolas Ballas and Artem Jolis before that, who's a student at Mila. So I'll start with a motivating example. So here you have a crow trying to get some food from a tube, and it's suspended in some water. So at first the crow can't reach it, so the crow goes and takes a pebble, places it in the tube. That causes displacement of the water level to rise, and so now the crow can reach the food. So there's a lot of really interesting capabilities here. And I really like these kinds of examples. I'll borrow a term from Jeanette Balk. She refers to these kinds of tasks and capabilities, such as the lockbox, as creative physical reasoning. And so creative physical reasoning, those are the kinds of tasks that I think would be quite exciting to try and tackle and go after with something like a world model. And so how do you enable this kind of reasoning and planning? Well, obviously in theme with the workshop is the world model hypothesis. So the hypothesis is that the crow, and I'm going a bit fast just to save some time, but the hypothesis is that the crow might have a world model and might plan sequences of actions to achieve the goal, right? So clearly there's some basic understanding of physics, the fact that the crow takes the pebble, places it in the water, causes the water level to rise, and that's going to make it achieve its goal. So that's quite remarkable. And so now one thing that we talked about a lot during this workshop is, well, what representation space do you plan in? And so the hypothesis we take in this work is we should plan not in pixel space, but we should learn a visual or a latent representation space, and that's the space that we should do planning in. Okay, and why not pixels? Well, modeling distributions in high-dimensional spaces is difficult. So here, I mean, Sora is now a bit old, but I'll just show an example of video generation from Sora. You see these kinds of physical inconsistencies, and this is already quite a big step from where we were a year ago or 2 years ago. Right, and these models are continuing to improve. I won't get too much into this, but Nicolas Ballas, one of the collaborators on this paper, actually has an effort where they used VJPA 2 as a reward signal for video generation models to improve physical grounding. And so I think this won the CVPR, won a challenge at CVPR, actually. And so the first thing is modeling distributions in high-dimensional spaces is difficult. And secondly, it's not obvious that if you want to do planning, optimization over sequences of actions, that you need to go all the way back to pixel space to verify whether you've reached good states or not, states that get you to your goal. So I think it's just a generalization of that, and it's quite obvious. Now, the challenge for learning world models for the physical world is data. It's a theme that's come up a lot, right? So, in this talk, just to set the scope, when we talk about planning, we're really just looking at robot manipulation. And so here I'll constrain the discussion to that. So when we talk about, wanting to learn a world model for robot manipulation, what do we have available? Well, OpenX embodiment is one of the largest data sets out there, and here we're talking thousands of hours of video, right? Whereas on the other hand, action-free video data, YouTube, you can collect millions of hours of data. So what we hope to do is, in this work, is leverage action-free video to learn a world model in a sample-efficient manner. So we use a combination of observational data, which you can think of as like YouTube videos, and interaction data, so that would be robot manipulation videos. Yeah, I mean, I'm just trying to save time, but there's lots of ways, and I think this is quite a popular approach. People are really trying to think about how to leverage human videos to augment learning of physical world models and even just learning visual motor control policies in general. So here, it's not ideal. I'll just preface by saying that. This is really a first stab, and ideally what we want is a much more integrated system that's not as ad hoc. But in this work, we have a two-stage approach. So in the first stage, we first pre-train on action-free data, so YouTube videos, this kind of data, over 1 million hours of video. And the second stage, we then train on interaction data, so robot manipulation videos, and then deploy that zero shot on a robot. So as for the first stage, this is the method. There's really not much to it. The inductive biases are the masking strategy, but besides that, you can see how this generalizes beyond video. So on the right-hand side, you have a clean video that you sample from your data set. And then what you do is you mask it. So no augmentations, you just randomly drop out patches of the video. And then what you do is you encode that masked video, and you try and predict the representations of the unmasked patches. Okay, so you don't try and predict the pixels, you try and predict the representations of the unmasked patches. And those targets are produced with this network here on the right, which is an exponential moving average of the network on the left. And so this is the SSL objective. You have a prediction loss, which is a mass modeling loss in this case, in latent space. And we need some way to prevent collapse. So, if it's not obvious, there's clearly a trivial solution here, which is you can just output the same representation for every single patch, right? And that would clearly satisfy this objective, and you haven't really learned anything useful. So you need some way of preventing representation collapse. So for all the great benefits of doing, planning and world modeling in latent space, we have to find a way to learn a semantically meaningful latent space at the same time, which is an issue you don't have with generative models that are learning in the input space. But I think it's a problem worth trying to solve. And so here, how we do it is with this exponential moving average encoder and a stopgrad. This has been used for a long time in RL. It's been used also in self-supervised learning and BYOL, other methods. Jan mentioned in his talk, this is the approach we take right now. What's not great about it is it's a bit complex, and we don't really understand fundamentally what it's doing. There's some theory. It's a bit hand-wavy, and there's a lot of assumptions. So ideally, going forward, we brainstorm ways to have other more interpretable and simpler collapse prevention mechanisms. Okay, and so say we do this pre-training on over 1 million hours of video. We just take that unlabeled video, do that training, just mask modeling in latent space. Now we want to just first probe the representations. I mentioned you can collapse. So we want to just get a sense of how good are these representations, what information has the model learned to encode, what's wrong with it. So what we do in this case is we look at a frozen evaluation protocol. We take this network that we've pre-trained, the VJEPA2 encoder, which is also open source, by the way. And then what we do is we just train lightweight probes on top. So for instance, we look at image recognition. So what we do if we want to do ImageNet classification, we take an image, feed it into our video encoder, computer representation, and then we just train a head on top to do ImageNet classification. You could do this also with action recognition on kinetics, fine-grained gesture recognition, something V2, long video understanding on Coin. So we look at a wide range of different tasks to get a sense of what information the representation has captured and what it hasn't. And just a quick summary. So compared to VJEPA 1, here we scale the data, we scale the model, longer training, higher resolution, and we see improvements, so that's a promising sign. This is just getting a bit more into the details. Just for the sake of time, I'm gonna skip this and not spend too much time. But all I'll say is, the model has demonstrated really interesting scaling properties. It seems to perform well at kind of more abstract object recognition, action classification tasks, so ImageNet classification and kinetics with a frozen backbone. But one thing that kind of surprised us is this model is also really quite good at fine-grained gesture recognition, so something v2. Something v2 requires really fine-grained motion understanding. You need to differentiate putting something in something versus taking something out of something versus pretending to put something in something and then not doing it. So there's really a lot of subtleties of motion there. This is a task where lots of models struggle. This is also a task where you see a huge gap between video and image models usually. So, a Dino V2 or V3, for instance, or the state-of-the-art, SIGLIP or whatever you take there, usually you see a big gap with video models, and this is an area where when you take a frozen VJEPA encoder and just train a probe on top to do classification for this task, you get state-of-the-art performance here, actually, without even fine-tuning the model. Okay, so the representations are good. We've evaluated them on a wide range of tasks. One other thing we look at is we take the VJEPA 2 video encoder and we align it with an LLM to evaluate on video question answering tasks. So besides those probe-based tasks that we look at, there's a lot of really interesting VQA tasks that we look at. Perception test is an interesting one. MVP, minimal video pairs, is also another really interesting one, produced by Benno, who's, don't think Benno's here, but Benno is a student at Mila and one of the organizers of this workshop as well. And we get really good performance, specifically on spatiotemporal reasoning with this model. So you might think the video features are not really a bottleneck because the data is quite important when it comes to lots of these VQA tasks. And it's true, the data that you use for alignment is quite important for VQA, but we do see a quantitative difference between models depending on the features. So the features still do matter of the video encoder. Okay, one other really interesting task that we look at, and we kind of started expanding to, we thought, we have a predictor here, right? If we go back many slides, we have this predictor here that predicts representations of masked patches. It's not action conditioned, and it's not of the form that we want just yet, but we can use it to kind of do this action-free kind of video prediction of the future. And so one thing we do is we take, we look at Epic Kitchens, and the protocol we look at is this frozen evaluation. So we take a video on Epic Kitchens, we encode it, and then we predict the future of the video using our predictor in latent space. We put all of those representations together and we feed it to a probe. And we train the probe, but leave the models frozen. And the probe is trained to predict action classes in the future, essentially. Okay. So how Epic Kitchens works, there's, I won't remember the exact numbers, but you have to predict nouns and verbs. I'm sure I'm going to get this wrong because it's been a while, but I want to say roughly 300 noun classes and around a little under 100 verb classes. I don't remember the exact numbers, but put those together and that's the number of, multiply those and that's the number of actions that you have to predict. So here, let's just look at the video on the left first just to give you an example. So, okay, pause. And then when it pauses, that's the model's prediction for 1 second into the future. Put serial back into box. So, yeah, we got good performance here using a frozen backbone. So previously, the state-of-the-art on this task were actually video LLMs, like PlausiVL, for instance, that were fine-tuned specifically for Epic Kitchen's action anticipation. Here, with a frozen encoder, a frozen predictor, and we just train a probe on top, we actually achieve state-of-the-art performance on both noun prediction, verb prediction, and obviously the combination, which is represented in the bubble size, in the bubble here, the number represented there. One other thing, Jan talked about this already, so I'll just go over it very briefly. One other thing we look at using the predictor is intuitive physics. So again, these are just probing-based evaluations we look at to get a sense of how the pre-training went. I'll talk about the robot fine-tuning after. But here, what we do is we encode the start of a video, okay? And then we predict the completion of the video using our predictor. And in this case, we look at intuitive physics. Intuitive physics is usually measured using this violation of expectation framework. So it's a really fun kind of way to set up a benchmark. And in short, there are two continuations to the video. One is physically plausible, and one is not. And the model, it's essentially a classification problem. The model has to select which one is plausible and which one is implausible. And the way we do that is you predict the future of the video, and then we just compare the prediction error versus the two encodings. And the one that has the lower prediction error we say is plausible, and the one that has the higher prediction error we say is implausible. And there, actually with the VJEPA encoder, we achieve state-of-the-art performance on this task. Not just that, you see a huge gain in performance compared to previous state-of-the-art models, even conceptually similar models like video MAE. Video MAE is conceptually quite similar, except the prediction is made in pixel space rather than in abstract latent space. Video MAE is shown here in light blue. And so, yeah, we were quite surprised by this because we weren't really sure what to expect when we ran it. Now, just to nuance this, the model does well in some categories. Off the top of my head, I think object permanence was one that it did quite well in. So I was surprised if an object was there, it was occluded, and then you removed the occluder and it disappeared. So that quite surprised the model. Lots of other categories, still there's a lot of room for improvement. So collisions are not modeled very well. It's not really surprised by those. So things that relate to properties of the scene, such as spatial consistency, color consistency, motion consistency, those seem to be good, but there's still many, many categories of intuitive physics where the model is still quite poor. But it was promising to see initial signal there. Okay, and I think I'm doing well on time because I'm trying to wrap up for the poster session. But second phase now is after pre-training on observational data, we learn by interaction, so we fine-tune on a little bit of robot data. So here, now we freeze the encoder, which I mentioned was non-ideal. It's something eventually we want to get rid of and have an integrated approach. But now we freeze the encoder and we train an action condition predictor on top to just do next frame prediction in latent space. And we train on roughly 62 hours of robot video from the Droid dataset. Mila was also actually involved in the creation of the Droid dataset, so Mila has had a lot of contributions in general to this line of work. And after training, well, actually, just to talk about the training recipe, we have two losses for training this. One is a teacher forcing loss, and the other is a rollout loss. But essentially, it's just next frame prediction. The rollout loss just helps the model kind of get good at feeding back its predictions into itself and making autoregressive predictions. Okay, and now how do we do this with planning? So, as Jan mentioned, the planning algorithm we use right now is kind of dumb. Could be improved a lot. We're using the cross-entropy method. The data is there. It's 1997, so surely there are better things we can do, especially that we can backpropagate through this predictor, but it actually works, reasonably fine for what we're trying to do right now. And really at this stage, we're just trying to get the world model kind of to do basic robot manipulation tasks. The setting we look at is specifically image goals, because that's something you can just try zero shot. And so what we do is give it an observation. So say on the left here, this is what the robot currently sees. Okay, and then you have an image goal, which is the state you want the robot to get to. What you do is you sample lots of actions, you unroll your world model with those actions, and you select the actions that give you the lowest L1 prediction error at the end of the rollout. It's that simple. So this is an example, for instance, in our lab here, just upstairs actually. You have a start frame and a goal frame. And on the right-hand side here is the energy landscape. Okay, so what do I mean by energy landscape? So the y-axis, well, z-axis, okay, that's the error, that prediction error. So here we're referring to that as energy. And so we want to find regions of low energy. And then at the bottom plane here, delta x, delta y, these are delta x, delta y actions. So if you fix, so z is, for robot motion, is up and down. So just fix z equals 0 just to be able to visualize the landscape. And just sweep a bunch of actions, delta x, delta y, and plot the loss there. And that gives us the energy landscape. And so one thing you can see is the energy landscape, surprisingly, is actually quite smooth in this case, and it's actually supports planning pretty well. And in this case, the minimizer of this energy landscape actually corresponds to the ground truth action to take you from the start frame to the goal frame. So this is just single goal reaching, pose matching, and this would be the first sanity check before doing anything. Just for time, I'll skip this, but here, we look at pose matching along kind of the 3 coordinate axes, just as a sanity check. We're able to get within 4 centimeter prediction error, deployed zero shot on our robot, and this is from an extrinsic camera. So this is the camera view that the robot actually sees. We don't tell the robot camera extrinsic, so it doesn't know where the camera is, and there's no risk camera. So the robot is doing all of this from that visual input, and it's getting within, 4 centimeter error, roughly, for all these tasks. So it's a good sanity check, especially that we only use 62 hours of robot video to train the world model. Right? Here I'll show examples of pick and place. And one of the limitations of the model right now is it's not very good at, let's say even longer horizon rollouts. And so to handle non-greedy tasks, what we do is we have image sub-goals. So the first goal, you can see here on the left, is grasp the cup. The second goal is lift it, and the third is place it. And then here, let's see the robot actually planning closed loop trying to do this. So it grasped it, it's lifting, it's navigating. And places it. Okay, so this is fully zero shot. The model was never trained on this task. It doesn't understand the concept of cup or shelf or pick and place. It's really just planning to reach the goal state. And on the right here, we deploy the same model, zero shot, but in another lab. Okay, so we just take that same exact code, deploy it on a robot in another lab, and with a similar setup. Here, pick and place of a box. So it grasps the box, and is able to move it and place it. So yeah, that's interesting. It just shows the generalization capabilities. It's working zero shot with clearly very different labs, very different backgrounds. And these labs are obviously not in the training data either. One thing we compare to is Cosmos. So now there's Cosmos 2, so it's worth evaluating that. But Cosmos at the time was released as, maybe a lot of you are already familiar with it. It's a video generation model that's action conditioned. Yes? Yes, so we're doing blocking control. The concept of frequency is not exactly the same as if we were doing non-blocking control. So we wait for an action to complete before sending and recomputing and replanning. Here we're running on 1 GPU. This is the planning time per iteration. So it's 16 seconds. It's not closed loop. However, I will say Artem, who's a student here, there's very simple optimizations you can do. You can parallelize this even across just a few GPUs, and you can get this working in real time, essentially, without these kinds of long pauses. Yeah. Okay, but here, so this is just on this is not in this paper. This is kind of follow-up work we've done doing inference, setting it up on the cluster. But here, for instance, you can see already, as inefficient as 16 seconds per iteration is, you can see trying to do closed loop planning using video generation with a diffusion model. I mean, already at 4 minutes, we can only do 80 samples, right? So maybe then you need a lot more GPUs to parallelize this, a lot more tricks. But again, it's just this idea that maybe pixel space is not the optimal space to plan in. And I should say Cosmos is not going back exactly to pixels here. It's a, I don't recall the space, but I think it's a VQVAE or VQGAN type space. So it's compressed, but it's still semantically very close to pixels. And so the point here is, maybe you can actually still get great planning performance and very efficient, and still comparable accuracy without having to go to pixels. One other model we compared to is a VLA. At the time, we compared to Octo. Now there are newer models, but the great thing about Octo at the time is it also supported image goals. And so, here we took a VLA fine-tuned on Droid, so fine-tuned on the same data, and we deployed it on the robot in both labs, Lab 1 and Lab 2. You saw examples of both, and we look at a wide range of tasks. And we do see zero-shot, the world model-based approach is able to perform better than the VLA approach. Now, VLA approaches have improved a lot also since then, and they support text goals. So I think that's an interesting avenue to explore going forward in the future. And then, we don't have a decoder because we're not going to pixel space, but you can train a decoder offline. This is also Artem's contribution to this work. And so on the left is the original video. On the right is a rollout, so given the first frame, doing a rollout of the actions and then decoding back to pixels to kind of just visualize the world model's predictions. And you see the world model's predictions are actually quite faithful. And if you invest in having somewhat powerful of a decoder, you can still get very strong, physically consistent video generation if you want to go back to the pixel space. Okay, so in conclusion, well, representation learning matters for world modeling. And it still remains an open question. What is the optimal representation for planning? In this project, we had a two-stage approach. We learned good visual representations, we probed it, and then we trained a world model on top. But ideally, I think you would learn representations simultaneously. And so representations that you learn simultaneously are going to be optimal for planning, or at least better. And maybe try and do that hierarchically. Interesting, yeah, I won't go into it, but lots of interesting notions of hierarchy to explore there as well. And yeah, maybe I'll just end it there for the sake of time. Maybe I'll leave time for questions in case there's anything. Yeah.
All right, so thank you very much for taking some time back. So we have time for one question or two. Yeah, so do we have the microphones or not anymore? Okay.
Cool. Thanks for the talk. Yeah, my question is for planning. So your horizon length was 1. How big is the delta pose? Because 16 seconds could be a lot depending on the delta pose.
20 centimeters
Okay.
along each coordinate axis. So
each pause in the video could that be 1 horizon length? I saw lots of
yes,
pauses.
exactly.
Okay.
Exactly,
Perfect.
exactly.
All right, thank you.
Thanks. So one last question. Do you have a question?
How did you decode back to pixel space? Conditional diffusion?
Yeah, I don't know. Maybe Artem, do you want to talk about that? How do you go back to pixel space? Do you want to talk about the decoder that you trained?
You can just have representations as input and pixels as output with feed-forward model, with diffusion model, however you want this. It works very well.
All right, so thank you very much. Thanks, Mido again. So we now have the poster session, so you can see they are being set up there. So we can slowly set everything up and move there. And in terms of talks, we are done for the day. It will start again tomorrow morning. Thanks.